Yeah. Okay, sir.
Good morning, Shailesh sir. PC here.
Ah, PC. Good to see you. Not see you, hear you. Yeah.
And Dr. Ravi, good morning.
Good morning.
All well?
Yeah, all well, sir.
Good, good, good.
सर नायक सर आपका कैमरा कुछ आउट ऑफ फोकस क्यों दिख रहा है?
वो भी हो जाएगा.
अच्छा.
Yeah. I think he had focused on a. We'll do that.
Now it is. Yes. Suddenly I thought it was so clear.
This is a new system we have started in last 1 month. So थोड़ा सा adjustment ये सब चल रहा है.
Now it is so clear.
Yeah.
As if we are sitting in a room. It is so clear now.
No, it's a very good system. And only thing is proper adjustment has to be made. So.
Good morning, President Sir. Shailesh Nayak Sir, namaskar.
Bansal, good to see you. Namaskar.
Namaskar. Good morning, everybody.
Good morning.
Namaskar.
Good morning.
Good morning, Dr. Bansal.
Good morning. How are you, Dr. PC?
Yeah, fine.
Good. That's really good. At least we are able to see each other's face and chit chat a little bit. Otherwise, the situation is not really very healthy.
Yeah. No, we actually, up to last moment, we were thinking we would be able to go. Only in January, we thought that it won't be possible.
Okay.
And everybody was looking forward to go there.
Correct.
Because ultimately, of course, you can see everybody, but the physical meeting has its own advantages.
Absolutely, sir. That cannot be replaced, actually, let me tell you.
Because you can talk many other things apart from this. Here we will be only talking about the.
Correct, sir.
Good morning.
Good morning.
Good morning, Shailesh Nayak ji.
Good morning.
Dr. Bhardwaj has joined. Huh? Good morning, Dr. Bhardwaj.
Good morning.
Hi.
Dr. Ravi Chandran.
Good morning, Anil.
How are you?
Good morning. Good.
Bharadwaj sir, good morning.
Good morning, ji. Good morning.
Good morning, sir. Professor Chaudhary from Kurukshetra University Department of Geophysics.
Good morning, Chaudhary.
Morning, sir.
Good morning, sir. VC sir आ गए तो उनको भी स्पॉटलाइट कर दो.
Good morning, sir. Good morning, Kalachand Natwadia. Namaskar.
Sir, we can start now.
So Ravi, what's for you in budget? Anything spectacular?
Nothing special. We know already whatever.
If we are able to save to the last years, I think that should be achievement.
Good morning, Ravi Garu. Venkateshwara from JNTU.
Good morning.
Shailesh Nayak Garu, namaste.
Namaste. Good morning, Kalachan.
Very good morning.
Doctor.
Good morning. Good morning, everyone. I am Dr. Meghali Borua from Department of Geology, Northeastern Hill University, Shillong. So, should I start the program?
Yeah, please go ahead.
Okay. Okay. Thank you, sir. So, a very good morning to all the dignitaries and participants joining us from different zones across the globe. I, Dr. Meghali Borua, on behalf of Department of Geology, Northeastern Hill University, Shillong, and Indian Geophysical Union, cordially welcome you all to this inaugural ceremony of 58th Annual Convention of Indian Geophysical Union on recent advances in earth sciences with special emphasis on natural hazards. So to start the session, I would like to say that light and brightness has always been equated with positivity and motivation, and harbinger of good, which is associated with spiritual beginnings, and the presence of Diya ensures success. So now we will have a virtual lamp lighting ceremony followed by Saraswati Bandana.
या कुन्देन्दु तुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा शुक्लां ब्रह्मविचारसारपरमा आद्यां जगद्व्यापिनीं वीणा पुस्तकधारिणीम् अभयदा जाड्यान्धकारापहा हस्ते स्फाटिकमालिकां विदधतीं पद्मासने संस्थितां वन्दे तां परमेश्वरीं भगवतीं बुद्धिप्रदां शारदाम्
So, and it is my absolute pleasure to call upon Professor Biswal, Convener, Local Organizing Committee, 58th Annual Convention of Indian Geophysical Union, and Head, Department of Geology, Northeastern Hill University, Shillong, to address the welcome address for this inaugural session.
Yeah. Good morning, everyone. Good morning, Dr. Ravi Chandran Saab, Secretary, MOES, and Professor Shailesh Nayak, President IGU. Our Vice Chancellor Sir's connection is dropped, so it will take another 2-3 minutes to join. So I thought in the meantime, I'll just interact with the audience. And sir, we all know that this is the 58th Annual Convention of IGU, and after its birth in 1963, IGU is continuously holding its annual conventions, successfully holding its annual conventions. So like any other year, this year we could not hold it in a physical mode, but definitely we would love to have it in a physical mode, and probably as time permits, we will be having it in the physical mode, some workshop or some activity, so that the morale and the activities of the geophysical scientists or the scientists involved in the geophysical studies, they are able to contribute, they are able to interact, and they are able to get the good network amongst themselves for bringing up the cause of good geophysical studies in India. Today, as such, we'll be having an inaugural program, followed by which we'll be having a technical session. All the technical sessions are divided into 8 technical sessions. And yeah, our VC sir has joined. So in place of going further, I would like Meghali, Dr. Meghali, if you can invite him. Actually, there is a meeting at 10:15. State government's meeting, and wherein our VC sir is scheduled to be there, so he's on the way. So before coming in between the audience participants, I would like to request Professor Prabha Shankar Shukla ji, Vice Chancellor, Northeastern Hill University, to give his welcome address. Sir, please.
Okay, good morning to all. Enga Padiao Sang Bhavaya Ficha Varra. Welcome to all of you in the 50th Annual Convention, Indian Geophysical Union. First of all, I would like to welcome Secretary and Chief Guest of the function, Dr. M. Ravichandran, and President Shailesh Nayak, and other dignitaries directly or indirectly concerned. One more thing, the society established in 1963, and Indian Geophysical Union started with the initiation and blessing of the 10th K.R. Raman, Professor S. Bhagavanta, Professor M.S. Krishnan, Dr. S. Balakrishnan. In the past, the union has proved a platform for dissemination of knowledge, sharing thoughts, views, interactions between postgraduate students from various universities, young scientists, researchers, eminent geoscientists, understanding societal problems and finding feasible solutions, and discussions on current topics and recent phenomena, which are required for the development of society and continues to serve the earth scientific community of the country. Many geoscientists supported enormous for sustaining Indian Geophysical Union and its development. We salute them for their contribution and encouragement. The motive of IGU is to encourage young researchers in improving their research capabilities, research articles, and widen their knowledge in globally. IGU requested senior scientists to provide necessary Geoscience,
Seems he is driving, so his connection got broken. So should we wait for some more seconds?
No, if possible, I think probably if it is only audio, he may be able to talk.
Yeah, it seems. Yeah, that's what I wanted to, but it is difficult to intervene when.
Because I think the bandwidth is not sufficient.
Yeah, although he is there, might have reached governor's house.
Okay.
There is a meeting is there. So.
No, we can continue. If he comes back, we can.
Yeah, that's right.
Because 10:15 is already there, so it must be going for meeting. So.
Yeah. So, dear participants, with the permission of our President IGU and with the permission of Secretary Ministry of Earth Science, I would like to welcome you all. Although whenever our VC sir will join, we may request him to say a few more words. But from 10:15 onwards, his meeting is fixed. That much I know, I'm sure. So I welcome you all for this very important program of IGU, and especially with reference to Northeastern region, it is of great importance because we are dealing with the natural hazards during these 3 days convention. Although if we would have met physically, it would have been a totally different outcome. But physically, if we are not meeting, still we'll try to provide best possible outcome and best possible discussion and the report for necessary action and further actions. So with this, I would like to request the MC, the Master of Ceremony, to please go ahead and go along with the program, please.
Thank you, sir, for your admiring speech. Now I take this opportunity to introduce our next speaker, Dr. Abhayram Bansal, Honorary Secretary, Indian Geophysical Union 58 Annual Convention. Dr. Abhayram Bansal, Senior Principal Scientist, National Geophysical Research Institute, Hyderabad. He has made out significant research work in the field of applied geophysics, primarily focusing on potential field and seismological data modeling and analysis. He has proposed a method for estimating depth to the bottom of magnetic sources from aeromagnetic data and applied it to Central India, Germany, Australia, and Iran. He is a recipient of prestigious National Mineral Award in the year 2005 by Government of India and Krishnan Gold Medal Award 2008 by Indian Geophysical Union. I welcome you, sir, for giving brief overview of this program. Over to you, sir.
Good morning to all. Dear Professor, I am Ravichandran, Secretary MOS and the Chief Guest. Professor Shailesh Nayak, the President of IGU. Professor Prabhashankar Shukla, the Vice Chancellor, NEHU University and Chairman LOC. Dr. V.N. Tiwari, the Director, CSR NGRI and Vice President of IGU. Dr. Kalatan Sen, the Director of India Institute of Himalayan Geology and Vice President of IGU, Dr. Sunil Singh, Director PSR NIO, Professor A.K. Singhvi, Professor Devesh Walia, EC members, awardees, and delegates. Very good morning to all of you. As you know, the Indian Geophysical Union started in the year 1963, and it provides a platform for dissemination of knowledge, sharing of thoughts, views, and it provides a platform between interaction between postgraduate students, researchers, and eminent scientists. The IGA is organizing its 58th annual convention, although it's virtually at Northeastern University NEHU, Shillong during February 2 to 4, 2022. This 3 days annual convention covers award talks and various sessions in different disciplines of our sciences. Around 125 research papers will be presented during this 3 day annual conventions, in which 80 will be oral presentation and 45 will be poster presentation. In general, 300 to 300 delegates every year attend the Indian Geophysical Union, and we are expecting the same number of delegates will attend this time. And this time we have made it totally free for the postgraduate student and researcher. And due to that also, we are hoping that more number of people, researcher will attend, and it will benefit to the both eminent researchers and young researchers. The IGU congratulate all the medal winners, that is Professor K.R. Ramanathan Award, Memorial Lecture, Decennial Award, Krishnan Medal, Anil Talwani Memorial Prize, IGU Harinaran Lifetime Achievement Award, IGU Electrotech and Geometric Endowment Award, Women Programs and other awards. We place on record our thanks to the local organizing committee, Professor Devesh Walia, convener LOC, and his team for their committed involvement and help in organizing the 58th annual convention. And we trouble them in the night also. We are calling them many times. And thank you very much for supporting us, sir. The IG is inducted to Professor Shailesh Naik, the President IGU, Professor Harsh Gupta, Professor V.P. Dimri, Dr. V.M. Tiwari, Dr. Kalatan Sen, Dr. R.K. Srivastu, Dr. Sunil Singh, the Vice President of IGU, for their unequivocal support and guidance. IGU is also inducted to all the EC members, fellows, and members for their continuous support. We also thank the chairperson and reporters of the technical session for accepting our invitation at very short notice. Thank you very much, sirs and madam. And we have made the co-chair young people so they can be the future leaders, and we have given equal representation for chair to the women to making women more power in the coming years. That is the motto of our government also. Our special thanks are due to Dr. Triple Prasad, Secretary IGU, Mr. Rafiq Muhammad Attar, Treasurer of IGU, for continuous support in executing various work related to the annual convention throughout the year, and we thanks other members also who supported directly or indirectly. Thank you very much. Thanks to all of you.
Thank you, sir, for your admiring speech. Now I take this opportunity to introduce our next speaker, Professor Shailesh Naik, President, Indian Geophysical Union 58th Annual Convention and Director, NIAS Bangalore, and Chancellor Terry School of Advanced Studies, New Delhi, for delivering the inaugural address. He is the chairman of the Research Advisory Committee of the National Institute of Oceanography, Goa, and Center for Earth Science Studies, Tiruvananthapuram. He has been member of many national committees related to earth science, coastal protection, mangrove and coral reef, and Coastal Zone Management formulated by Ministry of Science and Technology, Ministry of Water Resources, and Ministry of Environment and Forest, Government of India. He has been a recipient of many prestigious awards such as National Mineral Award, Vaskara Award 2010 by Indian Society of Remote Sensing, Dehradun, Vikram Sarabhai Memorial Award for 2012 by Indian Science Congress Association, Kolkata, Harinarayan Lifetime Achievement Award in Geosciences 2013 by Indian Geophysical Union, Hyderabad. I welcome you, sir, and would like to request you for delivering the inaugural address. Over to you, sir.
Dr. Meghali, Dr. Ravichandran, Secretary, Ministry of Earth Sciences, and today's chief guest, Professor Shukla, Vice Chancellor of NEHU, Professor Dinesh Walia, Professor Ashok Singhvi, and all awardees, Dr. Abhay Bansal, my colleagues at IGU, as well as the dear participants. Very, very warm welcome to all of you. Good morning. First of all, I would like to thank Professor Shukla and Professor Devesh Walia for agreeing to host this 58th annual convention of the IGU. And today's topic, we have been working on the very recent advances in the earth science with specific emphasis on the hazards, essentially because Northeast, we wanted to focus on some of the hazards which there are, like floods, earthquakes, landslides, and many others, which is very important for us to understand. If you know that today there are two major challenges. One is the impacts of the natural hazards and the climate change on the sustainability of humankind. The most places on the earth are vulnerable to one or other hazards such as floods, droughts, earthquakes, cyclones, storms, tsunamis, landslides, etc. We have to live with these hazards and prepare ourselves to respond to hazard to save lives. Natural hazards essentially represent the extreme fluctuations in the average dynamic state of the Earth system. The effective response to any such event depends on the quality of scientific knowledge about a particular hazard, expertise of the organizations who are responsible for responding to extreme events, and the hazard consciousness of the communities involved. The extreme or hazardous events interacting with vulnerable human and natural systems can lead to disasters, especially in absence of responsive social system. Hence, the building of effective resilience to natural hazards needs to be addressed at the three levels of the system: the global or the earth system, social system, comprising of infrastructure, governance structure, industrial capability, and the human system or the people. The knowledge about Earth system is critical to build an effective mechanism for an accurate detection and monitoring of hazard, early forecast, and setting up of warning services, and the constant assessment of hazard and vulnerability of the people. The basic knowledge element include the physics of hazard generation, their space-time history, and details of Earth processes. Global observations, including satellite and aircraft observations of atmosphere, ocean, land surface, cryosphere, processed in a real time, are required for hazard prediction models. Satellite provide capability to observe the Earth system at varied temporal, spectral, and spatial resolutions. GIS having capability to acquire data from many platforms, from variety of observing stations, organize into a database, analysis and modeling, and visualizing the various hazard processes, as well as Conveying advisories through web and location-based services is an extremely powerful tool that had made difference in responding to any hazard. There has been all-round improvement in forecasting of hazards during last 2 decades due to augmentation in the observing systems, understanding of physics, modeling, and forecasting. However, we yet to develop complete resilience to all kinds of hazards. The building capacity to forecast an early warning is not sufficient to mitigate risk from the hazards. The existing social systems, political, administrative, economic, and industrial structures are equally important to provide resilience to society. It is seen that though hazard-related information has been provided, in absence of effective communication to people at large or lack of ability of local administration to respond to an event still causes loss of lives and damage to the property. The setting up of national disaster management authorities at state and central levels and National Disaster Response Force in India has tremendously improved the response mechanism. The development of information system and emergency plans for evacuation, rescue, and relief by these agencies has helped to set up a very effective and efficient response mechanism in the country. The shelters have been set up in coastal areas to withstand any hazard, equipped to meet any calamity. Apart from these shelters, schools, colleges, and other public utility buildings are also used for providing temporary housing. The major damage occurs to the communication and power network during such events, and it is pertinent to house these networks underground to keep them functioning during an hazardous event. All police stations, fire brigades, government administrative buildings should be made hazard resistant in vulnerable areas. Periodic mock drills and communication tests are most critical and should be carried out religiously. It is also realized now that even if we have early warning system and responsive organization to address any event, without supportive human system, we can still lose lives. In India, over the period of time, especially on the East Coast, the trust of local communities in the forecast as well as in the local administration has increased manifold. They are now reasonably well educated about possible dangers from cyclones and tsunami. It is desirable to educate people, especially students, about the science, social impact, and the rescue measures. It has been observed that in many villages have volunteers to inform people about potential dangers as well as assist administration in directing people to safe places and providing necessary relief. After the event, they also provide evidence of damage and assist in providing compensation to affected people. Such citizen science-centric initiative can be immensely beneficial of recovery programs. Such people have to be equipped with a few tools such as smartphones and trained to carry out their functions. There is also need to consider that how the anthropogenic activities have influenced the hazard processes in generating extreme events. A changing climate leads to changes in frequency, intensity, spatial extent, duration, and timing of extreme weather and climate events. The recent IPCC report emphasizes on likely increase of intense rainfall events and heat waves in South Asia. Though it is difficult to relate the individual event to climate change, we are experiencing increasing events of heavy rain and snowfalls, heat and cold waves, drought, as well as increasing frequency or intensity of tropical storms. Rising sea level further compounds the impact on coast. In a recent study, it was shown that the increase in the air pollution and the other particulate matter in the atmosphere can affect cloud development in ways that reduce the precipitation in dry regions or season while increasing rain, snowfall, and intensity of severe storms in wet regions or seasons. We need to produce special climate products to monitor such events. An effective collaboration with the neighboring countries to build observational systems, develop standards for the data exchange, networking of required services, and prepare human communities has to be ensured. Various fora such as Indian Ocean Rim Countries Association, Bay of Bengal Initiative for Multi-Sectoral, Technical and Economic Cooperation, Regional Integrated Multi-Hazard Early Warning System for Africa and Asia, etc., are critical in developing resilient response mechanism. The collaboration with international research institutes to address science questions, improving understanding of interaction between Earth system processes is essential to build improved predictive models. There is a need to enhance our capability for responding to cyclones and other hazards at regional, national, institutional, and individual level. Communicating the information to all stakeholders is another critical area. The effective communication with local administration, media, as well as people at large is vital. An education system that produces scientists and managers are needed to implement such approach. We need to enhance our capability for education at a regional, national, institutional, and individual level. There is a need to constantly evaluate and improve the performance of forecasting system as well as to address the new challenges. I'm sure many of these topics will be intensely debated in next 3 days. I wish very fruitful discussion during this annual convention, and I again welcome all of you to this 58th annual convention. Thank you very much.
Thank you, sir, for your enlightened talk. Now I take this opportunity to introduce our chief guest, Dr. M. Ravisandran. He is the Secretary of Ministry of Earth Science, Government of India. His research interest includes atmospheric and ocean dynamics, ocean observations and modeling. He is the first recipient of Dr. Srinivasan Endowment Award by Ocean Society of India, National Award in the field of ocean science by Ministry of Earth Science. He has published more than 150 publications in peer-reviewed journal. I welcome you, sir, and kindly enlighten our participants about 58th Annual Convention of Indian Geophysical Union. Over to you, sir.
Thank you. Thank you, Magani. Professor Sailesh Naik, President of Indian Geophysical Union. Professor Prabhasankar Shukla, Vice Chancellor of Northeastern Hill University. Vice President of IGU, Dr. Kalachan Sain, Dr. Tiwari, Dr. Srivastava, and Dr. Sunil Singh. Dr. Deves Walia from Northeastern Hill University. Dr. Bansal, General Secretary of IGU. Various office bearers of IGU, awardees, scientists, students, ladies and gentlemen. A very good morning to all of you. Thank you, Northeastern Hill University, for hosting this 58th IGU Annual Convention on recent advances in earth sciences with special emphasis on natural hazards. And unfortunately, we couldn't meet in physical, but we are able to manage through virtual. It is indeed a great pleasure to be here among the geoscientists who have virtually assembled for deliberating on very important and yet challenging issues related to geoscience, especially natural hazards. Government of India says the common global goal for meeting the demand of the day for managing the risks from various natural disasters. The optimum utilization of our water, land, and natural resources is extremely important in achieving the sustainable development goals towards the disaster risk reduction nation. India targets a build to build a safer and disaster resilient nation by a holistic, proactive, technology-driven, and sustainable development strategy that involves all stakeholders and fosters a culture of prevention, preparedness, and mitigations. We are in the process of improving effective monitoring system, understanding the processes, modeling them, and forecasting various natural hazards. Among the natural disasters, hydrological disasters such as storms, droughts, floods, and extreme temperature, all in the list of world's worst disasters. Storms and floods account about 79% of the total disaster due to weather, water, and climate extremes, and cause about 55% of the lives lost and 86% of the economic losses, and drought costs roughly about 35% of the lives lost. This problem is further compounded by climate change and its impact on water availability, both globally and in India. Successive monsoon years have seen increase in extreme rainfall events in India during the last 2 decades. Cloudbursts and flash floods events have become more catastrophic in terms of economic losses and loss of life and property. Hydrological variability poses one of the greatest threats to the world population today. With the present day technology and know-how, we should be able to translate the forecast with the improved accuracy level into impact-based warnings and effectively disseminate the timely action by the disaster managers. There is a strong reason to prepare ourselves to face the potential disaster associated with the various natural hazards. As already pointed out by President, also in the IPCC, the extreme weather events will continue to increase, and hence we need to be prepared for water management and hydrological and all other disasters. Natural hazards vary from both space and time, some in the localized area but intense, like lightning, very short duration but intense, and other for long period and also global in nature, such as climate change, sea level rise, etc. It is important for us to describe various natural hazards events to the people and various stakeholders, societies, so that they have better prepared or informed about the various disasters, such as cyclone, earthquake, tsunami, lightning, and so on. It is imperative to inform the risk associated with these various natural disasters to the people, common people. In the warming world, we expect to be more severe storms, more severe droughts, more wildfires, etc. There is no way to avoid the natural hazards on a dynamic earth, but there are certainly ways that we can learn to live with them to mitigate the risk to the society. It is almost evident that widespread and rapid changes have occurred in all 5 spheres, such as the atmosphere, hydrosphere, cryosphere, geosphere, and biosphere. As an earth scientist, it is our endeavor to improve our understanding in all the 5 spheres and also its interaction and various timescales. As a earth scientist, it is our endeavor to work towards securing lives and livelihood of the people in a sustainable manner and also contribute to India's economy growth. We need to have an informed science-based policy decision to the government to have a transformative change in a sustainable way. Of course, the earth system is a coupled system, and we need to have a collective approach, various disciplines at various time scales. So hence it is imperative to promote the discovery, to provide a new perspective on the earth system for better understanding the earth processes and apply the understanding or apply the knowledge for a sustainability of the planet Earth as well as for the social benefit. I am sure IGU continue to promote geoscience in India, particularly to bring out societal relevant issues to the policymakers. Link and collaborate with other societies, especially geoscience, maybe ocean meteorology and geological societies or organizations to meet the earth science related scientific and societal challenges I'm happy that IGU is involving and promoting early career researchers in interdisciplinary research in earth science field. Of course, early career researchers should regularly conduct social events, short courses, workshops, etc. to bring new ideas, suggestions, vision for the future earth science research for socio-economic benefit of our country. The earth sciences plays an increasingly important role in the exploration of energy, mineral resources, and likely to increase its potential, also providing important advice in finding resources and mitigating natural hazards, thus supporting effective and secure society. We must together take steps now to recognize the problem, analyze the risk, and plan ahead. There is much more to be done, and solution is in the hands of all of us as government, as industry, as citizens, stakeholders, and scientists. I hope this annual event will dwell upon on all these aspects and bring out the actionable recommendation and concept document. I wish this event a great success. Thank you, one and all. Thank you.
Thank you, sir, for your admiring speech. And we are really grateful to you for the time and effort you took to share your thoughts with us. Thank you, sir. So now it's time for the announcement of prestigious awards by Indian Geophysical Union 2021.
अरे वेट करो, गलत, हाँ वेट करो, ऊपर जाओ, वापस जाओ. Yeah. So, sir, I would like our President, Indian Geophysical Union, to please declare these awards, sir.
Thank you. The IGU Professor K.R. Ramanathan Memorial Lecture has been awarded to Dr. M. Ravichandran. And after this, it would be delivered, this lecture. Our hearty congratulations to Dr. Ravichandran, and both to take over as a Secretary Ministry of Earth Science and to get this Memorial Lecture Award on personal behalf of me as well as all members of the IGU. So congratulations, Dr. Ravi.
Thank you, sir. I humbly accept. Thank you.
The second IGU Harinarayan Lifetime Achievement Award has been conferred to Professor Ashok Singhvi. Professor Singhvi is known for his work on the paleoclimate, and he's present here. On personal behalf of me and the all members of IGU, I heartily congratulate Professor Ashok Singhvi.
Thank you so much.
IGU Decennial Award has been conferred to Professor M. Radhakrishna. Professor Radhakrishna is a professor in the Department of Earth Science, IIT Bombay, and very active member of IGU. My heartiest congratulations, as well as all members from IGU, to Dr. Radhakrishna. Congratulations.
Thank you, sir.
IGU Anitalwani Memorial Prize has been conferred to Dr. Abraham Bansal, who is also a secretary of IGU and has made very significant contributions in applied geophysics and a very active member of IGU. On behalf of me and all IGU members, I congratulate Dr. Abraham Bansal. Congrats, Bansal.
Sir, thank you very much.
The IGU Christian Medal, which is one of the most prestigious medal for the young people, has been given to Dr. K.M. Srijit. On behalf of me and on behalf of all IGU members, I congratulate Dr. Srijit for his work in marine geophysics.
Thank you, sir.
IGU Electrotech and Geometrics Endowment Lecture has been conferred to Sri Rajesh Kumar Srivastav from the geologist in ONGC. On behalf of me and all members of IGU, I congratulate Dr. Srivastav for his meritorious service. IGU JJ NEHU Young Scientist Award has been conferred to Dr. Anil Kumar for his work in quaternary. On behalf of me and all members of IGU, I heartily congratulate Dr. Anil Kumar and wish him all the best in his future career. The IGU Professor D. Lal Best Paper Award has been jointly given to Dr. Das, Dr. Malik, and Dr. Rasya. My congratulations on behalf of me and all members of IGU to Dr. Das, Dr. Malik, and Dr. Rasya for their best paper.
Thank you, sir. Thank you very much.
There is also a grant given to women researchers and student toppers. This has been, this year, of course, it's not a physical, so we have not been providing travel grant. But the young women researchers of 2021, Ms. Anjali Dikshit from IIT Kanpur, Ms. Shiva Kalyani from Wadia Institute of Himalayan Geology, Ms. Vastika Bhaumik from Center for Ocean, Rivers, Atmosphere, Coral in IIT Kharagpur, and Ms. Seema Begum from CSIR and GRI. My hearty congratulations to all young researchers as well as from all members of IGU. Congratulations. The Professor Jagdev Singh and L. Balkrishna Memorial Grant is given to Dr. Abhinav Saini, Nishita and Sweta from Kurukshetra University, Abhishek Sharma and Ravi Shankar from Indian Institute of Technology, Bombay, Prapti and Richa Sharma, Indian Institute of Technology, Bombay, Shivangi Bharadwaj and Ravi Banaras Hindu University, Varanasi. My congratulations to them.
Thank you, sir. With the permission of the chair, with the permission of the chief guest and the president IGU, I want that all the awardees may come one by one. Means they may switch on their video. We'll put them on the spotlight for the sake of photograph. So it should not take a long time. Professor M. Ravichandran and Professor Shailesh Nayak ji may remain on the spotlight. Rest other spotlights may be removed. Yeah. So this is the first award. Hopefully photograph is taken because it is being recorded also. Now I would like to request Professor Ashok Singhvi ji to be there. Yeah. Then Professor M. Radhakrishna, if let him switch on his video. Yeah, please, sir. Yeah. And you may click the photograph if you want. Otherwise, it is being recorded too. Dr. Abhay Ram Bansal ji. Abhay Ram Bansal ji, please switch on your video. Yeah, yes. Yeah, Dr. K.M. Shrijit. Dr. Anil Kumar. Dr. Anil Kumar. You are there. You need to only switch on your video. No, I think some issue. Rajesh Kumar Srivastav ji, if you are there. No, I think he is not there. Then all three distinguished scientists, Ganshu Das, Jyotirmay Malik, and Rasia. You three of you, please come and please switch on your video if possible.
Ravi, you keep your video on.
Put your video on so that Jyotirmay Malik.
Sir, my video is on.
Yeah.
Malik.
Sir, my video is on.
यार मलिक को चूज करना भाई. No, your name is you are joined with some other name.
Sir, Jyotirmay, my first name.
Oh, Jyotirmay, that's what we are looking for. Jyotirmay, yeah, because we were looking for Malik. And Rasia, you are there? Rasia?
Sir, Russia is in Italy. I'm sure.
All right, no problem.
It's too late for her.
But
yeah.
she joined. Otherwise, I checked some time back.
Okay.
But it's okay. It's all right. Now she is not there. Yeah, we can have photo. Yeah, thank you. Then Anil Talwani Memorial Grant. All four of them: Anjali Dikshit, Seema Begum, and Shiba Kalyani. We are very sorry that we wrote Shiva Kalyani, but her name is Shiba Kalyani Sahu. So all three of you, if you are four of you, and Swastik Bhaumik, if you all are there, please switch on your video. Now, they were there. Swastik Bhaumik, yeah, organizer, please choose Swastik Bhaumik. Her video is on. Shiba is not there, it seems. Shiva is also there. Shiva also, you switch on your video. I don't think she has got the video. Seema Begum. Yeah, she has not joined. Anjali.
Hello, sir. This is Anjali.
Yeah, your video is also not on.
Yeah, sir, but I don't, due to some error, I was unable. Can you just give me 1 minute so that I can check the settings?
Seconds are possible.
Okay, then. Okay.
Other two have not joined. Seema and Shiva. Shiva, your video is also off. Otherwise, you have joined. Shiva Kalyani, you don't have camera, it seems. Anjali, your 1 minute is going to be over. Yeah, I think we can have it some other time. Your video is still giving some problem. Meghali, you may please take on from now.
Thank you, sir. So now moving ahead, now I would like to request Dr. M. Ravisandaran, Secretary of Ministry of Earth Science, Government of India, for Professor K.R. Ramanathan Memorial Lecture. Over to you, sir.
Sir, 1 second, I'll stop. just put in Anjali one for a second too. Anjali now, after trying hard, her video is on.
Yeah, sorry sir for the delay. I'm really sorry.
Yeah, all right. Yeah,
Thank you.
for photographs, yes. All right. Thank you, Anjali.
Thank you, sir.
Sorry for interruption.
Thank you. Maybe the host can allow to share my screen. I've been not allowed. Can you please allow us?
Sir, you can share now. You can share now, sir.
You are able to see my presentation?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
First of all, thank you, IGU for honoring me to make a presentation, or maybe the Professor K.R. Memorial Lecture on behalf of all the things. So actually, I have chosen the topic such as very different. I have seen the convention, whatever this 58th convention, the main points, what I have seen that it is mostly recent advances in earth sciences, and it has been highlighted. There are many topics related to atmosphere, ocean, geoscience, but nothing covered in cryosphere. So I thought maybe it is better to make some, what are the recent advances has come in cryospheric aspect, especially in the recent few years or maybe a decade. Mainly focus on what is called hazard, natural hazards, or maybe the intervention by the polar areas to the tropics. So I will just cover in all the three poles. So my outline of the talk is mainly why polar regions are important. And secondly, I will talk about what is the present status of sea ice, both in Arctic and Antarctic in both poles, and what are the teleconnections exist. See, whenever we are talking about teleconnections, we always talk about the what is called zonal teleconnections, mainly because of the tropics, ENSO, IOD, Atlantic, NINO, and other things. But nothing major things. Most of the people never talk about the meridional teleconnections, such as mid-latitude and the polar region in terms of tropics and other things. So I thought I will dwell upon this meridional teleconnections, especially both in Arctic and Antarctic, and also Southern Ocean. Finally, I will try to impress on what time scale this Arctic, Antarctic, and Southern Ocean is important for tropics, as well. Mainly, it is pertain to monsoon and cyclone, especially related to extreme weather events. So these are the major things, and take-home messages, that is the main point. So coming back to polar regions, why polar regions are critical? See, as you all know that it is basically it is acting as a cooling chambers, but nowadays this cooling chamber is warming up. So the gradients between the poles and tropics are reducing considerably. There is a small change in this structure. These polar regions have far-reaching consequences, especially large ice sheets, both in Greenland and Antarctica, is depleting. You know that about 75% of the world fresh water is residing at these locations. And if all, of course, if all the fresh water in the polar region, both the Arctic and Antarctic, it's melt. It is roughly about 70 meters in the sea level rise we expect. Of course, it holds about 99% of the ice on the Earth, and world largest carbon sinks. Also, it is in the polar regions, and also occasional surprises and other hazards, especially methane and hydrates related to permafrost. And also the third pole, the largest reserve of fresh water outside the poles, to feed about 1.9 billion people, it is also melting due to the warming effect. And of course, this polar region is an amazing biodiversity and life for adaptations. Understanding how the planet works in the polar component is very important. And because of the changes happening very fast here, the geopolitical and geostrategy pertain to polar regions also picking up very fast. So considering the polar regions, there are three poles. One is Antarctic. It is a land covered by ocean, and Arctic is ocean covered by the land. Of course, Himalaya is the top of the mountain. Of course, it is a land one. So the studying polar regions is very critical, and it is important, not only the present, but also past. And if you know the past history, then better understand the present, then later on we try to predict the future. So the climate is warming up much more quickly at the poles than the elsewhere, and affect the climate of the entire planet. It is almost the polar regions, especially Arctic, it is almost warming up twice than the global mean. So that is where more important we need to worry about it. So what are the evidence are coming in the polar regions? What we observe, what are the evidences? So number one evidence is the increased air temperature, not only at the surface, above the surface in the polar regions are increasing almost double than the global mean. And also the dramatic reduction in summertime sea ice extent and loss of multi-year sea ice. It is also going on very fast, especially in the Arctic, then the Antarctic. The increased upper ocean freshwater content because of the glacier melt, and the freshwater content is going on increasing, so that the stratification is increasing because of that freshwater, and also increasing ocean heat content, and so it's increasing tremendously, and amplified acidification of the ocean, and also the ecosystem is shifting. The tropical ecosystem or fish migrates to mid-latitude, and the mid-latitude ecosystem or fish and other things are migrating to polar regions. So the ecosystem is continues to shifting, and also accelerated Greenland ice sheet melting. It is a Greenland ice sheet alone, if it melts, it is about 7 meters, we expect the sea level rise. And of course, warming permafrost. When you talk about climate change, there are major three drivers, three things. One is surface warming, surface temperature warming, and decreasing sea ice extent and sea level rise. These are the three important components if we look at it. All the three things are happening in the polar regions. Whatever is happening in the polar regions, and later it compounded to entire. So this is just a seasonal changes of sea ice extent, Arctic and Antarctic. The left figure shows the seasonal variation of sea ice extent in the Arctic, whereas the major sea ice less, that means sea ice extent is very less in the month of September, whereas at the same time in Antarctic, the sea ice is maximum at that time. So the variability is higher in the month of September. So of course, the March also, it is the sea ice extent is decreasing. The red dot figure shows the 2012, the record minimum sea ice extent what is been observed. Of course, this 2021 also, it is almost in this, especially in the winter time, sea ice extent is very less is observed in 2021. Of course, Antarctica, unlike Arctic, there is not much variability, but however, the recent few years, the Arctic sea ice also has shown much variability and much decrease in the sea ice extent. When you talk about Antarctic, whatever the changes, between 2002 to 2020, Antarctica set roughly about 150 gigatons of ice per year, causing global sea level rise about 0.4 millimeter per year. It has happened. And especially in the areas of Eastern Antarctica is not much changes, but whereas the Western Antarctica, the changes are very dramatic. So that is a major place where the ice shelves and ice sheets are detaching from the Antarctic ice sheet. However, the gain, whatever the ice gain is more than offset by the Western Antarctic ice sheet as well as the Eastern Antarctic. In totally, if you see that, it is not very minimum change what we can look at it. But when you talk about Greenland ice part changes and the higher elevation of areas near the center of Greenland experience little or no change, whereas in the coastal belt, the changes are very dramatic. And it is roughly about 0.8 8 millimeter per year sea level rise is going on for the last few decades after satellite era. And also it is projected that in the various sea level projections by roughly about 2050, the Arctic summer sea ice will not have any sea ice in the summer, especially in the 2050. Of course, 2040 to 50, there is a major change both in Arctic as well as in Antarctic. One is summer sea ice will not be there in the Arctic, and whereas in the Antarctic, there is a geopolitical change will happen in 2047 because of the Antarctic Treaty level. So, and the other third pole is the Himalayan Cryosphere, Himalayan glaciers also slowly depleting. If we talk about 1975 to 2000, as well as 2000 to 2016, the second period is showing more what is called water equivalent per year glaciers are depleting when compared to the earlier decades. Of course, this is a very important things because the water bodies available here, it is dependent on more than 2 billion, roughly about 2 billion people. So we need to safeguard and we need to understand the process, what is happening in the Himalaya. So coming back to pole to tropics teleconnections, of course, the first one is understanding the dynamic link between tropics and polar regions through atmosphere as well as the ocean. Both the teleconnections exist, but it was not very well noticed earlier because it is the influence of these polar regions is not that much when compared to tropical energetic tropics. So that's why people are not much worried about. But now the thermal gradient between the low and high latitude altered and the gradients become less and less. And because of the gradients are less and the changes are also happening very dramatically. So the interaction among the climate parameters, especially atmosphere, ocean, sea ice, and its feedback, this is those are increasingly getting complex under the rapidly changing polar climate. So the atmospheric teleconnections, which are occurring very faster time scale, about few days to what is called intraseasonal time scale, whereas the ocean teleconnections, it goes for months to years or decade level. So it is important we need to understand this whole tropics teleconnection for better Earth system studies. So I will just quickly summarize a few linkage. What are the specific linkage with the Arctic? Few, and certain specific linkage with the Antarctic and Southern Ocean. I will just point out for the influences. So one is the Indian Ocean driving the Arctic sea ice pattern. Whenever there is a rainfall, Indian summer monsoon rainfall, it is extremes are happening. Whenever extremes are happening, the Indian monsoon excites eastward propagating Rossby waves all around the globe. And when it reaches to the Atlantic, it's split into two portions. That is a heat energy transport, one to the Arctic and one to the mid latitude. Whatever is transported to the Arctic, it is having a melting effect. So essentially, what is that want to convey here is the remote icy and monsoon variations induce dominant dipole sea ice melt pattern. It is like if you see that heavy precipitation event as well as the low precipitation event, if you make it do two different monsoon years, if you put it, you can have a dipole structure of sea ice pattern in both the in the polar regions. So the monsoon-related sea ice variations are complementary and comparable in magnitude to locally forced Arctic oscillation variability. That means whenever there is a monsoon, this monsoon transports good amount of heat to the poles and create sea ice melting, and that again compounded the more and more ice. And this is almost equivalent to other remote forcing. And also in the recent years, the increased rainfall over Northwest India and Pakistan contributed to more intense local anticyclonic outflows from this region. So whenever there is a heavy rainfall event in the Northwest India and in maybe in Northern India, the heat transported all the way to the Arctic. And because of that, there is a melting in the sea ice. So, and you know that from last few decades, the North Pakistan or Northwest India, the heavy rainfall events going on increasing. So that heavy rainfall event, whatever increasing, creates more and more energy transport to the Arctic, and then the ice melt is happening. It roughly take about 6 to 8 days. And the second and third one is MJO. It is a equatorial intraseasonal variability. So it is a convection, equatorial convections. So this Arctic amplification, that means wherever the heating effect is happening in the Arctic, and if you split the majority of the roughly about 10 to 20% of the heat in the Arctic is mainly due to the MJO variability in the tropical belt. That means convection. Essentially, the convection in the tropical Indian Ocean create cooling effect in the Arctic, whereas in the Pacific is happening in the Arctic. The Pacific warming is happening in the, that means warming effect is happening in the Arctic. Essentially, if you know that there are about 8 modes of MJO in the Indian Ocean, the most of the frequency of this MJO event is reducing in the recent years, whereas it is increasing in the Pacific. So this increasing in Pacific MJO frequency in this particular phase is contributing significant amount of heat to the Arctic. So in the short term, the Indian extreme rainfall event also contributing to sea ice reduction in the Arctic, and also the convection pattern in the equatorial Indian Ocean also contribute to the Arctic warming. And also now this is basically the tropics to poles we have seen. Also the poles to tropics also there is a connection. So it is basically in the Greenland Sea and Indian monsoon, it is highly negatively correlated. So through Pacific, actually when the autumn sea ice area in the Greenland Sea negatively correlated with the Central Pacific in June, July, August, and later on this Central Pacific warming in turn causes reduced rainfall during this summer monsoon. It is also demonstrated. It is in interannual time scale. And recently also it has been documented that in the whenever there is a why this extreme rainfall, whatever is happening in Indian monsoon, it is also due to the Arctic sea ice reductions. So the left side figure shows the sea ice extent as well as the frequency of extreme rainfall and total rainfall. So the sea ice extent and the extreme rainfall event in the recent decades are going 1-to-1, especially during the AMO event. This is mainly because of the the episodes of such rapid Arctic sea ice decline shows more consistent relation with the frequency of extreme summer events. So what is the mechanism basically why this Arctic sea ice melt and extreme rainfall? What is the mechanism? So basically we want to say that the sea ice reduction in the Kara Sea, especially in the Kara Sea, it changes the jet stream pattern in the Arctic area, and it is caused anomalous meridional circulations. So that enhance, there is a blocking of the Rossby waves in the mid latitude, and that Rossby wave activity flux towards subtropical Asia it is propagating, and it because of that stronger subtropical high and upper level divergence is happening. At the same time, we have a positive SST anomaly in the Arabian Sea together, so that moisture convection will be more, and because of that surface cyclonic circulation with having enhanced moisture convergence, and because of that extreme rainfall is happening. So essentially what I want to convey is the sea ice decline in Kara Sea is also contributing to the extreme rainfall in India. So although these teleconnections are through atmosphere and thus propagate fast, oceans too play an important role in shaping the tropical climate response to polar sea ice changes. So Arctic sea ice projection, if you see that, as I mentioned earlier, most of the simulations almost predicting that in the year 2010, 50 or so, there will be no more summer sea ice. So if there is no summer sea ice, then accordingly there is a ramification in the extreme rainfall events in India. So just I want to convey that the teleconnection between tropics and poles, especially in the Arctic, on the intra-seasonal time scales, MJO and extreme rainfall causes Arctic ice melt, and Arctic ice melts causes extreme rainfall in India. It is a feedback loop, especially in the later half of the monsoon period. That means August and September. On the interannual too, there is a link between Arctic and the Indian monsoon. Of course, the ocean atmosphere coupling is the key to predict extreme in the tropics associated with the polar regions, especially in the Arctic. I will just to give some two more glimpses about the Antarctic. When you talk about the Antarctic, the sea ice extend in the area of Bass region, that is the Bellingshausen Sea. Whenever the sea ice extend, this reduction is happening. The SST is increasing in the Pacific in this area. Because of that, there is a cyclonic circulations will be noticed here in the Pacific. And because of that particular things, you will have an excess rainfall. Basically, the excess rainfall years showed anomalous cyclonic wind patterns, and that lead to the anomalous positive air temperature, and that facilitates sea ice condition in the especially in the Bass region. So there is a link between the Bass region sea ice condition and excess rainfall in India, and also the Antarctic circumpolar wave, and also in Indian summer monsoon also, it's anti-correlated between these two region, Bass sea ice extent and Indian summer monsoon rainfall in the interannual time scales. And similar to Arctic, this MJO, that is a convection pattern, it is also contributing, it is exciting the tropical convection. It is also amplified, or all the way the heat are transported to the Ross Sea area, and it will have a sea ice reduction because of more convective activity, and sea ice reduction will happening in the Antarctic region, especially in the Ross Sea region. So there is a strong teleconnection in intra-seasonal time scale as well as to Antarctica. And also in the interannual time scale, the Indian Ocean dipole mode also contribute to the reduction of whenever there is a positive IOD years, you will have Antarctic sea ice reductions, and whenever there is a IOD even in the opposite, that means negative IOD, you will have a sea ice positive. It is a vice versa. And also whenever this IOD along with the ENSO, it is coexist, then that year we will get wave tide is much more than stronger, especially in the in the Ross Sea and the Indian sector of the Indian Ocean, Southern Ocean. Also, we can see that the increased influence of ENSO and Antarctic temperature. From the ice core records, we are able to see that there are many variability exists in ENSO time scale as well as PDO, but the variance of the Eastern Antarctica temperature record shows significant increasing trend at ENSO band and decreasing trend at PDO band since the industrial era. So we are able to see these features from the ice core records. So there is an increased influence in the of ENSO and Antarctic temperature as well in the after the industrial era. So coming back to Southern Ocean link, just a few examples I will mention about Southern Ocean. As you all know that the Indian monsoon is strongly influenced by the gradient between the air pressure. So you have a low pressure in the northern hemisphere and the high pressure in the southern hemisphere. So because of that, there is a strong equatorial, that means cross equatorial flow. Because of that, we have a very good monsoon years. But recently, what is happening is in the Southern Ocean, there is a warming is happening. There is a significant warming in the Southern Ocean. Because of the Southern Ocean warming, then we have the pressure gradient between the north and south. It is reducing. Because of this reduction in the pressure gradient between north and south, you have a less cross-equatorial flow. So because of the less cross-equatorial flow, there is a reduction in the monsoon winds or monsoon strength is happening. And we can see this, why this warming is happening in the Southern Ocean. There are two things. One is due to the westerly winds in the Southern Ocean that contribute to the warming in the Mascaran High region. Also through Indonesian through flow, this warming is happening in the Mascaran High region. Because of the warming in the Mascaran High region, there is a low in the Mascaran High intensity. Because of that, we will have a cross equatorial flow is going to be reduced in the coming in the recent decades. So this is what, whenever there is a westerly winds are very strong in the Southern Ocean, we will have a excited Rossby waves propagating towards Indian Ocean. So because of that, not only Mascaran High region, entire Indian Ocean also is warming forced by the Southern Ocean westerlies. And also the recent decade, the cyclone intensity and the durations are much stronger in the Southern Ocean, whereas the number is though the number is reducing the cyclone numbers, but however, the cyclone intensity and durations are significantly increasing in the recent decades, especially in the Southern Ocean. Also, there is an event called Kallakadal. It is basically the swell from the Southern Ocean. Since the westerly winds are strong in Southern Ocean, there are a lot of swells produced in the Southern Ocean. It comes all the way to the Indian coast. It is like a swell hitting suddenly. So you will have a surge in the southern, especially the southern peninsular India. You will have a significant impact in the Kallakadal. So we need to have overall our understanding. We need to have that means we need to understand the various processes in the polar regions. So we need to have more and more observation in the polar region to underpin the direct relation between atmosphere, ocean, ice sheet, and solitude, and also to demonstrate in the model for the better predictability. So what I want to summarize is the Rossby wave trains emanating from tropics, especially the convection or heavy rainfall event, are still main mechanism to explain the tropical and polar teleconnection from various actually interseasonal to multi-decadal timescales. And the teleconnections is happening in both ways, tropics to pole as well as pole to tropics. Furthermore, influences of polar climate can be significantly observed in the interaction between tropical climate modes. Of course, Southern Ocean warming is contributing to monsoon modulation. Also, the cyclone intensity and duration is increasing in the Southern Ocean. In the rapidly changing polar climate scenario, proper representation of the polar climate components and its feedback in the climate model is a key to understand the interconnected global system and its response to the changing climate. One inevitable way to improve the polar climate representation in the climate model is long-term and continuous observation in the polar regions. Though the atmospheric transfer of energy from the tropics to poles are accumulated in the poles, and it transfers this energy from poles to lower latitudes needs much more attention and investigation. It is for ocean tunnel in the long term, maybe the decadal or other time scales. So these are the things which I want to convey. So importance of the meridional circulation and meridional influence in the tropics, apart from the tropical teleconnections. Thank you very much.
Thank you, sir, for such an informative, excellent, and interesting presentation. You have very well highlighted the importance of polar regions, and we are really grateful to you for the time and effort you took to share your thoughts with us. So now, moving ahead, now I would like to request Professor Devesh Walia, Convener, Local Organizing Committee 58 Annual Convention of Indian Geophysical Union, and Head, Department of Geology, Northeastern Hill University, Shillong, to propose vote of thanks for the inaugural session. Sir has a rich experience of more than 30 years in the field of geological sciences and working especially in structure and tectonics of Northeast India region. He has published his research findings in various peer-reviewed journals. So I would like to request Professor Devesh Walia to offer vote of thanks. Over to you, sir.
Yeah, thank you. Everything has come to an end, so our inaugural program too. On behalf of Indian Geophysical Union and Northeastern University, would like to propose vote of thanks to all the dignitaries and the EC members, along with the participants present in for the program. This 58th annual convention is basically with special focus on recent advances in earth sciences, with special focus on Northeast natural hazards, because we know that Northeastern region is especially of importance because of various hazards and all, and we need to carry it forward. As I already told you that we were supposed to hold it in a offline mode, but somehow we have to hold it under this pandemic condition in the virtual mode. But still, hopefully, it will be a good interactive session. Firstly, I would like to thank our chief guest, Dr. Ravi Chandran ji, to have taken out time from his extremely busy schedule and to be there with us and enlighten us with his various thoughts. Especially, he said that in the inaugural session that there is no way to avoid the natural disasters, but definitely we can provide the solutions, and it should be studied, and we should be able to take up the whole cause for the benefit of people and society. Secondly, we would like to thank Professor Prabhashankar Shukla ji, the Vice Chancellor of Northeastern University, although because of his extremely busy schedule, he could join, but finally he couldn't give his message. But when we met, he said that anytime on a physical mode also, they would like to have Indian Geophysical Union in our campus, and will be grateful to have him later. I would also like to thank our honorable president of Indian Geophysical Union to have given us chance to this program. Although, sir, we couldn't do it physically, but definitely we'll be able to provide all support in the times to come, so that the more interaction, more networking among the various scientists, it can move forward, or we can take up the cause. As while during your inaugural address, as you said that natural hazards amalgamating or interacting with the climate change is a challenge, and definitely under Indian Geophysical Union and your presidentship probably will be able to do something good, so that we are able to resolve these problems. So I would like to thank Professor Shailesh Nayak for giving us this opportunity to host this program. I would like to thank all the awardees, to those who have contributed in their life, by way of various research and publications. And I would like to convey our heartfelt thanks to all the awardees, that you have done a great job, and probably with such smaller awards or smaller recognitions, probably you'll do good, and you'll do something for the country, for the nation. And we owe this gratitude to you, to have worked so nicely and to have taken out time to be present for this program. There has been the Professor Jagdev Singh and S. Balakrishnan Memorial Grant, and which is given to many people, as we can see that. So we are very much thankful, and we want that with such a grant, they'll be able to take forward again the cause. Further, the most important part of this program was the Professor K.R. Ramanathan Memorial Lecture. And I'm very much thankful to the EC members and to all the members that you have given us chance to hear the various thoughts and ideas, especially on the topic teleconnection between the poles and the tropics, and it is of great relevance, especially in the changing time and with the growth of the studies related to atmospheric science and all. It is of great importance. So I would like to thank Dr. M. Rami Chandranji to have taken out time especially for giving us this lecture. I must thank the various sponsors. Definitely Ministry of Earth Science, they are one of the major sponsors, and National Geophysical Research Institute, which is represented by Dr. V.M. Tiwari ji, that to have taken out time to be there with us, and especially by sponsoring the program also. NIO Goa is of importance, is always there with us, INCOIS and other organizations, other sponsors, those who have given us this time, this sponsorship to have organized this program. I would like to tell all the participants that during this program, we received more than 125 abstracts, and we have tried our best to accommodate all of them, either as by way of oral presentation or by way of poster presentation. And without the involvement of the participants, we would not been able to conduct this program. So I would like to thank you all for contributing, and hopefully in the times to come, either in a physical way or whatever way, IGU, whenever it organizes the program, you will be definitely provide more good publications or good abstract material or good material of research, so that it comes to the forefront and we are able to take up at the right spirit, and we are able to also understand to build it better. So with these few words, I would like to thank one and all. I would like to thank various chairmen of the session. We know that we have divided all the sessions into 10 various sessions. First session is the inaugural session, and next 9 sessions, they are the various technical sessions. As we are organizing in a virtual mode, so we are definitely time bound. So at times, the presenters may face that they have to speak a lot and they are not able to do so. So please excuse us for this, because time is very, very important, and time management is extremely important, more so. So with this, I would like to thank all the chairpersons of the program, of the various technical sessions, co-chairpersons, and the rapporteurs. Your role is very, very important, because end of the day, the recommendations and the way forward is of great importance. So please be there and please give us proper feedback. You can see that this program is live on YouTube, and many people, they have already seen it YouTube. We were not knowing, but they are asking some of the queries, which we may have to resolve them after the program is over. At the same time, there is a feedback form. So I would like to request all of you, because always there is a scope of improvement. So please fill in that feedback form, because whatever information you are giving in the feedback form, that will help us in giving you good certificate also. So with these few words, I would like to welcome you to this 3 days annual convention. Hopefully, all of you will gain and have good time in the next for next 3 days or 3 days up to 4th. Thank you very much. Thank you, sir. So with this, we have come to an end of our inaugural session, and we will start technical session, which is considered as technical session 2. And in the technical session, we have various chairpersons. So I'll request the organizing committee to further take up the and give the responsibility to the chairpersons. Dr. Shri Nagesh ji, I can see he's there online. Spotlight him. And co-chair Babita Sharma madam, and rapporteur Dr. Sandeep. So they can be there. And Dr. Bansal ji, please guide, so that let us start the program.
Yes, sir, please, we can start. Sri Nagesh is there.
Yeah, so let us start the program, and just to inform, just sorry to interrupt for a minute, for a fraction of seconds, that all the presentations are there with us, and they will be played one after the other. Whenever our chairperson, Dr. Shri Nagesh ji, will say, that time it will start. So everything, maintenance of time is in your hand now on, sir. Thank you.
So we'll stick to time, no issue. So shall we start the first session?
Yes, please.
Yes. It's a pleasure. Good morning to one and all, and it's a pleasure to be a chair of the one of the sessions, the second session in the IGU, and I request Dr. Rajendra Kumar Chedda, who is the Rajaramana Fellow and presently at CSR NGRI, former chief scientist, retired, and also he was an emeritus scientist of CSR. I request him to deliver his talk. And sir, you have exactly 15 minutes. The floor is yours, and please go ahead.
Okay. Do I have to share screen or it will be loaded?
It is loaded.
Okay. A very good morning to you all. Just before starting my talk, I just want to say how much I miss being in Shillong. So Devesh, it was an opportunity to see you, but somehow missed. Maybe next time. My topic of talk today is basically on understanding the strong ground motions in the Indo-Gangetic plains. So when we say ground motions, you have earthquake, you have all kinds of ground motions. And here we are dealing with strong ground motions. You have weak motions, you have all kinds of these, because these are the motions which will create a lot of damage in an area. So that is a thing of botheration to us. So that's the reason strong motions are very, very important if we have to reduce the damage. Next, please. Okay. Now, when we say ground motions, anywhere when we are trying to see, especially in terms of Indo-Gangetic plain, I have focused my talk. The reason being simple, that it is absolutely close. It is just abutting the seismically active region of the Himalaya. And it is filled with a lot of sediments, and the Himalayan region is notorious for having earthquakes, which go more than 8 magnitude. And in the last 100 years or a century, we have seen 4 major such earthquakes, ranging from the Himachal in 1905, then 1934, Bihar, Nepal, you have Shillong, then you have the Assam earthquake. So this region becomes very, very important when we talk of strong motion studies. And strong motion, when we say, we are essentially trying to quantify these motions which we observe during earthquakes. So when you quantify, the quantification, we see most time these 3 parameters are very, very important. That is the velocity of the seismic waves, then you have the acceleration, and you have the displacement. So if we have to quantify this ground motion, these parameters are very, very important. So I'll be mostly addressing these 3 parameters. And as I said, this Indo-Gangetic plain is not only important from the point of view of being very close to the Himalayan belt, because you have the critical structures which are coming up, like the recent one you have in the Gorakhpur, the NPCIL project we have finished at NGRI. And still this project is coming up, this is a nuclear power plant. And also you have mega cities where the density population is very high. So the risk is very high when we are talking of Indo-Gangetic plains. Next. We all know that when you have a layer of sediment, it amplifies the seismic waves. If you put 2 seismometers, you observe that the seismometer which is placed on the rock will have a waveform which looks something like this, and when it is on the surface, when you record, it looks something like this. That means the sediments have the capacity to amplify these ground motions, which becomes very, very dangerous. But the question is how to take out the effect of these sediments from the amplification. So I'll be talking mostly on that. Next slide, please. Next slide. Okay, we have examples where we have observed this phenomena right from 1897 Shillong earthquake, Kangra, Bihar, Nepal, then the Mexico, then you have the North Ridge, coming to recent examples in Bhuj and Nepal, where you see damage which is occurring in the far field, even 400 kilometers away from the epicentral region. You find that a lot of damage has been done, a lot of buildings have collapsed. So the idea is to see these ground motions and quantify them and try to see that if there is a region, how much of amplification and how much of this far field effect is causing this damage. Next slide. Yeah. So in the Indo-Gangetic plains, we had an array in the last 10 years. We started with the studies because knowing the importance of IGP. So we had a profile going across the Indo-Gangetic plains. The idea was to find out the sediment thickness. Although from the literature, we know that in this region, the sediment thickness varies between 500 meters and it goes up to 6 kilometers. So we also did the studies using this array, and we came out with sediment thickness ranging from 1,000 kilometers going up to 6,000 meters. 1 kilometer to 6,000 meters, that's 6 kilometers. And also when we go from the shield region towards the Himalaya, we find that the depth of sediments or the thickness of the sediments increases. Next slide. Later in 2012, we had a network of strong motion velocity meters in the Indo-Gangetic plain. The idea was to record some of the earthquakes and then play with the realistic data rather than going into a lot of assumption and taking some theoretical values. This network, you will find that there are some stations which are on the edge of this Indian Shield, and basically they are located on the hard rock terrain. And IGP being a sediment filled valley, you have lots of seismic stations. We are sitting on very high thickness of sediments. Similarly, in the northern, you have the Almora, you have TKT, and some of the stations which are on the hard rock and which are also very close to some of this region, the stations in the soft rock area. Like you have this Allahabad, which is on a hard rock. You have the Varanasi, which is sitting on very high sediment thickness. Next slide, please. So during this time, when we had this network, after that, we had two earthquakes which are of major significance. One occurred in the Bay of Bengal and the other in the Himalayan region in Nepal. So we recorded both the stations and they provided very, very useful data in terms of studying these strong ground motions and quantifying them. As you see, this is a plot which shows the seismograms recorded with reference to the distance from the epicentral region. Also in the IGP in the Indo-Gangetic plain and also at some other sites. So you see, this is the Varanasi stations, which is about approximately about 950 kilometers from the Bay of Bengal earthquake. And immediately just at Allahabad, which is about less than 100 kilometers, the crow flight distance, you can see the kind of amplification you find at the Varanasi, but you don't see at Allahabad. It is also true in case of two of these stations at TKT, Tarikhet and Almora in the Himalaya. And you have another stations where you find amplification happening with reference to two adjacent hard rock sites. So even this is a plot which shows that constantly you will find that the the soft sites sitting on sediments are constantly show higher amplifications, which is very, very in terms of the velocity and in terms of the accelerations. Next slide. This is just one example I am showing of the Bay of Bengal earthquake at Varanasi. This is the velocity, this is the acceleration, and you can see the kind of waveform you see, and you have this Allahabad, as I told you, because it is sitting on the hard rock. You can see the difference between these two waveforms where the amplifications, how they are subdued. So when you take the Fourier spectra of these signals, you will see that they are very nicely separated from the noise, and this is a plot of the Fourier transform for taken for the earthquake, which is in Bay of Bengal, for north-south and east-west component, and they are very nicely separated. Next slide. So what we did was we have to separate out the effect of sediments with reference to the basement. Most of the time what we see at the amplification, we have to separate out and see how much is the effect of the sediments to this amplification phenomena. So we used different techniques. This is one of the techniques we called standard spectral ratios, because it provides you the spectral amplifications for all the frequencies. So basically, when you take the Fourier spectrum, here it is shown, this is a repetition of my earlier slide. So you have the Fourier spectrum of a Varanasi, that is soft side, versus the hard side at Allahabad. Next slide. So when we take a ratio of these two Fourier spectra, what we call this technique as standard spectral ratio. So we noticed that the spectral amplifications for these earthquakes we found in terms of velocity as well as in acceleration were of the order of 3 to 4 times the amplification which takes place when you are comparing a hard side with a soft side. So it's of the order of 3 to 4 times of amplification. We also noticed for the Gorkha earthquake in Nepal, the same phenomena we noticed even for the earthquake which occurred in the Himalaya. Next slide. So after seeing that, we realized that this was very useful when you have a station which is sitting close by on a hard side and a soft side, like in case of Varanasi, as I told you, which is on the edge of the this Allahabad, which is sitting on the edge of the Indian Shield and very close Varanasi. But what happens is when you have seismic stations which are sitting right in the Indo-Gangetic plain where you don't see the basement goes after 5 kilometers. So in those situations, we tried an alternative approach and tried to see what happens. So for that, we used a method which we named as the Rss method, that is the ratio of the source spectrum of the target side versus the soft side. So earlier what we have seen, we have taken the Fourier spectra and try to see the ratio. Here what we do, we calculate the source spectrum using the Bruns model for an earthquake. This we have seen for these 3 aftershocks of Nepal earthquake, and try to see how it looks. So we take the source ratio of the source spectrum at the hard side and the soft side, and we see what results we see. And we realize, next slide, please. And we see that this is a source from the hard side. This is a Varanasi for aftershock of 7.2 magnitude. And this we did for all the 3 aftershocks of the Bihar Nepal earthquake. And we find that in case of Allahabad and in case of the Varanasi, it looks almost similar, except that here the amplitudes looks to be very, very subdued. So it also clearly indicates that the Allahabad side, because of its being present on a hard side, it happens because of that. And soft side, the amplifications will be much, much higher. So next slide. This is my final slide mentioning the few takeaways of that. So when we are trying to filter out the effect of soft sediments when for amplification and take out from the, so the best method is see at a hard side, see at a soft side, separate out this thing, and then you see what happens. So we have seen that it 3 to 4 times of amplification is happening in the Indo-Gangetic plain in the presence of a thickness of say about 4 to 5 kilometers of the sediment thickness. And the standard spectral ratio techniques are very good when we are comparing the nearby sites on a hard and on a soft, like the Allahabad, Varanasi, or the Almora and Tarikhet with the TDR. But when you have your seismic station, which are located inside the IGP where the sediment is too thick and you don't find a hard side, so when you take the far away stations of say about 1,000 kilometers, what we have seen, So we find that the results are very good when you take within 1,000 kilometers. Also, we see that some of the work was done using the teleseismic earthquakes more than 1,000 kilometers. There we find that this technique, SSR techniques, is very good when we are talking of lower frequencies, say 0.5 hertz. So for the soft sediment inside the IGP, I think the RSS method looks to be very promising. And SSR method is very good when you have the stations which are very close by on a hard side. And these are a few of the takeaways which I have just jotted down about our results. Thank you. Next slide. Thank you.
Thank you, Dr. Chedda. You just on time. Actually, after your talks, there is a half an hour time put for discussion. We'll take the questions that are asked. We'll go for the next. We'll go for the next talk. It is by Kapil, re-estimates of source location of the 1803 Garhwal earthquake and its tectonic implications. Kapil, please go ahead.
Good morning, sir. Am I audible?
Yes, you are audible.
Thank you, sir. Sir, presentation. Thank you, sir. Thanks to chairman, co-chairman for giving the chance for presentation. We actually into 2020 in August.
Kapil, you have just 5 minutes. You know that.
Yes, sir.
Right?
Yeah, exactly, sir. Yeah, thank you very much. There was an earthquake in Delhi, and we started thinking about near field and far field sources. And at the time, the far field sources, when we were thinking, then on review, we found that 1803 is an important earthquake. But at the same time, while doing this, we were trying to simulate certain things, but finally we concluded certain parts of this particular earthquake. I'm just putting certain things on in this paper. Yes, next slide, please. Yeah, this is important because this particular earthquake was felt from plains from Punjab to Kolkata. Then two different epicentral areas, underlying areas, Garhwal and Mathura, were initially proposed. Later on, total of 8 different epicenters, 7 magnitude, as well as different rupture propagations were proposed in the past for 1803 earthquake. Magnitude range was 7.3 to 8.1. The most important thing is this Qutub Minar was also damaged. Top cupola of this particular minar was damaged because of 1803 earthquake. Claims rupture reached up to HFT or not reached up to HFT. This is also a point. And the last part is this. This is important as far as the central seismic gap is concerned. Next slide, please. Recently, Bilham 2020 has written about 4.5 meters slip potential of this particular zone, and he suggested that 1991 and 1999 was not sufficient to release all the slip accommodated there, but he suggested that 7.3 and 7 magnitude in this particular region. So next next slide, please. Yeah, here we can see for the most important part, when the past researchers has presented the location of this particular earthquake, they have presented it from higher Himalaya till up to HFT. So Abrams and Jackson presented has suggested in lower Himalaya, the number 1. Then Ambrose and Douglas in 2004 has suggested, based on the intensity data, they have suggested in higher Himalaya. Then Bilham and Ambrose, they also suggested the same particular suggestion, that it is in higher Himalayas. Epicenter was in higher Himalaya. In 2005, Rajendran suggested the area in near Srinagar site. Based on their intensity investigation, they also proposed the isoseismal map for this particular reason. Then Martin and Zeliga and
you have only 2 minutes.
Sir, yeah, definitely.
2 minutes. Please.
Yeah, there's no issue on that. Yeah, exactly, sir. So finally, the point came out when Malik has done paleo investigations, and he has suggested that this is at HFT. So keeping all these things in mind while simulating this particular earthquake, we have next slide, please. We have used all the epicenters and the rupture processes, and we have generated the ground accelerations from all these epicenter. Next slide, please. Yeah, these are the two isoseismal map, Abramson and Douglas, Rajendran and Rajendran. Both have suggested intensity 8, 9 in the mesoseismal zone. Next, please. Here, in this particular part, 1803, from this particular, when simulating this particular earthquake, we found that at different location, when we have studied MST while simulating this, we have found that MST was also proposed in the higher Himalaya for with a dip of 4 to 7 degree, in lesser Himalaya 16 to 25 degree, and then the depth is also 10 to 15 degree, 10 to 15 kilometer, and 20 to 25 kilometer in lesser and higher Himalaya. So in our input parameters, this is the parameters. These are important. Next slide, please. So we have considered, then recently NCS also done a study for estimation of kappa, as well as attenuation quality factor. So we have considered those particular input parameter presented at this particular slide with the length and rupture. Next slide, please, sir. Next slide, sir. We have considered the stochastic finite file. Sir, 5 minutes are not over, sir. 1 or 2 minutes are left, sir. So, please. So stochastic finite fault modeling technique was used. Sir, I'm just briefing my results. Next slide, please. These are Rajendran and Rajendran's. When we consider, we have prepared the peak ground acceleration distribution map based on rupture presented over there, and the rupture direction here suggested. Next, please. In 2013 and 18, they have given a subsurface model. On the basis of that also, we have prepared the peak ground acceleration distribution map that is on the screen. Third one, please, sir. Then Malik, after this particular part, he has suggested a magnitude 7.5 to 8, and the area is HFT. Then he suggested that rupture reached up to that. That particular simulation we have also done, and we have developed the peak ground acceleration distribution map. Next, please. On the basis of this, Bilham also proposed a rupture area. We have also simulated that particular rupture area for a magnitude 8.1. Next, please. Finally, we have estimated the intensity suggested intensity in the past literature suggested by various researchers, and intensity generated through these ground acceleration on these locations, and then generated a correlation coefficient. We found that Rajendran et al. Is the correlation of coefficient is very close to 0.7, but it is not 0.9. That is point. But this particular thing suggests a location which is, I think, we believe in inner lesser Himalaya with a magnitude 7.7. Thank you, sir, for giving 1 or 2 minute text.
Okay, we'll take the questions in the discussion time.
Thank you, sir. Thank you, sir.
Now I invite Swati to make her presentation on source characteristics of small to moderate earthquakes for the Delhi region of India.
Sir, am I audible to you?
Yes, madam, please go ahead.
Good afternoon to all the respected members present virtually. Myself, Swati, and I'm working as a project fellow in the Seismo-Electromagnetic and Space Research Laboratory, Department of Physics, Raja Balwant Singh Engineering Technical Campus, Bijpuri, Agra. I'm going to present a case study entitled Investigation of Precursors of Rudraprayag Earthquake Magnitude 5.1 occurred on 6 December 2017 by using the GPS TEC and ULF data observed at Agra station. Magnitude of earthquake was 5.1. Sir, can you please next slide? Yeah, so in this slide, I am showing you the details of the earthquake. And for this study, we have considered the ULF data recorded at the Agra station and TEC data that is recorded at Agra station as well as the IGS station Lucknow. Sir, next. Now for this, in this slide, I have basically shown my ULF results. We have expanded all the bursts in time and looked for any electromagnetic content in them. We found the varying between 10 to 25 seconds electromagnetic pulses of period, and in frequency was in the range of 0.06 to 0.1 hertz in many of them, which are selected and encircled, considering them associated with the earthquake. This matches very well with the ULF frequency range. Now, I have shown the example of the LEMI 30 file for X component along with the encircled burst and the burst in cycle generated on the expansion of for December 5. So next slide. Now, these are the TEC results related to the measurements. We have considered the TEC data from 21st November 2017 to 6 December 2017. Results have been plotted for our observing station Agra and Lucknow. We have found the enhancement and depletion in our study, which proves that this variation is only and only due to the earthquake. In order to support our study, I have also shown the plot for variation in the geomagnetic activity. This proves the point that there is no fluctuation in the data at the time of earthquake. Now, before this event, we have many precursors both in the ULF and TEC data. Hence, this validates our point. In TEC also, we have shown various enhancements and depletions which resembles the same. Now, the effect of geomagnetic activity arises at high altitude, and it takes time to reach to the low altitude, and so at low latitude, effect of magnetic storms cannot be seen immediately. They take time, as this is mentioned in the literature already, and it has been confirmed by the research groups that has been working at Agra station earlier. Now, next slide. Now, in this slide, to support my findings, I have shown a plot of some meteorological parameters such as land surface temperature, soil moisture, soil temperature for a period of 15 November to 15 December 2017. The variation in the data, that is the depletion and enhancement at the time of earthquake, proves that this is only due to earthquake and not due to any other interferences. And now, so next slide. And now I would like to conclude my presentations with the following points. And I have shown in the figures and in the tables that we have got precursors in the TEC as well as in the ULF, in TEC and ULF data. And to support my findings, I have also shown the graphs which proves that there was no effect of geomagnetic activity in the period under consideration, and enhancement and depletions were found. And significant changes in the meteorological parameters have also been found prior to the earthquake, and hence it is ascertained that significant variations which are found are only due to earthquake. So the last slide. I would like to acknowledge and there we are thankful to Ministry of Earth Science, Government of India, New Delhi, for extending us financial support. And at last, I am thankful to IGU for providing me this opportunity where I could present, and it was my first experience. Please forgive me if there was any mistake. Thank you.
Thank you very much. Did I miss? There was a presentation just before you, right? There was one by Mr. Abhishek.
Yeah.
Source
Yes.
Yeah. Source characteristics of small to moderate earthquakes for the Delhi region of India, right?
Yes, sir. Yes, sir. Yes, sir.
Yeah.
Mine
Please
was
go
the
ahead.
third one.
Yeah. Please go ahead, Abhishek. I'm sorry, I just missed it. Please go ahead.
Okay, sir. Okay, sir.
I'm sorry.
So slide, please.
Slides, please. We can hear you loud and clear.
Okay, sir. Good afternoon, respected teachers.
Yeah, we can see your slides. Go ahead.
Okay, sir. So I am Abhishek, working as a research scholar in the Department of Geophysics, Kurukshetra University. Today, I am going to present the source characterizations of small to moderate size earthquakes for the Delhi regions of India. Next slide, please. These are the content of my today presentation, that is introduction, seismotectonic of the study area and data set, the method I use for estimating the source parameter for the Delhi NCR region, result and its discussions, conclusions, and the references. Next slide, please. So the source parameter is basically the attribute of a source of an earthquake that characterizing the earthquake source zone. Like what will be the moment magnitude of earthquake, what will be rupture area, what will be the stress drop on earthquakes. So basically, earthquake source parameter are classified in two categories: kinematic parameter, dynamic parameter. Kinematic parameter are the fault length, width, area of fault, direction of faulting, and earthquake volume, whereas the dynamic parameter are the earthquake energy, rupture velocity, stress drop, seismic moment, and the earthquake magnitude. So in the present analysis, I estimate the seismic source parameter for the Delhi region. So let us start with the seismic tectonic of study area and data sets. So figure 1 represents the seismic tectonics, various seismic tectonic feature like the fault, major and minor lineaments that are the present in the my study area. The major one are the Mahendragarh Dehradun fault, Delhi Hardwari Sona fault, Mathura fault, Delhi axis of faulting, and Delhi Sagodhar ridge. Along with this, the figures represent show the triangle, show the different seismic stations which are installed in the study area, and the blue stars represent the past historical earthquake which is occurring in the same regions. Next slide, please. These are the data set which I used for the estimations of source parameter. I used almost 13 events that is occurring from 2010 to 2020 that of magnitude 2.5 to 5.1 at the depth of 5 to 35 kilometers. This the data is taken from the recorded by the National Center of Seismology, IMD, New Delhi. Next slide, please. For estimations of source parameter, I use the Brune 9070 model. According to this model, the earthquake dislocation is a model as a shear stress pulse that is applied immediately to the interior of dislocation surface. So according to Brune 9070, the source model can be predict the following source spectrum that is governed by equation 1. In equation 1, the M node is a seismic moment. FC in denominator is representing corner frequency. Rho is the average crustal density, which is taken to be 2.7, and V is the velocity of the wave which I used in my present analysis. This figure is represent the displacement spectra which will be obtained after the analysis. The conjunction from this figure we can estimate the two parameters. One is a long period spectral level, and another one is a corner frequency. The corner frequency is a conjunction point of the low frequency part and the high frequency part. Next slide, please. As we know, the recorded waveform are the convolution at the seismic station is a convolution.
Kapil, kindly skip all this here. Go to your results, please, because your time is very short. This is all known. Please go ahead.
Okay, sir. Next slide, please. These are the various results which various plots which is show the best fitting Brune spectra with the observed displacement spectra for the Sona station and the Rotor stations. In the present analysis, I estimate the source parameter using grid search approach, in which corner frequency is estimated by the Andrews approach, whereas the another model parameter, that is the long period spectral level, and the Q is estimated using the grid search approach. Next slide, please. These are the various results which I obtained from the P wave analysis. Another one is a result obtained from the S wave analysis. After averaging the two results from the both type of wave, the seismic moment range I found is varying from 4.05 10 to the power 12 to 3.44 into 10 to the power 15. The average stress drop is varying from 1 to 46 bar. Average corner frequency is varying from 2.45 to 11.4 hertz, whereas the average source radius varying from 0.15 to 3.05 kilometer. The average radiated energy, that is ER, is varying from 9.3 to 10 to the power 6 to 2.37 10 to the power 11, and the average seismic moment estimated seismic moment magnitude is varying from 2.4 to 4.2. In the present analysis, one of the remarkable result we found that next slide is this stress drop. We obtained a stress drop is varying with this seismic moment, which suggests the breakdown of the constant stress drop scaling relation for the regions. Next slide. Based upon this, we can say that observed that the very low stress drop obtained for this present analysis, that is varying from 1 to 46 bar. So based upon this, we can say that the rock mass in the upper part of the crust in the study region having a low strength of accumulation of strain energy, and the rock maybe undergoes a brittle fracturing and the adjustment. As we see, the stress slope is varying with this testing moment. So we can say that there is a failure of the self-similarity for the small to moderate size of earthquakes. The output of present analysis can be used as input for the seismic hazard assessment and the simulations of strong ground motions for the Delhi NCR region. Next slide, please. These are the various references which I used for the present analysis. Next slide. Thank you.
Thank you, Abhishek, for sticking to time. We'll
Thank you,
take questions at the end, as I told.
Okay.
In continuation with the Delhi earthquakes, we'll now also hear on Delhi ground motions from Babita Sharma. Babita Sharma, please go ahead and make a presentation.
Hello, sir. I am audible, sir.
You are audible. You are audible.
Okay,
Please
thank
go
you, sir. So the topic of my talk is characteristics of earthquake ground motions governing the damage potential for Delhi and surrounding region of India. We know that the proximity of Delhi and surrounding region to the active faults, along with its geographical settings, is a subject of discussion to comprehend the seismic resilient capital of India. And we know that Delhi and NCR region may be affected by the far field earthquakes from the Himalayas, as well as the near field earthquakes associated with the local seismic activity. Considering this ordinary setting of this region, the present study is an insight to differentiate the damage potential of the ground motion associated with the near and far field conditions, to further see the consequences, to understand the comprehensive seismic hazard of Delhi and surrounding region. Next, please. So here in this figure, I have shown the Delhi region in a regional perspective over here, and also the local perspective. The usual seismic activity in Delhi NCR is apparently because of this region falls in the seismic zone 4 on the seismic zoning map of India, which is prepared on the based on the historical seismicity. The Indian plate is constantly moving, as we see in this picture, in the northeast direction, which causes the strain accumulation at the interface and the detachment zone of the main Himalayan thrust. So there are frequent occasions of seismicity. For this reason, the flexed Indian lithosphere releases stress at many instances. And we see over here many regional features like MCT, MBT, and MFT, which are the cause of the several moderate to major earthquakes which have affected the Delhi NCR region. If we see in a local perspective, broadly the Delhi NCR is sandwiched in between the Mahendragarh-Dehradun fault and Great Boundary Fault, and more specifically a congregation of the other smaller tectonic features crisscrossing in between each other and making this dissected subsurface, making it a preferable location of the strain accumulation. So I have shown here the data which we have used in the present study. 3 earthquakes we have used for the far field, which I have shown in the upper right picture. 3 earthquakes, 2 earthquakes from the Pakistan region, southern Pakistan region, and the 1 earthquake in the Uttarakhand region. So these 2 earthquakes we have taken moderate to major earthquakes, 3 earthquakes, and the local earthquakes which occurred several earthquakes 3.5 to 5.1 magnitude we have taken. And taking all these data, we have estimated the response analysis. Next slide, please. Yeah, so I have shown here just one station result, Jafrabad station response analysis. And by taking up the 5 earthquakes which we have chosen for this study, 5 earthquakes were recorded at this station, and the response analysis at Jafrapur, we have seen the clear distinction of the predominant period. We see here the lower period is estimated at the 3 earthquakes which are taken from the high frequency earthquakes, means the earthquakes in the local region, and the far field earthquakes are showing up the predominant period at the higher side. So this is the clear distinction we are getting at almost all the stations, and this is giving us the idea to get the study of these seismic hazard assessment in these terms of the near field and the far field earthquakes. Next slide, please. Now we have estimated the normalized spectral acceleration by using this near field and the far field data, and we have tried to compare it with the Bureau of Indian Standard Code. We have seen over here in the left picture, which is for the near field data we have taken up. So in this case, the lower period side, the average estimated response is slightly not coming within the limits of the BIS code. But at the same time, we see the long period estimation of the spectral acceleration by using these earthquakes. It is coming within the limits, but slightly amplitude is increased. So with this data, we can emphasize on the structural design code may be improved, or they should be strictly implied into the region to get the more resilient society in the Delhi NCR. Next, please. So this is the impact of the ground motions I am showing over here. So this is showing that the earthquakes which are coming from the far field, showing the long period waves, and they are more affecting the multi-story buildings. On the same time, the earthquakes from the near field region, they are the high frequency earthquakes, and they are dangerous for the low-rise buildings. Next. So these are my conclusions, that the response analysis of recorded ground motions of the long period and the short period waveforms exhibited clear distinct behavior. So accordingly, near field and far field, both most vulnerable areas, and we are finding the most vulnerable areas in Delhi NCR are the northeastern region of the Indian Delhi NCR, and they are lying in the floodplains of the Yamuna River, alluvial deposits of the younger origins of the foreland basin. So, however, the earthquakes ground motions, both low and high frequency, may also have the characteristics of enforcing the liquefaction and resonance influences in the foreland basin. Thank you so much.
Thank you, Babita ji. Thank you for your presentation and sticking to time. Now we will move on to the...
Sir, with your permission, I'd like to announce one thing. I would request the presenters to switch on their video while they're presenting. It will be good for them if their face is also visible on the video.
I agree with that. I thought they should be doing it because it's not appropriate. Please kindly,
the presenters are requested to switch on their video.
Yeah. So let's move on to Himalayas now from Delhi, and Dr. Yadav would be making the presentation on probabilistic seismic hazard analysis. After this talk, Babita ji, you are the co-chair, right? I request you to take over. I just waited because your presentation is there.
Okay, sir. Thank you, sir. Thank you.
In all fairness, after this talk, please conduct the proceedings. Thank you. Go ahead, Yadav ji. Thank you very much.
Thank you, sir. Good afternoon to everybody. Just today I will deliver a lecture on the topic and updated probabilistic seismic hazard maps for the Himalayan seismic region. So a number of seismic hazard maps has been prepared by several researchers, starting from the Professor Khatri, and then the GSEP program was launched, and then the NDMA has developed a kind of probabilistic seismic hazard for the whole the India region. And there are a several number of researchers are there who prepared the seismic hazard map, and there is an attempt here to just update this kind of the probabilistic seismic hazard maps for the Himalayan seismic region. So next slide, please. In the probabilistic seismic hazard, basically we are interested to measure the ground shaking in a probabilistic manner due to the occurrences of the earthquake. So here we measure the predicted level of the ground acceleration, particularly for the peak ground acceleration or peak ground velocity or the intensity. Different kind of the ground motions are basically measured here, and there are the basic two things that we are interested, that is 10% probability in the next 50 years, that is around the 475 years of the return period, and for the longer return period it is 2475 years. So that is related to the 2% probability in the 50 years, and this is the basic equations from which we are estimating the probabilistic seismic hazard. So exceedance level of a particular ground motion, that probability of the exceedance of this ground motion is basically estimated from this equation, where we can see that there are the different terminologies, that is the probability of exceedance with respect to the magnitude and distance, and the probability distribution function with respect to magnitude and the distance. So using this formula, we have estimated the probabilistic seismic hazard map of the India. Of the Himalayan seismic belt. Next, please. So the study region is basically Himalayan seismic belt. Here, it is one of the most peculiar seismic region in the Indian subcontinent, where the Indian plate is colliding with the Eurasian plate and develop the most active region in this region. And you can see the seismicity. If you see the seismicity, most of the seismicity is concentrated along the Himalayan seismic belt. A number of earthquake has been occurred. Some great earthquakes has been occurred, like the 1897 Shillong earthquake, 1905 Kangra earthquake, 1934 the Harnarpal earthquake, and then 1950 Assam earthquake. So these are the major earthquake which has caused a lot of wide space destruction in the region. And on the basis of this distribution of the seismicity, we have categorized different kind of the seismogenic.
Dr. Yadav, you have only 2 minutes left.
Okay, so different seismogenic source zones we have developed. And then next slide, please. We adopted a number of ground motion prediction equation. Next slide, please. Next slide. We have adopted a number of attenuation relationship. Total 13 attenuation relationships have been adopted, and then the probabilistic seismic hazard has been assessed in the Himalayan seismic belt. Next one. So the result is here. First, we have developed the hazard curve, that is the probability of exceedance curves, and this is representing the annual probability of exceeding about the various ground motions in a specific site. So we have considered the different sites around which we have developed the hazard curve, and based on this, the best main initial curves from which the hazard maps has been prepared. So here 2%, 5%, and 10% probability of exceedance has been calculated, that is representing different return periods. Next one, please. Next one. Next, please. Next slide, please. Hello?
Is it not updating for you?
Hello, the slide has moved. We've gone to the next slide.
It might take.
Slide is already moving.
It is not moving with on my computer. So okay, no problem. So in the next figure, we can see that basically we have calculated the seismic hazard for the different sites. The uniform hazard spectra has been calculated, and then the different maps have been prepared, like the peak ground acceleration maps. You can see for the 475 years return period, and then the 2475 years return period. So you can see how a hazard is basically varying in the region, and basically these hazard maps are prepared for the different depth sections, like the 2 to 24 kilometer, then 25 to 70 kilometer, and deep for the greater than 75 kilometers. So you can see that the deep sources are also generating the seismic hazard in this region. Okay, next one, please. And then for the several other maps have been prepared for the different accelerations. So that like the 2.2 seconds spectral acceleration has been calculated. Then the 0.6 second acceleration has been prepared, and then 1 second.
Time is up. Time is up.
Yes, please can you put the last slide, please. So in the conclusion, we have observed the peak ground acceleration is basically varying with 0.66 G, and for the 475 years of the return period, and 1.38 for the 2475 years of the return period. So mainly high PGA is basically observed in the Kashmir Himalaya, Garhwal Kumaon Himalaya region, Nepal region, and Western Assam, Arunachal Himalaya region. Thank you so much.
Thank you, Dr. Yadav. Now next presenter is Satya Biswal. Satya Biswal, you may start with the presentation, please. Satya Biswal, are you there?
Slide. Yes, audible. Hello, ma'am.
Yes, you are audible.
Am I audible?
Please start. You are audible.
Yes,
please start.
slide, please. Slide.
The slide is shared. It might not, it's probably not going to you right away since your network is a bit slow. Just wait. It should show up on your screen as well.
Yes, ma'am. I can see my slide.
Yeah.
Good afternoon, everyone. I am Satya Biswal, worked as a PhD scholar in Northeast in CSR NIST. Glad to present our research work on approximated model for central depth and source localization of anisotropy beneath the Shillong Plateau and Himalaya, implication towards deformation and dynamics. Next slide, please. Next slide, please. Northeast India is one of the most tectonical regions of the.
Mr. Biswal, can you switch off your video?
Mr. Biswal, since your connection is not very strong, I would suggest you to switch off your video so that your voice can come clearly. Mr. Biswal, can you hear me?
Am I audible, ma'am?
Yeah, keep your
Yes,
video closed, otherwise your voice is breaking. No? Yes, you are audible now, but don't start your video, okay? Switch off your video. If you switch off your video, your voice will be clearer.
Yes, sir.
Okay.
Yes. Northeast India is one of the highest seismic potential zone of the world, resembling the complex seismotectonics and geological processes. Shillong Plateau, governed by unique power tectonics, is surrounded major regional volcanic faults. Himalayan Foot-Dip region, which is a narrow valley juxtaposed in between the collisional tectonics and oblique subduction, shows a superposed deformation pattern. Here you can see in the tectonic map of Shillong and Himalayan Foot-Dip region, the yellow star mark represent the great earthquake with respect to year and its magnitude, and the seismic are plotted here in Shillong Plateau by water transmission Himalayan marked by blue water triangle. Our main objective is to determine anisotropy in the Shillong and Himalayan region to understand the pattern better. Next slide, please. And 80 splitting.
We have lost your voice.
Yes, ma'am. His network is not very stable.
So can we move on the next presenter?
Up to you, ma'am, if you say so.
Okay. So we are moving on the next presenter. Nilesh K. Jaiswara.
Nilesh, I don't know whether he's here or not. Mr. Nilesh, if you are here, please let me know. I don't have his PPT with me. He hasn't submitted his PowerPoint presentation.
Okay. Then we will go on the next one. Sonia Devi.
Okay.
Sonia Devi, are you there?
Yes, ma'am.
Okay. Please start with your presentation.
Okay. Presentation, ma'am. Good morning to all. My name is Sonia, and I'm working as a research scholar at Department of Geophysics, Banaras Hindu University. The topic of my presentation is strong motion simulation of 2021 Miyagi earthquake using modified semi-empirical technique. Next slide, please. What is strong ground motion? Strong ground motion is the ground motion when the PGA value exceeds 50 Kelvin, then that motion can be categorized as strong ground motion. Next, please. In simulation, basically, we try to generate data by assuming some model parameters. Therefore, simulation is a forward geophysical problem. Also, from the past earthquakes, it is clearly demonstrated that the site effect site effect can play a significant role in amplification of the ground motion. Next, please. So it is clearly demonstrated in 2001 Bhuj earthquake. This earthquake caused severe damage in Ahmedabad city, in spite being at an epicentral distance of more than 250 kilometers. So site plays a significant role in the damage caused in the Ahmedabad city. So in this figure, in the present work, we have estimated the site effect by using the horizontal to vertical spectral ratio method, and further incorporated the site effect in the existing semi-empirical technique. So incorporation of site effect in existing semi-empirical technique will provide more realistic outcomes. So next slide, please. For site estimation, we have adopted horizontal to vertical spectral ratio method. This method is basically based on the assumption that the vertical component, it is free from the site effect, and when we divide the Fourier amplitude spectra of the horizontal component with the vertical components, so we are only left with the site effect. So next slide, please. This is the formula which we have adopted for site estimation. Next, please. This is the basic methodology for the modified semi-empirical technique. In the existing semi-empirical technique, we have incorporated the site effect in the theoretical spectra. Next, please. Next. So in semi-empirical technique, we start with the wide Gaussian noise, and the fast Fourier transform of the wide Gaussian noise is performed. Then this white noise is multiplied with the theoretical spectra, which was modified by incorporating the site effect. Then the spectra is corrected for the correction function, and the envelope is applied. This process is for a single subfold. The same process can be repeated for n number of subfolds, and by after summing the all the records from different subfolds, will obtain a final accelerogram. Next slide, please. We have tested our modified semi-empirical technique for 2021 Miyagi earthquake. So this earthquake is of magnitude 7, and the black star represents the main shock, and the black rectangle represents the rupture caused by this earthquake. The dimension of the rupture plane are 44 by 18 kilometer. Next slide, please. We have estimated the site amplification at 2 stations. These site effects, they are incorporated in the these site effects, they are incorporated in the bedrock simulated records, and will obtain the records at the surface conditions. So figure B represents the time histories for observed and simulated records. The black lines represent the observed time histories, and the red represents the simulated one. And the figure C represents the response spectra for these 2 stations.
With 2 minutes only.
Okay, ma'am. So further, these results, they are quantified in terms of root mean square error. Next slide, please. In conclusion, for the present case, we have estimated the local site conditions by estimating the horizontal to vertical spectral ratio method, and these site effects are further incorporated in modified semi-empirical technique. The site characteristics observed from horizontal to vertical spectral ratio method, they are further compared with the geology of the region, and it shows a close resemblance with the geology. And further, the simulated and observed records, they are compared in terms of time and frequency domain, and they provides a satisfactory match between these two. Therefore, the comparison, it confirms the effectiveness of the modified semi-empirical technique for Miyagi earthquake. Thank you.
Thank you.
Sir.
Babita, unmute yourself. Unmute yourself.
Sir, Satyapriya
We
Biswal
are
was
finished with the
trying-
presentations. One presenter is absent, and one presenter we are not able to connect him fully. because-
he's trying to, he's asking for permission to present again, ma'am, if you allow.
Okay.
Okay, let him go ahead.
Okay.
Satyapriya,
Please
you can start again.
connect him, please.
Thank you so much, sir, for allowing me to present once again. Sir, please, slide, please. Previous introduction is, so Northeast India is one of the most tectonically active regions of the world, which resembles the highest seismic potential zone and witness some of the great earthquakes, which are plotted in the yellow star mark in the tectonic map of Northeast India, with year and its magnitude. And Shillong Plateau, governed by unique pop-up tectonics, is surrounded by some regional faults like Oldham, Brahmaputra, Dapsi, and Dauki Falls. Himalayan Fort-Deep, which is a narrow valley extending in east-northeast to west-southwest direction, juxtaposed in between the collisional tectonics and oblique subduction, shows a superposed deformation pattern. Our main objective is to determine the source localization and central depth of anisotropy beneath the Shillong Plateau and Himalayan Fort-Deep region, and to understand the mechanism that governs the deformation pattern in Northeast India. Here you can see in the tectonic map, the red inverted triangle represents the seismic stations in Shillong Plateau, and blue inverted triangle represent the seismic stations of Himalayan Fort-Deep region. Next slide, please. For this estimation of central depth and source localization, we have totally used 87 teleseismic co-refracted phases collected from different studies over an epicentral range of 85 to 180 degree, which and we use the spatial coherency method, which is a more reliable grid search method to estimate the spatial coherency. This method finds the central depth of anisotropy on the basis of maximum coherency between fast polarization direction and delay time, represented by a minimum spatial coherency curve. The spatial coherency method has 4 criteria, that is the spatial variation in splitting parameters, and stations must be close enough relative to the depth of anisotropy. The source of anisotropy must be a prediction of single layer, adequate azimuthal coverage. Important parameters we use generally, the Shillong Plateau is gridded with 2 cell size, that is 0.36 and 0.40, with a central difference of 0.11, and Himalayan Fort-Deep gridded in 3 cell size, 0.20, 0.21, and 0.23, with a central difference of 0.16. And in this map, in this tectonic map, that is bars represent the shear wave splitting results, and in 2.C, the blue bars represent the shear wave splitting results plotted on the topography map. Next slide, please. From the above spatial coherency method, we have estimated here in this figure 3.A, this represents the variation factor as a function of depth in Shillong Plateau, and here the minimum of coherency curve achieved at a depth of around 100 kilometer, and at this depth the coherency plot for the co-refracted phases, that is the SK splitting parameters, at a depth of around 100 kilometer, showing the maximum coherency. The events coming from north are plotted by blue solid lines, and the events coming from the south are plotted dotted lines. And similarly, in case of Himalayan Fort-Deep region, the minimum of coherency curve achieved at a depth of around 150 kilometer. At the same depth, at the particular depth, the coherency curve achieved for the different SKS parameters. Next slide, please. From the above studies, we have concluded that the SWS results from the available studies suggest the direction of FPD trends in northeast southwest, which aligned parallel to the absolute plate motion of the Indian plate. Conclude that the asthenospheric flow controlling the absolute plate motion of Indian plate is responsible for the northeast oriented stresses beneath the Shillong plateau. The corresponding depth of anisotropy, that is the 100 kilometer, coincide with the lithosphere asthenospheric boundary beneath the Shillong plateau, which strengthens our implication that the asthenospheric drag at the base of Indian lithosphere is responsible for the absolute plate motion of India, is the major source of anisotropy and controls the deformation patterns of the Shillong plateau. Similarly, the central depth of around 150 km for Himalayan fault drift suggests the asthenospheric force corresponding to this particular depth is suggested as the major source of anisotropy in this tectonic region. Next slide, please. And here is this figures of our study recently published on Geological Journal. Here is the image shown for your kind information. And thank you very much for giving me opportunity to participate in the convention of Igu. Thank you very much.
Thank you, Satya. Sir, over to you, sir.
We have 15 minutes. We have 15 minutes.
Yeah, 15 minutes.
And questions for speakers. And when you are asking a question, please refer to the name of the speaker so that he would address, rather than asking a question and looking for. Please go ahead. Anybody there?
Okay, sir. Any question?
Anybody? Any questions, please?
We need to break the ice. Being the first technical session,
Yeah.
we need to ask.
Valyagi, you want to ask a question?
I could have asked, but I was busy in one
Okay,
meeting,
I'll ask.
so
I have questions for two of the speakers.
Yeah.
First question is to Abhishek, who's talked about static stress drop source parameters, which is computed. Abhishek, could you answer me why there is a variation in stress drop between P wave when you used and S wave?
Can you repeat the question, sir?
Why there is a variation in the static stress drop values when you are using the P wave and the S wave?
Because there is a variation in the in the source radius as we estimated from the P wave and S wave. So as the stress drop is directly linked with the source radius, so we have a variation in stress drop from different types of waves.
So usually when you look at the stress drop, you look for the shear waves or for the primary waves?
So according to Bruns's model, we basically go with the shear wave, but we have a lot of literature where the different scientists use both P and S wave.
The other question which I wanted to, why does that region has low stress drop in context?
It might be due to it might be, I can interpret this like the upper crust in the study area having a low strength material that might be not able to accumulate strain energy for long period of time. So this will release in a short packets. So we generally get a low magnitude earthquake in the NCR regions.
But you also showed a static stress drop versus magnitude, right? You showed. But there is a lot of variation in those static stress drop values.
Yes, sir.
So you have to have a look at it. Good.
Okay, sir.
Babita ji, I have a question for you.
Yes.
Very interesting talk. Actually, it's a very nice presentation, which I should say so. But you know, Delhi can be divided into two. You have the rich as well as the soft sediments. Did you find, I wanted to see the variation, see you showed the variation between the near source effect, near source earthquakes, which are all those moderate, less than the moderate size earthquakes, and then the earthquakes which are coming from the Himalayan frontal, the Himalayan arc, where the magnitudes are larger comparatively to ones what you said. Definitely, when you saw that for the larger magnitude earthquakes, there is a long period waves were coming in and the dominant frequency. Did you see the variation? What is the variation, at least in the high frequency earthquake, between the ridge and the valley, that is the Yamuna sediments, soft sediments where you are?
Yes, because I have not shown all stations results over here. I have found in hard rock areas different kind of predominant periods, and basically means both the earthquakes, like near field also and far field also. But we have to correlate these earthquakes with the sedimentary thickness also. Whether these kind of like things we are observing from the low lying sediments or some deeper layers. So for that, we will extend our study for estimating the sedimentary thickness also, and also the long period observations for getting the other parameters also in line.
Yes, see in the initial talk, the first talk which indeed when Dr. Chadha was presenting, he showed you comprehensively how from thickness to variation and then the frequencies, amplification and the dominant frequencies. Indeed, that is very, very important. Characterization of the sediments have to be done. That is the first thing which needs to be looked into, and especially the thickness of the sediments. And I think you have got these local earthquakes. From that itself, you will have the P2S converted phase, S to P or P to S.
Yes, sir, we are already planning to do the site characterization by using this data only, which we have already recorded, and we will then demarcate the amplification values both for the near field and the far field also. So that we have to do in near future.
And also for these local earthquakes, did you use the spectra of the horizontal divided by vertical and remove the source effect, and did you see
that's what I am saying you, sir? We will do it with the same data. Just now we have only done the response analysis, which I have showed in my results.
No, I saw that. I'm also asking, have you done? That's why.
No,
so
sir.
In 5 minutes you can't show everything.
I have to do that, sir.
Yes. Okay.
Yes. Thank you, sir.
These are the questions from my side. Anybody else? Please go ahead.
Yeah, anybody, this is a good platform for you to interact. If you want to comment or say, if not a direct question, something you can pose. All of you are free to say something, comment something.
Sir, can you hear me?
Yes.
Yeah. Actually, I wanted to test my mic also, so that's why I'm asking a question. So my question is to Abhishek again. So Abhishek, how many earthquakes have you used for your analysis?
Sir, I use around 13 wind.
13. So,
yes.
Suppose you take one earthquake only and you do P spectra and S spectra. Will you see any variation in the parameters that you get?
सर आई थिंक अगर मैं इवेंट यूज करता हूं मेरे पास सिर्फ एक ही वैल्यू मेरे पास आएगा सर, मतलब स्ट्रेस ड्रॉप का मेरे पास एक ही वैल्यू आएगा सर. सो यूजिंग वन इवेंट आई थिंक इट माइट बी वेरी डिफिकल्ट to get variations in the different source parameters.
No, I'm saying that you take one earthquake, you take the P wave and do the analysis. You again take the S wave and do the analysis. Will you get a variation in the stress drop or the moment magnitude or the M naught? Will you get एक में आएगा variation?
I think so it is not possible to get a variation using only one earthquakes. That's why we use a huge number of data to analyze the variations between various source parameters.
No, you are not honest. So if you take one earthquake, you will say that you will get the same stress drop, you get the same moment magnitude, you say same M naught. Okay. You take the second earthquake, you do the analysis, you will know difference. You take another earthquake, you take the difference. So for different earthquakes, you will get different stress drops, right?
Yes, sir.
Now you are saying, so for all of the earthquakes, you should get low stress drop, because you are saying that the final stress drop is low.
Yes, sir.
Okay. 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 All right. I understood now. Okay. And another thing, when you say low stress drop.
Yes, sir.
So you are saying that the earthquakes happening very frequently.
No, sir. The earthquakes are occurring with low magnitude because the subsurface material is not, I think, not capable for storing the huge amount of strain energy. So the rocks, I think, undergoes a brittle fracturing and adjustment. That's why we're getting very low magnitude earthquake around 3, 2, and 5 around magnitude in the Delhi NCR region.
But this also means that it is fracturing very quickly. No, one earthquake happens, a little stress drop accumulating, another earthquake, a little stress drop accumulating, another earthquake. So the
Yes,
earthquakes
sir.
are happening fast.
Yes,
so do
sir.
you see many earthquakes in Delhi?
So yes, sir. I think in 2020 we have a lots of earthquakes during period of, I think, May, March, May, and June. I think. Maybe.
Okay. Okay. Thank you.
Thanks.
So yeah.
Yes.
Please go ahead. Valiaji, Jai.
Yeah,
Please go
one
ahead.
small request to everyone. If possible, you can switch on your video for a fraction of seconds, for 30 seconds, to have one photograph for this technical session too. Because I see that many people, more than 77 were attending this session. So just switch it on so that let us have one photograph for record.
Professor Walia, I have one small comment.
Hanji.
I have an advice for Dr. Yadav. In his presentation, the figures which he was showing, he has to be a bit careful, because in that the boundaries of J and K were shown, which were not in agreement. This is a very, very serious thing, because it's a national convention.
I also wanted to comment on
that.
Yes.
So yeah, just pass on this message to him that he should be more cautious while doing this.
Okay, sir. Thank you. Thank you, sir. I noticed, but it is by default in GMT it is plotted. But
many times we do take from other countries, then such problem is there. So we need to be cautious, especially while presenting outside India also, definitely. Important observations, sir. Thank you very much, Chadda sir, for giving this important, because that's how we learn, that's how we improve. So all of you, please, Meghali, I don't see your
YouTube.
Satya Singh ji, Hanji.
Can we remove that from YouTube, from our RBS presentation? Because of this boundary issue, there's a serious issue.
Yeah.
If possible, please remove from YouTube.
Sir, it can be blurred out or edited out as per needs.
It is live telecasted, so we cannot do anything, sir.
We can't change the live telecast, or you can change the video.
In the beginning, I wanted to say this, but somehow I said that for ice breaking, if I'll say this, then it is not good. So this is important.
Okay.
But we cannot do anything, Bansal Saab, now. But we must take care. So it's okay. It is important that it is pointed out, and it should be taken care of that way. So I think many of us are there videos. So many of us have not yet switched on the video. If you can listen to me, you can switch it on before we go out for lunch break. Because lunch break is going to be there for 45 minutes. We'll again get in at 1:50, so that 5 minutes before 2 we can start the program.
Dr. Walia, this is Mala from SGRC. I'm audible?
Yeah, 100%.
Yeah, good. Actually, there is small suggestion from the presentation by Swati and Devakar Pundir. They were trying to correlate this GPS TC variation and ULF emission and with the earthquake precursors, I think Rudraprayag earthquake.
Yeah.
So I would like to make a small comment here that ionosphere is a highly dynamic region. So I think Ms. Swati was trying to say depletion and enhancement. They are trying to correlate with the earthquake precursors. So one needs to take care of day-to-day variability of the ionosphere before establishing or validating such kind of correlation. And same is true for ULF emission also. So this is a small comment for the presentation.
Yeah, important. I hope Swati and Devrat Pundirji is there. So you can consult further also and take care of such comments.
Thank you.
So, yeah, but you could have switched on your video while speaking at least. Yeah. All right. Thank
Hello,
you.
sir. Thank you.
So those who are there online, hopefully organizers, they have clicked some photographs. So again, I'll hand over mic to Shri Nagesh ji for closing remarks or whatever.
Thank you very much, Professor Walia. Thank you all the presenters for sticking to time, and it's an auspicious beginning so that there is not going to be a cascading effect. And kindly bear in mind, as Dr. Chedda has said, when you're presenting the maps, the boundaries of the India have to be correctly shown, because it is admonishable, and we cannot run away when we don't show our boundaries of the country properly. Thank you for all the presenters for making wonderful presentations. Thank you, Walia ji. Babita ji, would you like to make any closing comment?
Thank you, sir. It was really very informative session because we have talked a lot of related to the strong ground motion, also the seismic hazard point of view. It was really informative. I am also thankful to all the speakers, and thank you, sir. Thank you.
Thank you. Thank you.
Yeah. Thank you, everyone. I would like to request, only one small request is there to our rapporteur, that please make short report of the presentations. Today, 8 presentations were there in the first technical session. For the technical session as such, make a short report and present it. Even you can share it in the chat box if you write short report. Thank you very much. Bansalji, any
Sure, sir, I will take care of it.
Organizing committee, any organization, anything, any comment or anything before we end this session?
Maybe reporter can give his report after the session, after the question answer.
Yeah, Sandeep Arora ji has heard probably. Yeah.
Sandeep, you want to say something? Please.
Reporter.
Sandeep Arora.
Sandeep ji, if you want to say something, although his connection seems to be stable, his face is not moving.
It's frozen.
It is frozen. Yeah, Shillong is cold, but his place is also cold, that seems.
He's from BHU, yes.
Yeah. No, it's all right. I found his face frozen, so that's why. Sandeep ji, are you there? No. I think some connection problem. So any announcement? Yeah, now he's there. Now he's there. No, but it is still frozen. So, sir, with the permission of the chair, co-chair, and Bansalji, I would like to thank you all, and I would like to thank Dr. Shri Nagesh ji. Yeah, you are moving. Sandeep ji, would you like to say something?
Hello.
Yeah, would you like to say a short summary of the presentation?
Yes, sir. Yes, sir.
Yeah. It was requested to you that please send a short report on
yes, sir. I will send it after this session.
Yeah, now your time to speak.
So I can conclude the whole session, a brief review of the whole session.
Please.
So first of all, I would like to thank Chairperson Dr. Shri Nagesh, Co-Chair Dr.
Your voice is not.
There is a bad connection. There's a bad connection, Vaidyaji.
Yeah, you may switch off your video so that your voice.
Including
It's frozen.
Dr. Mohan, Dr. Yadav for these informative talks. In this studies, out of this 8 participants talk on strong ground motion studies in Indo-Gangetic, the modified source location of Ms. Swati presented the precursor study related GPS, TEC and ULF data. Mr. Abhishek discussed the source characteristic of different earthquakes in Delhi region. Dr. Sharma then presented a useful talk on earthquake ground vibration motion for NCR region. This is followed by a nice talk on updated PSHA maps for Himalayan belt by Dr. Yadav. Mr. Biswal demonstrated the idea of anisotropy beneath the Shillong Plateau and Himalayan Fordip region. Lastly, the session ended with a talk by Ms. Sonia Devi on strong motion simulation. So on behalf of all the committee members, I would like to thank everyone for their enlightening talks. Thank you everyone.
Thank you, Sandeep. Thank you very much. Valyaji, unmute.
Yeah, that's the problem. Thank you. So thank you, Sandeep ji, for giving short or brief report of the program. I would like to thank Dr. Shri Nagesh ji for chairing the session, Dr. Babita for helping the chair as co-chairman, and Sandeep Arora ji for being the rapporteur. All the dignitaries present, because of you only, the program is successful. All the presentations, they were quite good. And now this link will be on, so you can join, you can leave or whatever you want. You can leave the program now and join by 1:45. We'll try to start next session at 1:55 so that to cover up some time. You know that Shillong is very cold. By 4:30, it becomes dark. So before it is dark here, your place may remain lighted. Before it is dark here, we would like to finish off most of the activities. So with this, thank you once again. Thanks. And organizing committee, would you like to say something?
No, sir, everything's fine, sir.
No. So all right then, see you at 1:45. Thank you.
and be reduced without any
Rao Sahab, good afternoon.
Good afternoon, Dr. Walia. So am I too early?
Yeah. You can check you are given granted permission to share your slides. Just check once.
I have already I submitted the PPT.
Your PPT, but they said that it is not there.
And now.
अच्छा, just now submitted.
शायद 1 hour हो गया. Yeah.
Oh, all right, sir. Let me check.
Yeah. हमने तो आपको शेयर करने के हिसाब से we kept the system ready.
Oh, अच्छा. I think it's better it's played from your side, I think.
Yeah. No issues. So morning session went on well. It ended also as per schedule.
Yes. Yeah, that's
we are
good.
waiting for Dr. O.P. Mishra ji to join. The moment he joins, Bansal sir, we will start the program, isn't it?
Yes, sir. We are waiting for Mishra. I will call him and let you know.
आपकी आवाज साफ नहीं आ रही है.
Okay, I'm calling him, sir.
नहीं, पास से बोलने से भी वो करती है, क्या बोलते हैं, कुछ पतली हो जाती है.
अभी सर, now?
अभी रिलेटिवली ठीक है.
अच्छा, वीडियो
कई लोग लिख रहे थे, कई लोग मैसेज कर रहे थे, आपकी आवाज नहीं आ रही है. हमने कहा हम लोग कुछ नहीं कर सकते हैं, बंसल साहब को ही रिक्वेस्ट करिए.
अच्छा, उसी टाइम बोलते तो मैं वीडियो ऑफ कर देता.
नहीं, अभी भी आपकी आवाज ना थोड़ी सी पतली हो जाती है, पिच उसकी बदल जाती है.
ओके.
कुछ आपका जो माइक्रोफोन है उसकी कुछ क्वालिटी के ऊपर है.
ओके, माइक्रोफोन का है या बैंडविड्थ का इशू है?
हाँ, आपको हमें एक माइक्रोफोन गिफ्ट करना होगा.
थैंक यू. आई एम कॉलिंग ओपी मिश्रा साहब.
लाइक देखिए, राव साहब की आवाज कितनी क्लियर आ रही है. पीसी सर, विल यू प्लीज स्पीक समथिंग? देखिए कितनी क्लियर है.
Yeah, I hope it is still clear.
Yeah, very clear. That's all.
Very clear.
Abhay, you can use headphones for better results.
Actually, headphone is no face. I'm in isolation.
मिश्रा साहब को रिमाइंड तो नहीं कराना पड़ेगा ज्वाइन करने के लिए?
आई एम कॉलिंग हिम सर.
हाँ, जस्ट प्लीज.
Who is the co-chair?
Co-chair is Mala Bhagya madam. She is there.
Yeah, good afternoon, sir.
Good afternoon.
Good afternoon, madam.
How are you?
Yeah, I'm fine. How are you?
Fine, thank you, sir.
No, if there is some delay for Mishra Saab, then I think you should start.
Okay.
No, it's still 1 minute.
We'll wait.
हाँ, अभी टाइम है, 2 मिनट है.
Mishra is joining, sir.
Hello. Good morning to all of you.
Namaskar, Dr. Mishra.
Namaskaram. How are you, dear?
Yeah, I'm fine.
So today I was down a little bit because of the tonsillitis and my fever.
Oh,
but
I see.
Now AGU fever is better than the natural fever of body.
Okay.
IGU fever.
So officially, I would like to welcome Dr. O.P. Mishra, Director NCS, for this very important 58th Annual Convention, especially on the topic natural hazards, recent advances in earth sciences with special emphasis on natural hazards. So with the permission of the organizing committee, I think I should start the program. So I would like to welcome Dr. O.P. Mishra, Chairman of the session, and Dr. Mala Bhagia, the co-chair of the session, and rapporteur Dr. Rajesh. Hopefully all three of you have joined along with the other presenters. I am very happy to see that after lunch session also, we have got on dot 46 participants are there. Probably as the time passes by, the participation will increase. In the morning session till end, there were more than 77 participants. So it is very encouraging. So without wasting much time, I would like to hand over the dais to Dr. O.P. Mishra Sahab. Hopefully, because of the time constraint, hopefully you will be able to do justice. And there are 10 presentations and one of them is absent. So we will get time, 5 minutes extra for that. Although there is half an hour discussion towards the end, so it will further give you sufficient leverages to manage the time. So Dr. O.P. Mishra, sir, please.
Thank you very much, Professor Walia. I'm really grateful to IGU to give him the opportunity to chair the session 3. It is a very important session. It is the recent advances in the earth sciences with a special emphasis on natural hazards, development of new techniques and the methodology, integration, hazard assessment, risk analysis. And there are total 9 speakers. One is the lead speaker, and the lead speaker has 15 minutes time, and all the speakers, other speakers, 8 speakers have 5 minutes time. So I just request the other speakers to just give the findings, what they have done and how this work is unique for them, because 5 minutes you can cover only that. And at the end we have the half an hour discussion, that is 15 to 30. 15 hours to 30 hours, that is 30 minutes we have discussion. So I would now request Dr. Purnachandra Rao, N. Purnachandra Rao, for speaking for 15 minutes, seismic monitoring, key to development of early warning system for geohazards. So Professor Rao, floor is yours.
Sir, please unmute.
Sir, you are muted, sir. No, sir.
Oh yeah, thank you very much, Dr. Mishra. So today my presentation is about a new emerging field called environmental seismology, which we have just started in NGRI last year, and it has very wide applications other than earthquake studies. So I will give you a few examples. Since it's a new field, I'll take the liberty to show a few examples before I show some of our results. So this is a very recent development, so I'm quite excited to share with all of you. So can we have the next slide, please? Yes. So what is environmental seismology? So far, seismology has been confined mostly to study of earthquakes and sometimes nuclear explosions. But as you all know, that the mechanical disturbances in nature, which could be due to atmospheric, hydrospheric, cryospheric, or solid earth disturbances, they're all recorded by the very sensitive seismographs, which are in hundreds all over the earth. So these include noises generated from geohazards like earthquakes, icequakes, volcanoes, landslides, rock slides, avalanche, debris flow, floods, cyclones, etc. Or you have ambient noise generated by ocean waves, wind waves, and rainfall. You also have anthropogenic disturbances due to traffic, trains, industrial noise, drilling, human and animal movements. So you have a vast range of noises that can be recorded, and I will show you what all applications are there by using these kind of recordings. Next, please. Yeah, so the evolution of environmental seismology is into so many fields now. You have what is called ambient noise seismology, which is becoming very popular now. There you don't need any sources, you don't need earthquakes or explosives, but the background noise itself contains a lot of signals. And if you cross correlate data between two stations, two seismic stations, you get a Green's function which looks more like an earthquake wave, and represents the structure between those two stations. So this has now been widely used for tomographic studies worldwide. Then you have fluvial seismology, which refers to seismic monitoring of river flow, and along with it the sedimentation. By using an environmental seismology, you can characterize all the details of this river flow and the sedimentation. And then you have glacial seismology that deals with the icebergs detachment or ice breaks and flash floods which are caused due to glacial lakes and things like that. And then urban seismology deals with the noise generated mostly in the urban areas due to industrial traffic, trains, and so on. And you'll be surprised how this noise can be utilized very usefully for mapping the subsurface structures. Then you have what is wildlife seismology. Actually, this is a term coined by me because now I find a lot of applications are emerging in terms of monitoring the movements of wild animals in forests. By using seismic recordings, it's possible to do that. I'll show you some examples of that. And lastly, geohazard monitoring. So now with the kind of technology we have with dense networks, it is possible to monitor not only earthquakes, but landslides, avalanches, floods, and rock slides, and so on. All the geohazards can now be monitored if you have a good network. Next, please. So these are some of the applications of environmental seismology. I will not go into details of all of that, but basically you can monitor geohazards, you can monitor glaciers, you can model sediment transport, river deposition, groundwater changes, volcanic eruptions, and so on. I mean, there are so many others, other applications as you can see on the screen. Next, please. Yeah, the critical zone is the breathing layer of the earth where the entire life is confined. So basically we are talking about the very shallow top layer where you have the life, the trees, the animals, the forests, the rainfall, you have the hazards, everything that is there. So it has now become an important subject to monitor these critical zones, and environmental seismology is one subject that can monitor all these physical changes that happen in the critical zone. Next, please. Yeah, landslide monitoring also. It has been shown that when you if you monitor velocity changes between seismic stations, then you find very clear signals. You can see in this figure that you have drastic change in the velocity just prior to a few days prior to the landslide activation. Next, please. Yeah, this is the example of modeling of river flow and sediment deposition. So if you do the spectral analysis of the seismic signals, then it is possible in the frequency domain, you can separate out the contribution because of the turbulent flow, the sediment transport, the explosion of air bubbles, gravity waves, and so on. So basically you can even characterize the size of the pebbles or the kind of transportation, the quantity, the velocity, everything can be characterized by analyzing the seismic signals. Next, please. Yes. So this is an example of how groundwater level changes can be monitored with seismic data. And you can see here, this is an example from Koina, where you can see that the change in the water levels as a function of time, and this actually corresponds also to the seismicity occurrences. So it is now possible to correlate groundwater level changes with seismicity. Yeah, next, please. Yeah. So glacial lake outburst flood is a major crisis. You have hundreds of glacial lakes in the Himalayas sitting at great height, and because of ice melting or if there is a crack in any of these glacial lakes, the entire lake can be flooded. It can flood the foothills of the mountains and the inhabited areas. A very dangerous thing. So now it's possible that if there is any break, you know, the glacial breaks or the iceberg detachment generates signals which are recorded on the seismographs, and there is possible to give a prior warning if there is any such possibility. So we are now looking at all the glacial lakes, and we hope that it will be possible to give warnings in future. Next, please. Yeah, this is an excellent example of how environmental seismology can be used for volcanic eruption forecasting. And this is an example from La Reunion Island in the Indian Ocean. And you can see in the plot below, the red signals are the changes in the velocity that can be seen just prior to the velocity, the eruption of volcano. That means when the magma is coming out to the surface, obviously the velocity of that region will change. And therefore that velocity change is reflected in the seismic correlation between stations. And if in a real time, if you can monitor this, it is possible to predict the speed, the velocity with which the magma is coming up. Then you can actually forecast when the eruption will take place. So this has been successfully done for the La Reunion Island by French scientists. So this is a very big prospect for future. Next. Yes, even in the oil industry, this subject can be utilized. In fact, you'll be surprised that the explosive can be substituted. The seismic sources can now be substituted with background noise. So using ambient noise, the kind of the reflection seismology is now being done without these seismic sources. You can see these two examples. One is using the seismic explosive source. The other one, the second one is using the ambient noise, and they're very, very similar sections you can see. And below you can see the kind of the tomographic images that can be generated. The very high resolution sections can be generated. Next, please. Yeah, this is a very interesting development of tracking wild animals in the forests. So, you know, when wild animals are moving around in forests, their footsteps, they make mechanical disturbances or noise, which is recorded by a seismograph station. So if you install a seismic network around a forest area, it is possible to locate and track each one of these animals. And particularly for elephants, it's possible, it's easy because they generate low frequency signals compared to the other animals. So this is now, in fact, only last year there was the first study that was published, and it shows how you can track movements of elephants. This is very important because, you know, the forest officials, they have a lot of problems related to elephants coming out into inhabited areas or blocking the railway tracks and things like that. So this is another application that has emerged, a very interesting application. Next. Yeah, this is something unbelievable that, you know, the whales, they make a noise, which is again low frequency, and this can be used as a seismic source to map the seafloor structure beneath the seafloor. So the conventional seismic imaging of the seas, in the oceanic regions can now be done if you have an area filled with whales. The sounds generated by whales act as sources that will tell you about the structure beneath the ocean, so shallow structure. So this has tremendous applications, and this also has just something that has just started, and people are trying to apply this. Next. Yeah, so last but not the least, this is about monitoring of geohazards. Now, in this figure, you can see the first image. These are all seismic records of different geohazards. You can see the first one is that of a rock fall. The second one is that of an earthquake. Third one is that of a debris flow. The fourth one is that of a sediment transport. And each of these has a distinct signature, the seismic signature. And on the right side, you can see the spectrogram. The spectrograms are also distinct, and they occur in distinct frequency ranges. So if we develop proper tools, we can characterize and we can identify these events on our seismic records, and it is possible in real time to detect and give early warnings for some of these hazards. Next, please. Yeah, now I'll come to the work carried out by us during the last year, which was on the 7th February 2021 Chamoli disaster. I think all of you are aware of this major disaster. It is approximately 1 year ago, and this occurred in the Chamoli district, where you had a huge rock slide at Rontigad, and this created an avalanche and a debris flow which flooded the Rishi Ganga and the Dhauli Ganga rivers, and the flooding proceeded to Alaknanda. And this also destroyed the hydroelectric project, the power project of NTPC in Tapovan, and about 200 people were killed. So it's a major hazard. And since then, there has been a lot of interest shown towards developing of an early warning system. We are currently working on this. And this work, you can see here, the seismic record is so clear. It's like a textbook example. You can see that rock slide, you can see the mass flow, and the third spot, you can see the flood very clearly in the nearest station. And this work was published in Science. We had 2 papers in Science last year, yeah, as you can see at the bottom, one in April and one in October. I will show you some slides regarding with reference to this work. You can also see in this small window, the seismic network. We have about 70 to 80 seismic stations in this area. That red spot is the event that occurred, which was recorded very beautifully. And we demonstrated that we had at least about 30 minutes of lead time. It would have been possible to give a early warning. Next, please. Yeah, so this is the first one. There is a rock slide phase, the starting of this geohazard cascade. And it could be recorded about 1,000 kilometers away. On the right side, you can see all stations from abroad, the Kathmandu, the Islamabad, and in Kabul. This rock slide was clearly recorded. So the starting point was recorded, and subsequent phases were also. And you can see that the signal to noise ratio is so high. The green spots are the signals, and the red and blue bars, they show the background noise. So the SNR also is pretty high and very clearly recorded. Next, please. Yeah, so this is about the mass flow. That also was well recorded, although not so sharply. So about up to 200 kilometer distance, which was recorded, and SNR is a bit lower compared to the rock slide, but nevertheless, it was very well recorded. Next, please. And lastly, the flood phase also was recorded, although flood is not very sharp, very clear. So up to 100 kilometers distance, the flood signal was recorded. The SNR is rather low, but since we know that the rock slide and the mass flow has started, so it is possible to do a predictive, kind of a predictive deconvolution to see where the flood phase is in each of the seismic records. Next, please.
2 minutes left.
Yeah, I have only 2 slides. Yeah.
Okay.
So these are the major findings from the study, as you can see. So we showed that large flow events can be detected across a seismic network and can be tracked as they move downstream. And NGRA network would have been sufficient for an early warning of the 7th February event with up to 30 minutes warning for Joshimath, 10 minutes for Tapovan, and a few minutes for Rishi Ganga. So this study suggests that early warning based on regional seismic networks is very much possible. See, on the right side, you see the techniques used for locating and tracking the flood, which was developed in NGRI, this methodology. And this will be presented by Rajesh in the afternoon session. So I will not speak much about it. Next, please. Next, yeah. So this is the first science paper that came in April. And next, please. This is the second paper, which comes with all the details of the scientific study that was carried out. So this work was carried out in collaboration with the GFZ Potsdam, and so we are very glad to state that it got published in a very high journal. Now we are developing the early warning system, and we are working on that. And I hope very soon we'll be able to provide a success story with respect to early warning of geohazards. Thank you very much. Next slide, please. Yeah, thank you.
Thank you, Dr. Rao. It is very nice and crisp presentation. I think my co-chair, Dr. Mala S. Bagia is there. So I request that you should please note down some questions are there. You can look into that. And now straightway, I'm not going to allow anybody questions because at the end we ask question. So may I request, isn't it okay? So in the end, the question will be invited, isn't it?
Yeah, that's true. That's true.
So now the next speaker is Rajesh, on detection of the 7th February 2021 Uttarakhand rock slide in Himalayas, India, using the seismic data. So you have really, the work is very good, wonderful work, but we have given you only 5 minutes. I think it is better for you to speak in 5 minutes.
Yes, sir. Thank you for giving me this opportunity. And I mean, initially you have seen some results from the Punchandra sir talk. That is, we are able to detect and track the landslides and rock slide events using the seismological data. But the key, next slide. Yeah, but the key success of this tracking and detection of these events are mainly associated with the methodologies involved in, let us suppose. So far people are using the spatial migration and amplitude source location methods to track and identify the landslides and associated mass flow events. But unfortunately, these two methods are grid search methods, first thing. Secondly, these two methods involve the crustal parameters like velocity of the region in the spatial migration method and attenuation factor of the region, particularly for the amplitude source location method. So both the methods involve the crustal parameters. But as we know, the location of these events are random and they can occur in any region. So once we fix with the grid search method and using these two methods, so uncertainties in the crustal parameters as well as the location of the event, they will crucially influence the accuracy of the results and as well as the time required for the computation of these things. So we have find another method, like we tried with a method which is conventionally used in the seismology, that is polarization back-azimuth method, to detect the landslide signals. And we would like to present this method in this work because this has a facility like it doesn't depend on any crustal parameters, and as well as the time required for the computation is completely independent of the location of the earthquake. Therefore, we present here in this work the comparison of all the three methods in a crisp way. Go ahead, next slide. Yeah, here you can see in the left top panel, this is already discussed by the Punchandra sir. This is the Uttarakhand event location, which we have located using the seismological data. In the top panel, the inset was showing the seismic signal of the events like rock slide and mass flow and flood event. So we are not particular now in this presentation about the flood event and mass flow, and we are only analyzing the rock slide event. You can see on the right panel figure, this is the signal recorded by the seismometer, the top one, and the second figure shows the bandpass filtered. That is raw signal spectrogram. You can see in the third panel figure in the right side. Here you can see, and the shaded region shows the spectral content between the 1 to 5 head, because as we can see in the spectrum of the data, the energy is mostly populated in the frequency band of 1 to 5 head. So we have selected this band and filtered the data, and we have used nearly 14 stations. You can see in the left bottom figure, these are the red triangle show the 50 stations used in this study. Next slide. So particularly here we present the three method, that is spatial migration method, which the method, I'm not going deep into the methodology, but I will brief it. Like, it involves the velocity of the region, and it discretize the entire region into grids, as well as by assuming the source location at a point, it will migrate and try to minimize the error between the observed envelope timing, envelope peak timing, that is the phase of the envelope. So by minimizing that, we can estimate the location. By that way, in the spatial migration method, we have estimated the location. Here you can see the gray shaded region in the right top panel figure. This is the location estimated from the 5 stations: Auli, AUGM, TRNR, THN, and DH. And similarly, we have used the 14 stations in the amplitude source location method. You can see here, this is the location obtained from the 14 stations using the amplitude. The crucial parameter is the attenuation factor of the region. As this terrain is too complicated, getting the attenuation factor which gives the best results for different locations may vary. And here you can see in the left panel figure, polarization back azimuth method. So we have estimated the polarization back azimuth of the signal which we have identified in the previous figure, and the polarization back azimuth at the particular event time is exactly shown with the arrows here, and they are all intersecting at a point. As there are discrepancies in the timing of the signal due to the fact that there is a random background noise always there in the seismological data, due to the fact there is an uncertainty even in the polarization method. But from the 5 stations which we have used for the spatial migration, the same 5 stations we have used to estimate the back azimuth of the event location, and all these 5 stations are shown with the arrows. And by drawing a ellipse cycle with the intersecting points of these arrows, will give us the location of the land rock slide event. You can see here in the pink ellipse here, this is the even there is an uncertainty because rock slide and landslide events are not exactly the point sources, as we can see in the case of the earthquakes. Next slide. So in brief, that we have discussed the multiple station polarization back azimuth method as a substitute for the amplitude as well as the spatial migration techniques for potential early warning system, because that, as already I have discussed, this time required for the computation of this location using the back azimuth method is independent of the location of the event, and it doesn't involve the crustal parameter. That is the crucial thing of this method. And probably if we want to develop an early warning system using the seismological data, we have to search and trial with the different methods which even provide the best accuracies. So in that way, we have coined this polarization method as one of the best methods. For that, we will trial this in our real-time work. And next, our final conclusion is like, final conclusion is like, so this is the one of the best method to be coined with. So far, people have not trialed with this method. Now we are in the race to trial with this method. Next. Thank you. And I would like to acknowledge.
Yes. Thank you very much, Rajesh. You are on time. I appreciate your time constraint, and you have given a very good presentation. So can we move to the third presentation? I think she is session chair, co-chair, Mala S. Bagia. GPS measured tsunamigenic ionospheric perturbation and possible early warning scenario. Yes, Mala.
Yes, good afternoon, sir.
Good afternoon.
Yeah, good afternoon, everyone. Can I have my slides, please? Yeah, thank you. So before I talk about my slides, I would like to recall the speech by Dr. M. Ravichandran from morning session, where he emphasized on the Earth system as couple system and our efforts towards improving on the understanding of 5 spheres of the Earth, interaction between them in various time scale, and our endeavor to work towards securing the life and livelihoods in sustainable manner. Our recent efforts made by us are probably in the same direction, and we are trying to study the coupling between the lithosphere, atmosphere, ionosphere system with an aim to develop a tsunami early warning system based on the ionospheric measurements. According to the title of my presentation is Tsunami Genic Ionospheric Perturbations and Possible Early Warning Scenario. Can we go to the next slide, please? Yeah, so before we go into the results, just a brief of the mechanism, lithospheric, atmospheric, ionospheric coupling during the earthquake events. So I have taken an example of offshore earthquake. So during any earthquake, the first perturbation which goes into the atmosphere, those are acoustic wave directly from the epicenter, mainly from the epicenter and mainly in the acoustic wave. The second perturbations which get introduced into the atmosphere from the propagating Rayleigh surface wave, those are also mainly in the acoustic wave. And if since this is an offshore earthquake, the tsunami, propagating tsunami can also introduce perturbation into the overlying atmosphere that can be in the 2 frequency range, acoustic gravity and the gravity range. Now, acoustic gravity perturbation, they travel mostly ahead of the tsunami. We'll see in the next slide. And gravity perturbation, they travel behind the tsunami. Can we go to the next slide, please? Yeah. So in one of our recent case study where we where we try to study the ionospheric perturbations during the 2004 Sumatra tsunami event, we have taken GPS measurement of the ionosphere from the Indian East Coast, the stations which are the colorful triangle in this figure, and the stations are installed under the ISRO Gagan project. So from this, starting from the Trivandrum to Guwahati, means southern part of the India to low latitude station, ionospheric perturbation observed almost simultaneously at the Indian East Coast after the onset of Sumatra 2004 event and before the arrival of tsunami at the Indian East Coast. When I say before, it's around 90 minutes, means 1.5 hours. So the perturbations are as shown in the right-hand side plot. These are the absolute TEC. This TEC is measured by the GPS satellites. Tracks are shown in the right-hand side figure, the colorful tracks, and the onset are the disk is the onset of the earthquake. So when we try to determine this perturbation, we can see that the 60-minute envelope present in the GPS satellite measurements made at the Indian East Coast, and the frequency is around, the period is around 30 minutes. So gravity frequency, all this perturbation, if these perturbations are induced by the forcing from the north or southern direction, then there should be certain time delay in the onset of this perturbation. But those are also simultaneously in the Indian East Coast. That means the source is not coming from the north or south, but they are from somewhere else. And how to correlate this perturbation with the propagating tsunami? Because this is only like eye rolling game. We are trying to correlate this perturbation with the tsunami. So in this figure, GMT map, we have given the tsunami counters also as the to show the tsunami propagation over the Indian East Coast. Can we go to the next slide, please? We have performed a simulation study to validate that these perturbations are generated by the propagating tsunami. The simulation was performed for the tsunami ionospheric atmospheric interaction, and in the simulation results, we have plotted the output at 20 minutes, 30 minutes, and 40 minutes after the event. The green counters are the propagating tsunami, and the red and blue counters are the ionospheric perturbation generated by the tsunami inputs from the ground. So one can see the green counters, which is the propagating tsunami, that is well behind the ionospheric perturbations. And within 30 minutes of the event, ionospheric perturbation reached at the Indian East Coast, but tsunami is well behind. Now, when we try to calculate the velocity of the propagating tsunami and the ionospheric perturbation, the tsunami on an average velocity over the Indian Ocean was around 200 meters per second, and the ionospheric perturbation velocity was around 600 meters per second. That is in acoustic speed at 200-300 kilometers of atmospheric height. That means ionospheric things travel 3 times faster than the tsunami at the ground. So this can be very well used for the tsunami early warning. But here the Indian East Coast was around 1,500 kilometers away from the epicenter. What about the near field stations? So based on this result, we developed a theoretical model to calculate the tsunami early warning time at various distance from the epicenter, and we have divided this various distance in the critical and high critical and moderate zones to provide the early warning for the tsunami. Can we go to the next slide, please? This
Mala,
particular,
1 minute more.
yeah,
Mala,
yeah, sure. Yeah, sure, sir. And this particular result is under consideration for publication. So once it comes online, I will be presenting that results again at the suitable platform like IGU. So, but today's presentation, I can conclude with the line that ionospheric based tsunami early warning system is under preparation. Thank you so much. Thank you so much, organizing committee, for this opportunity. Yes, sir.
Yeah, very good, Mala. Really good. So this is really a very prospective session that we are going to speak different tools and different methodology that can addressing the issues of the early warning of the natural effects, natural processes, whether it is related to earthquake or the tsunami-genic earthquake. So it's very nice. So go to the fourth speaker. That is the Rss Shankar. Remote sensing and GIS-based landslide susceptibility mapping using the frequency ratio method and Sikkim Himalaya. Yes, Rss.
Hello, sir. Hello, sir.
Yeah, please.
Good afternoon, everyone. Myself is Rss Shankar, Research Scholar, University of Allahabad, under the supervision of Professor J.N. Tripathi, University of Allahabad. My topic is remote sensing and GIS-based landslide susceptibility mapping using frequency ratio method in Sikkim Himalaya. So next slide. The current study aims to identify landslide susceptibility map for Sikkim Himalaya, India, utilizing integrated methodology of geography information system, remote sensing, and frequency ratio method. There are several factors for occurrence of landslide, but in which two major factors, one is rainfall and second is earthquake, which trigger the landslide drastically. For landslide susceptibility mapping, has used multiple data sets: rainfall, lithology, distance to faults, distance to drainage, geomorphology, slope, soil, stream transport index, topography, wetness index, stream power index, altitude, NDVI, and land use, land cover. These maps I will show in next slide. Study area is Sikkim Himalaya. My objective is to identify the most sensitive zone for landslide using remote sensing GIS in Sikkim Himalaya. The next slide. 13 thematic data layers are generated using different open source data with the help of the ArcGIS software for landslide susceptibility mapping. I have taken first is the figure is the rainfall, second is lithology, third is distance to fault, and fourth is distance to rivers, fifth is geomorphology, sixth is slope angle, seventh is soil, eight is stream transport index, ninth is topographic wetness index, 11th is stream power index, 12th is altitude, and 13 is NDVI, and 14 is land use, land cover. Next slide. Method. FR is one authentic method for mapping of landslide susceptibility zonation. In this method, there are three steps, such as calculating the ratio of the number of landslide occurs to the total number of landslide in the factor. Second is calculating the ratio of the factors class to the total area of the factor. Third is the FR. Each class was calculated for the landslide affecting factor are given below. FR is equal to A divided by B divided by C divided by D. The higher the value of FR, the stronger the correlation between the occurrence of landslide and affecting factors, and vice versa. After that, by using this method, the landslide susceptibility mapping is generated using ArcGIS software, and this map is classified into five classes shown in the figure. Very low, moderate, high, very high. The very high the percentage of the very high is 11%, and high is 15%, moderate is 25%, and low is 25%, and very low is 21%. The very high to high zone is located in the southern part of the Sikkim. The accuracy assessment of the study area is approximate 88%. Is done in the area under the curve AUC technique based on the FR model and landslide inventory location. The finding this research may be available in determining landslide prone areas. Thank you, sir.
So very nice. You are within the time. So can we move to the next speaker? Hello, I'm audible?
Yes, sir.
Okay. So we can call the next speaker, Sukhant Malakar, Active Seismic Zone and Earthquake Vulnerability Assessment in the Himalaya by Machine Learning and the Fuzzy MCDM approach. Yes, Sukanta?
Yes, sir.
Please.
I am Sukanta Malakar. I am a research scholar at IIT Kharagpur. I am working under the supervision of Professor Abhishek K. Rai. My top title of my work is Active Seismic Zone and Earthquake Vulnerability Assessment in the Himalaya by Machine Learning and Fuzzy MCDM approach. Next, please. Coming to the introduction part, the Himalayan zone is one of the seismotechnically active zone, comprising extending from the north to northeastern boundary of India, which includes the portion of China, Myanmar, Pakistan, Bangladesh, and comprising an area of approximately 10 lakh square kilometer area. The why it is important to study the earthquake vulnerability in this region, because as per the Apollo 2017, the population of this region is increasing by 3.305%, which is 3 times the population increase which can be seen globally. And with 2018, they have concluded that if a earthquake of magnitude equivalent to the earthquake occurred in the 1505 occur in India, occur in the Himalayan region, it may kill more than 6 lakh of people, and most affected region will be the Indian part will be the most affected region. So it is very much important to study the earthquake vulnerability in the Himalayan region. We have also seen that there are numerous earthquake occur in past, and some of them are the great earthquakes, which and one of the recent earthquake is the Gorkha earthquake, which occurred in the 2015, killing more than 10,000 people. So this is my study area. And next, please. Coming to the data and methodology for active seismic for the active seismic zone, I have taken the data from the USGS. Mostly the data which I have considered is the open source database, and data used are for the social and for the vulnerability mapping. I have taken all these parameters for the mapping of vulnerability, and these parameters is calculated using the fuzzy AHP technique. And after calculation of that, the final earthquake vulnerability map was created using fuzzy topsis method. And for the active seismic zone, I have taken the machine learning. I have used the machine learning technique which is hierarchical density based clustering method. Next, please. And this coming to the result part, we can see that for the vulnerability mapping, we can see that we have classified the vulnerability mapping into 5 classes, and we can see that for the deep green color is for very low vulnerability, and the for high vulnerability, the deep red color is for the high vulnerability. We can see that more than 50% of the Himalayan population are under the very high threat of earthquake vulnerability, but in contrast, only 13% of the landmass is under very high to high vulnerability. It is this can occur because of the migration of the people, because it's the harsh climatic condition. People are mostly migrating towards the metropolitan cities, so making the region more vulnerable. And if a major earthquake occur in this region, for example, the 2015 Gorkha earthquake, it killed more than 10,000. And if some earthquake occur in future in some metropolitan region, means if this epicenter is in some metropolitan city, it may kill more than lakhs of more. It may cause more casualty. So it is very much important to measure the earthquake vulnerability. And for in above figure, we can see that for the earthquake seismic zone, we have identified 12 cluster 12 cluster, and the aerial extent of the cluster appear larger in the Eastern Himalayan zone, Eastern Himalaya, those in the western part of the Himalaya. And these work, the vulnerability mapping has been validated using sensitivity, and we have done the sensitivity analysis to measure the criteria, understand the criteria. So next.
Okay, thank you. Yes, very good. We have to the next speaker, Kolipaka Venu, and his colleague Ram Raj Mathur. Application of cross-hole seismic technique
Sir,
and mass wall.
Sorry to interrupt, but the presentation from Kuripaka Venu hasn't been received, and they are actually not in the participant list as well. So we
Okay.
will.
So go to next. Okay.
Yes.
So next speaker is the Himanshu Paul. He's here. Characterization of the Dhauli Ganga flood Uttarakhand on 7th February 2021 using seismological data. Yes, Himanshu, you have 5 minutes to speak. So be concise. Yes. Any problem? Himanshu, yes. Yeah, you can speak.
Himanshu, your voice is not coming. I'm not sure what's happening.
Himanshu, you are muted. Yes.
So he doesn't seem to be muted, but his voice is not coming. I'm not sure what's happening. Himanshu, I would suggest you to disconnect and connect again. I don't know. Your voice is not coming.
Sir, can you hear me now?
Yeah, I can hear you now. Yes.
Yeah. Okay, thank you, sir. So I'll just start my presentation. Good afternoon to everyone. So I'm going to speak about the flood of the 7th February event. So we know two speakers has already spoke. So you can you do Control L, so it will come to full screen. Control L. Okay, Purnachandra Rao sir and Rajesh has already spoken about the rock slide that occurred on 7th February 2021. Can you go to the next slide? Yeah, so I'm going to focus on the flood that was generated by the rock slide. So you can see in the figure on the top right, you can see that the flood can be seen at different. So this is the snapshots taken from videos that were generated during the flood, and you can see our study which was published in Science. There we corroborated with satellite imagery and the timing of the video to find that the flood near Rainy Village. So in the top left, you can see the map of the stations, and there are two squares which are written, one as T, other as R. So T is Tapovan, R is Rainy Village. So Rainy Village, you can see that the flood occurred at Rainy Village at around 5:01 UTC. And we can also estimate that the flood reached Tapovan at around 5 hours 6 minutes UTC. Okay, so you can see the moment here. Okay, so if you look at the spectrogram, which is on the bottom left, you can see that at around 4 hours 52 minutes, you can see a large signature, so it corresponds to the length rock slide. And before that, we see a signature which is the earthquake, and then again at around 6 hours, we can see another earthquake. But right at around 5:15 hours, we can see a large signature. Okay, so what does this signature represent? We know that the rock slide occurred at around 4 hours 52 minutes, and the flood reached the Rainy Village and Tapovan at 5:15 6. So you can see in the spectrogram at around 5, 6, we can see the flood was here. But at 5:15, there is a large signature, which we initially we could not understand, but later on we realized that this is the signature of the flood when it reach the nearest station. So on the right bottom, you can see I have taken the seismogram and filtered it to frequency range. One is 0.1 to 1 hertz. On the top, you can see when we bandpass in a low frequency range, we can see the landslide and the 2 earthquakes, which is before and after the landslide, and around 5:15 hours, 5:15 hours, we do not see much signature. But when we take a high frequency range, 1 to 10 hertz, we can see that there is a large signal at around 5:15. So in our study, we found that this signature is due to the flood when it reaches the closest station, which is Auli, which is near to Joshimath. Okay, so so this means that the flood which is moving can be detected at different times. So this became the motivation for locating the flood. So can you go to the next slide? Yeah, so as you know, these landslide or debris flow signatures, they do not have this P wave or S wave kind of thing. So the traditional method of using arrival time seismology does not work with this thing. So instead, what recent studies have shown that the amplitude can be used to detect the location of these events. So here I have plotted some seven stations at the same. So the y-axis is same for everyone, and you can see this large signature is due to the rock slide that happened at 4:52, and you can see this rock slide amplitude is decreasing as the distance between the stations, distance of the station from the source is increasing. So this becomes a methodology in which by looking at the amplitude, we can locate the source. So we use this formula where AI is the amplitude at ith station, A0 is the source amplitude, and R is the distance. So using this equation, what we do is that we iteratively search for A0, because we do not know what is the source amplitude. So source amplitude here means that the amplitude if the station was at the source. So for example, if the flood is at one point and the station was right at that point, then what will be the amplitude? That is the source amplitude. So we don't know the source amplitude, we only know the amplitude at the station recorded, and we also don't know R. So there is a way we grid search for all these three parameters, and then from this we get the R, which gives me the location. And there are some consideration that I have to take into account. For example, I have to consider the site amplification. We can see that I have shown site amplification for 3 stations, and on the bottom figure, you can see the site amplification is amplified at different frequency range for different stations. So, and our range of interest is around 2 to 8 hertz. So we can see that the site amplification is occurring right at the same range. So we have to consider the site amplification and correct for the amplitude. And if even the correction not occur, we have to eliminate that station. And here you can see a gray band, and I have magnified this gray band on the right hand side, and you can see even when there is no amplitude, you can see in the original figure, you can see that there is still a difference in amplitude, and then this difference in amplitude can be used to locate the source. Go to next slide, please. Okay, so using that method, I have shown you at different times. So each of the map show you a time snap. So for example, the first figure is at 4:56 hours, and you can see that the red is the highest variance reduction. So I take 1 minus data minus feed by data. So
1 minute more, Himanshu.
Yes, sir. One slide more, sir. So using this methodology, I have shown you that at different times, the flood can be located at different points. And you can see at around 5:20 or 5:15, the flood is closest to the Auli station. That's why we saw a large amplitude at the Auli station. Next slide, please. Okay, so once we know the location of the flood, we can also look at the water level. So this is an empirical equation given by Gimbert et al. This is the amplitude spectra. On the top, you can see 3 different colors. This amplitude spectra depends on the distance of the station, the river width, the seismic velocity, everything. But I am only showing for different distance from the station. So if the flood is at different station from the station, then we can have different spectra. Now we fit this different spectra. So on the right, on the left, you can see this green. Green is the observed and black is the synthetic spectra. And we match the spectra after every 2 minutes, and we keep constant everything. So the river width is, we know, the river distance we know, the seismic parameters we know. We just vary the water level. And in the bottom, you can see this figure, which shows you the water level at different times for the station Auli. So you can see at around 520 or 518 or around that, there is a rise in the water level. And taking this synthetic, we also generate the spectrogram. This is the observed and the synthetic spectrogram. And from this spectrogram, we can say that the water level rise to 18 meter near the Auli station. The flood gauge data also shows 15 meters. So this results is very well corroborated with flood gauge results. Next slide, please. So thank you for listening. If you have any questions, I'll take it at the end.
Yes. It's very good presentation. Can we go for the next presentation by Shikha Vasisht? She's going to present Shikha Vasisht and her group, implication of site conditions on vibrant ground shaking in the far field regions of 2017 Rudraprayag earthquake. Yes, Shikha?
Hello, sir. Am I audible?
Yeah. Please go ahead.
So can you please show my slide? Good afternoon, everyone. Myself, Shikha Vasisht. I'm working as a research fellow at National Center for Seismology, Ministry of Earth Sciences. Today, topic of my presentation is implication of site conditions on vibrant ground shaking in the far field regions of 2017 magnitude 5.5 Rudraprayag earthquake. The Rudraprayag earthquake was occurred on 6th February 2017 in the Himalayan arc segment. Rudraprayag earthquake was occurred in a region that falls in and around the zone of moderate magnitude earthquake that occur all along the Himalayas within a 50-kilometer zone between MBT and MCT. The zone is called as Main Himalayan Seismic Belt. The focal depth of this earthquake is around 19 kilometers. As I have told you that this earthquakes fall in a region where moderate earthquakes has occurred generally, this earthquake has drawn my attention because it's a moderate earthquake, but still shaking was felt in the far field regions, including national capital, New Delhi. To understand its nature, this study was carried out by us. 15 seismic stations were used in this study. To understand the nature of the site, basically the site characteristics, HYV ratio method was performed. Based on predominant frequency, sites are characterized at hard site and soft site. Low frequency peaks are associated with soft soil and high frequency HYV peaks are associated with hard site. As you can see here, Meerut, Bahraich and Assor's predominant frequency lies on lower side, so they are termed as soft sides. And Lohaghat, Sohna and Lohaghat, Delhi and Ajmer predominant frequency lies on the higher side, therefore they are termed as hard side. So can we move to next slide, please? To find out the amplification factor at different sites, we have also applied site to reference method on all stations. In this method, we took one hard site as a reference site, which we have used NDI and New Delhi in our case, and response spectra at each site was calculated. After that, response spectra of each site is divided by response spectra of our hard site, that is NDI, and these curves are obtained. Here, orange curve indicates the north-south component of our data and blue curve indicates east-west component of our data. As you can see, amplification is seen at our soft side, that is Meerut, Bahraich and Assor. And in case of hard site, nearly flat response is seen around one, that are Sohna, Ajmer and Lohaghat. From the results of 15 sites, we have concluded that amplification factor soft site is approximately 2.2 times higher than that of the hard site. So can we move to next slide, please? To validate my results, I have also calculated 1D velocity model at all the sites, and it has been observed that Asora and Bahraich shows that their soft site at low velocity is observed at few meters of thickness, and in case of hard rock, high velocity as seen at few meters of thickness, as we can see in case of Lohaghat and Ajmer. So, can you move to next slide, please? I have also plotted PGA with epicentral distance. A decay pattern was observed, and this equation is found, that is y is equals to 332.152 x to the power minus 1.88. It's a power equation. It shows the decay pattern of PGA with respect to epicentral distance. From my study, I want to conclude that the analysis of ground motion data recorded at 15 sites reveals that soft site, namely Meerut, Bahraich, and Asora, located in the far field region, shows average ground amplification 2.2 times higher than that of the hard site. The 1D velocity model at each site using seismic background noise data found in conformity with the results from response spectra obtained using HYV analysis and site to response reference approach. I have also made an effort and obtained PGA at recording sites in the far field superimposed over available GMPs for the Himalayan region. However, they are found poorly correlated. Interestingly, I have found that the result shows a good correspondence with the GMP developed for Japan region. Thank you.
Okay. So it's all right. Thank you very much for your good presentation. Can you go to the next? Saurabh Barua, surface rupture of the 1897 earthquake in Chandrang Valley. Yes, Saurabh?
Yes, I'm there. Please load my presentation. Yeah, thank you, Dr. O.P. Misra. The topic I have covered, that is surface rupture of 1897 earthquake in Sidrang Valley, Shillong Plateau. As we all know, if you happen to see this figure, 12 June 1897, that particular earthquake occurred, which is of magnitude 8.1. And if you happen to see, this has produced more than 1G kind of acceleration. And subsequently, the isoseismal map shows that it has felt up to Madhya Pradesh and of course in China and some other parts around the continent. And if you happen to see the tectonics in this part, there is a pop-up tectonic as said, as established, and there is a collision. And this collision between the continental crust and the sedimentary rocks in the Surma Basin, that is the cause of the because. And subsequently, it is said that the causative fault is Oldham fault. But the interesting part is that Oldham fault is of length around 100 kilometer, 100 plus kilometer. But there is no remnant on the surface of this particular fault. So we try to revisit through this study, is there any surface rupture still available due to 1897 earthquake? That way, first approach was to see the seismicity map of that particular region. And seismicity map is sporadic and it is just intense, but no conclusion can be made that it is following a certain kind of fault line or so. And subsequently, we have also tried to see the stress pattern. Stress pattern is oriented towards the northeastern part of towards orientation. And that way, not much conclusive effort could be established. And if we want to see the focal mechanism solution, and the entire region cannot be constrained under a typical particular type of focal mechanism solutions. So in that regard, what we do, we jumped over to the geophysical studies, then fluvial geomorphological studies, and of course, then subsequently validation through geomorphological studies. So next slide, please. If we happen to see the Sidrang Valley, this is the Krishna River, and this is the Sidrang River. And this Sidrang, this is also aligned to the Sidrang fault. And it is said that after 1897 earthquake, this particular fault has been developed. And here, if you like to see, this is the Mara Krishna, that is the dead river of Krishna River, which has now shifted to this alignment. So we have carried out our geophysical studies through MSW and resistivity survey, and of course, total station topography survey. In these profiles, this is number 1 profile, number 2 profile, and number 3 profile. And if you happen to see, this is the MSW survey, and we have estimated the shear wave velocity profile, and these are the subsequent shear wave velocity profile along those 3 profiles. Now, interestingly, besides MSW survey, we have also have the resistivity survey simultaneously, and that as a result of inversion, we could establish the resistivity and subsequent the velocity pattern in that particular profile. And that way, we tried to validate the MSW shear wave velocity profile and also the velocity estimated from the resistivity survey. And subsequently, to validate more these results, we visited with the geomorphological studies whether any remnant of 1897 earthquake or Oldham fault still exists. We had the geomorphological studies, and we happened to see some kind of scarps, sagging pond, and of course a fault line, maybe a fault line we call, because it is not still validated by the active tectonic geomorphology. So these are some of the features that we have established over the last field work. And very interestingly, we also tried to see at 1964, 1991, and 2014, the fluvial geomorphology. Next slide, please. Next slide, please. Yeah. Through fluvial geomorphology, we during those periods, 1964, 1991, and 2014, we saw the Krishna River channel migration as well as the Sidrang River channel migration. Still, it is migrating at a very high rate, and this rate exclusively establishes that the region is tectonically very much active. But again, when we come back to the 1897 earthquake, what these profiles shows, profile 1 and profile 2 and the profile 3. These are the subsurface strata, which has been disturbed, or rather I'll say uplifted by the during 1897 earthquake by an amount of 5 meter plus minus 1 meter to that extent. And as a result of these, we again wanted to validate why these, there should be some remnant, in the sense there should be the establishment of terraces or indication of terraces. So we had the topographical survey, and we could establish 3 different terraces in the region. And these terraces are established in dead Krishna River channel. And these are some of the photographs. And yes, I have just concluded. So the channel migrations said the region is very much intensely active so far tectonic is concerned, and the subsurface strata is really disturbed. So what are the highlights of this particular study? That district westward river evolution after 1897 Shillong Plateau is very much active, and the topographic mapping of riverbed terraces indicate that there is a tectonic influence on rivers with the 3 different terraces. And of course, there is a maximum uplift from MSW and ERT survey by 5 plus minus 1 meter. So in a nutshell, that we couldn't see any remnant of Oldham fault, but still there is a lot of subsurface strata deformation available in Sidrang Valley and its vicinity. Thank you so much. So I conclude here.
Thank you very much, Saurav. Now we have the last presentation of this session. That is the Dr. Himanshu Mittal, role of the side effects. in earthquake early warning shaping determination. So Himanshu,
Yeah, good afternoon, sir.
good afternoon.
Good afternoon, everyone. Can I have my slides, please?
Yeah, go ahead.
Yeah, good afternoon, everyone. I'll be speaking about the role of site effects in earthquake early warning algorithm for magnitude and shaking determination. Next slide, please. Actually, earthquake early warning is a process of issuing where we can issue a kind of warning that may be of seconds warning before the arrival of strong shaking. Unlike other warning system, the warning system in earthquake early warning that may be only for seconds, but even that seconds of warning that can be helpful in saving the life, and that may be the to save property damage as well. Basically, there are two kind of earthquake early warning system. One is regional earthquake early warning system, and another one is on-site earthquake early warning system. In regional earthquake early warning system, basically we are using we are estimating its magnitude and its location, and using ground motion prediction equations or maybe some other methods. We are estimating the shaking at the further distances, and then we are issuing kind of warning. But in case of on-site earthquake early warning, we don't have that much time, because in on-site warning we are dealing with the data from a single instrument. So in that case, we are using data from that particular single instrument only. We are using few seconds, and then we are estimating some parameter, and then we are correlating it empirically with magnitude. So based on those parameters, magnitude is being estimated. So some of the parameters used are like PD, tau C, and PGA. Tau C, that's average time period parameter from initial few seconds after the arrival of P waves. Same way, that may be PD, that's maximum amplitude of the vertical displacement, and then PG, of course, everyone knows. And this on-site earthquake early warning system that's being operational in many countries, including Taiwan, Japan, Romania, and India as well. India actually has taken the methodology from Taiwan, so definitely they are working with their methodology, and it's based on PD and PGA. So in this case, we have tried to study the effect of site effects on PGA and PD estimation using the few second time window after the arrival of P event. And for that, we have downloaded the ground motion data from Japan network, from their KNet as well as KickNet network. Initially, 125 earthquakes were downloaded from 1996 to 2016, but later on, 50 earthquake has been used, lying between the magnitude range 5.3 and 7.3, and those are having depth 0 to 50 kilometers only. Can I next slide, please? Yeah, please. Yeah. So these are the results, like for using initial 3 seconds after the arrival of P wave. Left hand side, this is for rock site. Yeah, let me define. After downloading data, we have classified into 3 site classes. We are saying class A having VS30 more than 650 meter per second, class B VS30 between 350 to 650 meter per second, and then class C that have VS30 less than 350 meter per second. So first one, that's for rock site, or you make call it class A. So this is using 3 second window. Second one, that's for using class B, and last one is for class C. So you'll find like it's not much more different in 3 second window, because right now PD has not evolved completely. Next slide, please. Yeah, this is for 4 seconds. So here you'll find like PD, it's growing, and for rock sites, maybe it's not growing that much, whereas it's showing much scatter in case of class B and class C. Next slide. Same way, you'll find the same pattern in using 5 second window also, because for class A, not that much scatter, whereas for class B and class C, there is a lot of scatter. Next slide. By the time we reach 6 second window, you'll find the PD that has become kind of stable. Stable in the sense, I'm not saying it's not increasing beyond it. It's increasing, but not abruptly. So that means I'll say even for higher magnitude earthquakes, also 6 second window or maybe more than that, that can be used confidently for estimation of PD value, but again at the cost of losing warning time, because conventionally we are using 3 second window after the arrival of P wave. In case we are using 6 seconds, that means 3 seconds we are losing, and by that time strong shaking has already traveled 10 kilometers. That means 10 kilometer more blind zone that will increase if you are using 6 second time window. Next, please. And again, this is 7-second time window using regression coefficient. Next one. 8. This is using 8-second. Next two also, please. This is using 9-second. Next. And this is using 10-second. Next second. So I shouldn't say these conclusions, but these are the summary kind of things. So what we have found, like PD estimation may be affected by site effect, as we have seen, like in case of class B and class C site, like amplification is there toward the higher epicenter distances, but it's not quite obvious looking at those regression plots right now. I have shown here because the regression coefficient is not showing that much deviation from each other. Although higher PD values are observed close to epicenter distance in case of soil as well as rock site. I shouldn't say soil because right now I'm using here class A, B, and C. And as I already mentioned, PD values, those becomes constant after 6-second window. And initial 40 kilometer data, that's ideal for correlation for PD and magnitude. Again, one thing I will like to emphasize that I have not shown here, that it shows the difference when we use PGA value instead of PD. Next slide, please. Right now, as you must have found, we are not getting that much correlation coefficient here. So I'll be adding more data downloading from that website only, because till now we have used till 2016. So we'll be using from 2017 to 2020, and we'll be augmenting that data in this work. And more data also be used, because right now I have used only KNet network of Japan. So I'll be using more data from KNet also. So thank you.
So you have to use the more data of the India, of the National Center for Seismology. Okay.
Yeah, sure, sir.
So,
Sure.
So it's all right. I'm very happy that we concluded a total of the 9 presentation. I think one presentation we missed, and we have only the 20 minutes. So if you divide equally, then we have 2 minutes left for each speaker to answer. So now depends on the size of the question. If your question size is smaller, the speaker can give the answer in a smaller. So 2 questions or maybe more than 2 questions, depending on your quality of the questions. So please, now the first question is to Dr. Purnachandraoji. You can ask 2 questions from him, and answer must be very concise.
My presentation is 15 minutes now. So more questions are allowed.
Yeah, you have questions, of course, but in the giving the question distribution, you should be also equally treated. Okay, so please. Any question in the question box? Anybody can ask question. Maybe Rajesh, you can check in the chat if there is a question.
No questions in the chat.
No questions in the chat, sir.
So everybody afraid from Dr. Purnachandra Rao. He has already got the earthquake and landslide. So it's good. I have one query, Purnachandra Rao. It is not a question. Of course, when the landslide happened, when the breaking of the chunk of the ice had taken place, it is falling on the land, and then the movement started to take place. Then we are getting the signal in seismograph. Why you are telling early warning? The process has already initiated, and the havoc has already happened. So during the flow, the flow of the debris, flow of the water and the ice and all the things happening, then we are taking a certain schedule, right?
Yeah, well, actually, as you know, the velocity of seismic waves of the order of 11 per second. Whereas the velocity of flow of water is of the order of meters per second. So that means the seismic wave corresponding to the flood of the station will reach the seismic station much before the flood starts moving.
Sir, your voice is not clear, sir.
Voice is not clear at all.
There is a problem with your speaker and mic.
There is some issue with the voice.
Hello. Yeah.
Yeah.
Is it audible?
Yeah, now it is clear. There was some issue with the voice.
Yeah. So as I was saying, Mishra Sahab, as you know, the seismic velocities are much higher than the velocity of the flood flow. So the seismic signals can reach the stations within few minutes. So even before the flood arrives at a certain point, the record of the flood initiation or the debris flow is already recorded in our instruments. So if you have a automatic system, a warning system which is based on an automated software which recognizes the flood initiation, then it is possible to give a warning. Of course, all this is through VSAT. Before the flood arrival, it is possible to give the warning. So the concept is only because seismic waves are much faster.
Yeah, okay. So, Mr. Rajesh?
Yeah, sir,
Yes.
can you, maybe,
please.
one more thing I would like to discuss with Rao, sir. I think this is the precise reason we call it early warning system, actually. We don't call it forecasting. Because
Yes, you're right.
We call it early warning system. And I would like to
forecasting is before the event occurs.
Before the event. This is the early warning. So after the event,
Yeah,
right, sir? Yes. So
Yes,
volcanic eruption part, actually, I would like to discuss with you in more detail because we are also using seismic
So
data.
you can write a mail to him because time
Yes,
is
yes.
short, isn't it?
Yeah, I'll discuss.
And he's
with you
expert, he
later.
can give the answer.
Who is the, sorry, who asked the question now?
Mala, I think.
Mala here, sir.
Oh, Mala. Okay, fine.
I recognize her voice, that's why I guess it is Mala.
I think, Chairman, you should insist that people should come on video so that we know who is speaking.
Yeah. Please come on that. I have early warning of the voice, so I can detect the person.
Okay, fine.
Early warning.
So you can have now. I think one question to Rajesh. It is also related to the same event. What the Rao has given a very brief on science paper.
Yes, sir.
Rajesh,
I'm ready to. Yes, sir.
Any
They can
questions
ask.
to Rajesh? No questions? Rajesh, I have one query to you. You have given the 1 hertz to 10 hertz. That is
Yes,
also
sir.
the earthquake signal zone. When the
Yes, sir.
earthquake happened, it is also 1 hertz to 10 hertz.
Yes,
So
sir.
how could you segregate the earthquake signal from this noisy type of the thumping signal?
Actually, we have seen a particular pattern in the spectrum, sir. Like earthquake signals, they don't span over a longer period time. Like although it has the high frequency energy, it will not span over a longer time. Like it will the landslide and debris flow signal. These signals will span over few minutes even, sir. But like earthquake signals, they won't span over that time. As well as the second fundamental thing we have seen in the spectrum, like the energy distribution from the high frequency to low frequency. In earthquake kind of thing, the energy will increase from high frequency toward the low frequency. As well as in the landslide kind of thing, the energy is in the reverse pattern, sir. If you can observe the spectrogram, so at the high frequency, energy is lower. At the low frequency, energy is lower. At the high frequency, energy is higher, sir. That's the crucial differences we have seen so far.
Yeah, of course, it also depends that where the earthquake source is. So
yes,
it can
sir, that also depends.
It can also
yes,
behave
sir.
in that way. So it can also sometimes confuse. Anyway, so you have to have a robust control on isolating the signals
Yes,
from
sir.
the natural and the after the effect of the natural disasters like thumping and all these slides.
Yes,
It's
sir.
all right. So next question, I think Irjes is here. No? Irjes, I think Mala is going to. Mala, in any question to Mala? GPS measurement of tsunamigenic ionospheric perturbations. She has given a very good thought-provoking idea. So, any questions?
I just want to know if Chairman permits from Madam Mala that how much before you can get the early warning?
Sir, that is a precise thing which we are going to publish in our next publication. Actually, this particular Sumatra event, it was around 90 minutes before the event, and it depends on the distance, how far the site is located, the coast area is located. So we have calculated the distance and time. So that publication will say that how much time at what distance is early warning is useful actually.
She is not going to disclose you her result. Okay.
I
Yes.
have one question, sir.
You are indicating the some magnitude also?
No, not so far. not so
No,
much. Only
tsunami-genic means you want to indicate about some magnitude, that how much, what should be the minimum magnitude which you are going to give early warning to.
yeah, you are talking about the height of the tsunami, right, sir?
No, not height, not height. I am saying that you are saying that tsunami-genic ionospheric perturbations, na?
Yes, sir.
So means those such ionospheric perturbations which are capable of giving tsunamis, giving rise to tsunamis.
Yeah,
So what
threshold.
should be the minimum?
Yeah, threshold.
Yeah,
Yes.
minimum threshold. That's what
Yeah,
you want.
for that, I think we will collect the statistics and we'll try to answer that part, sir. That,
I think Professor Walia, she cleverly put not earthquake, she cleverly put like a tsunami-genic ionospheric perturbation. So you cannot ask the magnitude. In that case, she knew where put the earthquake. Okay. So she
That's
wants
right.
that ionospheric interactions.
no, we have a study with earthquake also, sir, actually, and then we
It's
are
all right.
trying to
It's all
correlate
right.
magnitude.
I understand that you asking that the actually the perturbation level of the ionospheric and these lithospheric interactions, how it was the bigger to generate the tsunami. Professor Walia asking in the terms of the magnitude. Anyway, that interactions, we'll love to see your paper. Okay.
Sure.
Thank you.
Thank you.
So I think Irjes was absent. Really?
No, he has presented. He has presented.
He presented? Irjes.
Yeah.
Okay. Sorry. I think Sukanta is not there. Na? Sukanta is also there. So Irjes, any question to Irjes? You can open your video, Irjes.
No, sir.
No question? Okay.
No, which topic was that? If you want to ask questions,
Irjes
we
was
should
remote sensing and GIS based landslides.
Susceptibility
mapping.
mapping.
Okay. Iswa. Okay. So next we can move to the next speaker, Sukanta Malakar. Active seismic zone and earthquake vulnerability assessment in the Himalaya by machine learning and fuzzy MCTM technique. You can open your video so that everybody can see, Sukanta.
Sir, I don't have webcam, sir.
Okay, no problem. So you ask a question. Anybody? We have a good listener. I think 70. I'm not getting a question from audience.
Yeah.
I'm very happy that this session is very fruitful. So I think you asked some good questions from the speakers. I have given you time. No question. So Sukant, tell me, what was the limitation of machine learning in geosciences?
Sir, actually in machine learning, you need lots of data set.
Okay.
That's the main problem in machine learning technique. Otherwise, it will give you very uncertainty and it will give you very much error if you use very limited data set.
But there should be a threshold limit that so much data is needed about the grid pattern. And if you have some threshold value for that, suppose you have given you area of the in geosciences 100 kilometer by 100 kilometer of the grid spacing of 25 kilometer of each. Okay. So if I will give you the 100 by 100 square kilometer means, and it was divided into 25 kilometer grid, is it sufficient to analyze those data of the
Sir, if you give me area, it depends on the data set. Means if you are planning to find magnitude, for example, if in some work people are finding the magnitude of the earthquake. So for magnitude of the earthquake, they are required the fault data set. So they require large amount of data set for that purpose.
And I wanted to know that your confidence level is minimum how much? Maximum there is no limit. So minimum
no, maximum is the confidence level is minimum according to as per my analysis 90% accurate.
Okay. Okay, right. So next step is the Kolipaka Venu.
No, sir, they were absent.
He was absent. I think I confused this Sukant name. Okay. So now the next speaker, I think Himanshu Paul. He has given a good presentation. Himanshu, have any question on the 7th February? It is going to be, this is 1 year. So maybe Purnachandra Rao is going to celebrate the anniversary of that disaster events with new findings. Okay, so 7th February, I think Himanshu Paul has any question? Himanshu has no
considering
question.
topic to be new,
Topic
there are
is the
less
yes,
queries.
characterization of the Dhauli Ganga, the flood, Uttarakhand, 7 February 2021, using seismological data. It is very good topic. Of course, it has a very good publication. So, okay, no questions. If you have questions, if you remember, then you can write a mail to a speaker. Can I come to Shikha Vasisht? She has given a good presentation how she can link to the site a specific seismic characterization. So one question from her, only one question.
Yeah, in Shikha's presentation, I think the PGA plot, what she was trying to show, there this site response effect was not seen, right? PGA and distance in that. So maybe we can try to look into it in more detail.
Yeah,
the site response effect, right, in the PGA, because it is show the regular pattern.
Yeah, ma'am, it show a decay pattern.
Yes, regular pattern. So that
Yeah.
site response thing was not clear, right, in that one.
Yes, ma'am.
Yes, so we can try to look into it more detail. Okay.
Yeah, thank you for the suggestion, ma'am. I'll work on it.
Take the suggestion and deal with it in your paper. Okay.
Yes, sir. Yes, sir.
Questions to Saurabh Barua. He has worked on Great Earthquake 1897. Any question? I think Walia Saab has question on it, or maybe
Yeah,
Purchandra
I have-
has a lot of work on it there. He can have one question.
Yeah, I have a question to Saurabh Barua. So hi Saurabh. Meeting
Yes,
after a long
I'm
time.
fine. Hello, yeah. Please,
Open your video. I did not see you for a long time. So show your face.
yeah. Okay, 1 minute, please. Yes.
Keep asking question, Purna.
Yeah, oh, he's looking very different. So Saurabh,
Nice to see you.
congratulations, very nice work. My question is twofold. Firstly, whatever geomorphological studies that you have carried out, I mean, how do you correlate that the deformation what you have seen? It must be correlated with the 1897 earthquake. What is the how can you say with confidence?
Yes, the very reason is we have also carried out over the past few publications on paleoseismological studies. And those paleoseismological database and our geomorphological, fluvial geomorphology, as well as the subsurface velocity modeling, all these integrate, when integrated, I mean, it comes closer to the same conclusion, with obviously very less kind of minimal error, you can say. So in that regard, that geomorphological trend, what is the fault line you have seen, there we haven't worked anything that is yet to be touched upon, but the identification of fault line, almost it is almost more than 30 kilometers we have traversed, and that is still lied untouched so far paleoseismological studies is confirmed. So this is the way that there is a plenty of scopes, I think, for our researchers to go to the field and identify those locations. We have the latitude, longitudes, and it is of course a rough terrain, but still there is a scope for paleoseismological studies to be more confident that these subsurface strata and the fault length, what we have seen, that is pertinent to 1897 earthquake.
And Maswa also shows some deformation.
Yes, yes. From Maswa and resistivity, we have established this particular deformation, and which is around 5 meters.
All right. Okay.
Thank you. Thank you for your question.
Saurabh, why did you put its magnitude 8.1? The history says it is 8.7. What was actually the putting the magnitude of the 1897 earthquake 8.1?
Yeah, there is a reason behind, because when we look forward to the seismic moment magnitude, it comes around equivalent to 8.1. And that is why it is taken as MW 8.1.
So
but the rest are other estimations.
No,
Yes.
no, any magnitude you can do, there is no much drastic variations on these. You look into that, I don't know, because in that time there was no instrumentation era. So it could be the intensity, maximum intensity, what they have been measured. And a lot of the macro earthquake survey has been conducted. And maximum intensity, the empirical formula, they derived it. So even if you look into that, this is just a query to put you. If entire world is 8.7, they are telling 8.1 is too undermined, I guess, because on this issue. Okay, thank you very much, Saurabh. It was very nice.
Thank you. Thank you.
presentation.
Nice to see you all
So,
after long
yeah.
intervals. Thank you.
So I have the last the speaker, that is Himanshu Mittal. He has given a way out for the earthquake early warning. What he used on the KickNet or HiNet data. Now he is in the National Center for Seismology. So you can see that first he tried to test the KickNet and HiNet, then he will go into the NCS national network. Okay. So you can have any questions. I think Abhay can ask a questions on earthquake early warning. Or any speaker if he wants to. Yeah.
Yeah, please, sir.
Dr. PC.
Please.
Yeah, I have a question to Himanshu Mittal. Anyway,
sure.
firstly, congratulations, Dr. Mishra. I see a lot of young people from NCS are actively participating. A very good sign for me. So, Himanshu, I want to know that you are talking about correctness of magnitude estimation in an early warning system. But I'm wondering that if you do site correction in your amplitude, your magnitude determination, means if you take care of the site effect while estimating the magnitude, then I think there should not be any problem, no?
So that's what I'm trying to study, sir. How much effect those sites are going to make on magnitude estimation? Because generally we are correlating either PD with magnitude, that means maximum amplitude of vertical displacement, or that may be tau c, that may be average time parameter, that using a few second window after arrival of P wave. So that way correlation is already established. So I'm trying to look like if I'm classifying that in different site classes, how much site effects going to affect that PD determination and using different time windows.
Yeah, I think that's very important. Otherwise, magnitude will be overestimated.
Yeah, definitely, sir. Otherwise, even PD is also overestimated in some cases, and even for lower magnitude, PD is underestimated, or it may give wrong alarms because of low frequency noise. In that case of lower magnitude earthquakes.
Yeah. Okay. Good luck.
Okay, thank you. I think Abhay is monitoring us. We are on time. Taken only 1 minute more. Because this may be taken as a
I
cyber.
have, Dr. Mishra, I have a query for Himanshu Mittal.
Yeah, please.
Yeah, please.
Saurav here.
Please. Yeah.
So, Dr. Mittal, it was really a nice presentation from your side.
Thank you.
And this, once you visited CSIR NIST to Jorhat to look after the EEW system in northeastern region of India. If you can, I mean, it's a request from Northeast Institute of Science and Technology, Jorhat, that if you can pursue your EEW system in northeastern region of India, that would be a fantastic additional effort from your side. All the best. Thank you so much.
Thank you, sir. Thank you. Definitely NCS will be doing its best efforts for everything.
Thank you so much.
Yes, Saurabh, off the record, I asked you to come to the national network with your all seismographs to make it more stronger, more denser. Okay.
We'll be glad to associate with you.
Because we are going to make a consortium of the network to open up the data to each and every researcher, each and every academic and research institution to make it a big job for the nation.
We'll be glad, surely.
Thank you very much.
That will be great. That will be great.
Yeah.
Thank you, sir. Thank you very much. I'm very happy. So I can stop here.
Thank you all.
Walia ji, thank you very much.
Yeah, thank you, Dr. O.P. Mishra, for nicely conducting the session. And it is there towards that last part, some gossip. So 1 minute it has taken extra. It's okay. I would like to request or ask Dr. Mala, if you want to say something, say a few words about the session.
Yeah, thank you, sir. I think the session went off very well, and we could see excellent presentations on the application of seismic monitoring. It's a completely different approach to look into the seismic data, actually. So that was a couple of presentations were excellent, and then the use of machine learning language to identify the active seismic fault, which is the need of an hour, I think. So that work should be really pushed ahead for that one. And of course, the site effects, the youngsters were presenting site effect on ground shaking and early warning system. That is also one of the new things, especially earthquake early warning system. So overall, the discussions and presentations were very good and well in time. So thank you all the speaker and thank you organizing committee for this opportunity. Yes, over to you, sir.
Yeah, thank you, Dr. Mala. We have got the rapporteur of the session. Dr. Rajesh, would you like to add up a few words?
Yes, sir. All over it went very successful, with a few discussions on early warning as well as artificial intelligence applications and all together. This is the need of the hour, like we can say, hazard monitoring and early warning, which is the need of the hour. So overall, it is a successful one. That's all.
Yeah, we request you to prepare a short report and submit.
Sure, sir. I have made I have noted them.
Yeah.
So
Dear participants, we are very happy to conclude this session. You know that environmental seismology is one of the upcoming field, and who other than Dr. Purnachandra Rao, he made presentation for you all, and the session was chaired by Dr. O.P. Mishra. So we are very much grateful to all the presenters and the chairman, co-chairman, and the rapporteur, special invitee, Dr. Purnachandra Rao ji, to be there with us. And thank you. We can wind up this session now.
Thank you. Thank you very much.
So yeah, there are some queries. There can be cross interaction anytime. You all know all the faces are known, and there can be some more questions, and there can be more solutions to them. Now we are going to enter into the very important phase of today's presentation. That's what is the poster presentations. Dear participants, we can have oral presentations very successfully, very smoothly, but poster presentations is very, very difficult. You also must be thinking that how to discuss your research in such a short period of time over virtual platform. But none other than Dr. O.P. Mishra is going to chair. Just 1 second. I was supposed to turn the page. Dr. Uma Shankar is going to chair this session, and Dr. Tanvi Arora is going to be there to help him as a co-chair. And we have got rapporteur Abhishek ji is there. So you know that it is very, very tight session. Time is limited. So without taking much time, there are 12 poster presentations are there. Just wait 1 second. I need to ask from the organizers. Organizers, what is the system for poster? You will make or they will come by themselves? Acha, all right. Acha. Yeah. So yeah. So without again coming in between, time is running already. At our place, sunset is already there. So with time, there may be much more cold, and it may be difficult for you also may get some cold from here. So the important thing is that out of 12 poster presentation, 2 poster presentations are not uploaded. So 10 poster presentations are there. Professor Uma Shankar, you may take on from here, and the presentations will be displayed as usual, like the oral presentation by our team here, and the person's name, whatever you will take, that person will come and say something. If he is not coming, the slides will be played and it will be over. So over to you, Professor Uma Shankar, for this first time experiment of poster presentation on virtual mode. Yeah, please.
Thank you, sir. Thank you, Alia sir. Good afternoon, all. Rao sahab, namaskar. Bansal sahab and Rai sahab is also looking there in insect. That Sukanto Rai sahab. Namaskar, sir. So welcome you all in this 4th session, poster presentation. There are 12 poster presentation are there. With me, there is Dr. Tanvi Arora is there. So after this, maybe she will take over. So in this one, as you see from the technical program, you have given 2 minutes time to present your just in a brief work what you have done in your these topics. So straightforward, I come to the first this presenter, that is Karthikeyan is there.
Yes, sir, I am here.
Yeah, please go ahead and finish within time, please.
Okay, sir. Sure. First of all, good evening to everyone. I'm thankful to give me an opportunity for presenting here. My study is signature of co-seismic ionospheric TEC disturbances associated with magnitude of 7.6 Peru region during the doublet earthquake. In this, I like to say that various sources induces the ionospheric variability from above and below, and from below there is a earthquake, cyclones, and many things are concentrating on the ionospheric region. So, in my study, I got get to the hello.
Yes, please go ahead.
Here we study the co-seismic ionospheric perturbation during the Peru earthquake of magnitude 7.6 at 20 to 45 UT and 20 to 50 UT, which occurred consecutively within the period of 5 minutes. Here the earthquake occurred at 600 kilometer depth with the normal fault, and seismo-ionospheric disturbances associated with the earthquake is studied using the GPS station, TEC utilized using the GPS stations, and the regions are classified as region 1 and region 2 in the methodology section. Sir. In the region 1 and region 2, which is north to the epicenter and south to the epicenter, I had separated the two regions. And to, in the region 1, I had utilized the different satellites of PRN 14, 18, and 21, 22. And for region 2, PRN 18, 20, and 29 are utilized during the time period of 22.5 to 23.5 UT. That is from 10:30 UT to 11:30 UT. And during that time, I had observed the perturbations over the stations of POVE and SCRZ in the region 2, which has the dominant variations during the earthquake time of around 1 TECU variations, which is not seen in other studies. That is the first thing I had to report in my study. And another thing is that in the region 1, which is north to the epicenter, does not seem much variations because it is far away from the epicenter. Also has the variations of 0.05 TECU for the stations CONE, IBEC, and MZEC. That are the stations which is in the region 1 having the very least variations observed, and in the region 2, the two stations POE and SCRZ are having the more variations, and it is observed the N-type variations like compression and rarefaction type waves like it observed. And to confirm the earthquake-induced signature is seen in the ionosphere, I had utilized the Marlet-Wavelet analysis technique, which is from which I can able to say that the gravity waves which propagates during the wave energy which released during the earthquake can able to reach the ionosphere, which is having the dominant frequency of 3.6, 3.8 millihertz and 4.16 millihertz, which is falls in the region of infrasonic frequency range, because the waves which is having more long period infrasound waves with periods of more than 10 seconds only can reach the ionosphere. The previous studies reported. So from that, I can conclude that the seismo-ionospheric perturbations during the earthquake caused by the acoustic gravity waves.
Thank you very much for your quick presentation.
Thank you.
So we have to move to next presenter as Mannat Khanna. Is there?
Yes, sir.
Yeah, please go ahead.
Thank you, sir. I'm waiting for the screen to start presenting.
Yeah, please display her presentation, please.
Yes, sir. 1 second. By the way, I would just request the presenters to means I will be zooming into the slide to the best of my understanding where you are talking about. But if you want me to move, you just let me know and I will move the slide to the correct place. Okay.
Yes, thank you. So in our study, we have estimated the site response at different strong motion stations in Northeast India using the horizontal to vertical spectral ratio technique on earthquake data. So we know that the damage caused by an earthquake at a particular site is also dependent on the local geology, including the hardness and thickness of the sedimentary layer above the bedrock. Hence, we have estimated the site response in the form of site amplification levels and the associated predominant frequencies at different sites using the HVSR technique, which may be used by with micro tremors or earthquake waveforms. For our study, we have used earthquake waveforms. So the benefit of this technique is that a reference station is not required due to an assumption that the vertical component of ground motion is not affected by the sedimentary layer. The amplification level can be directly computed by the horizontal to vertical spectral ratio at the surface for one side. So can you bring it to the lower portion? So the figure on the left is our study area, and therein lie the recording stations and the earthquake epicenters as well. So after evaluating the spectra of the three components of the main earthquake events, we have smoothened the data, and we have represented it in the form of these 11 plots for the 11 stations. So for the first 9 stations, we are getting higher amplification levels and of about 2.5 to 3.8, and the corresponding predominant frequencies are lower, varying from 0.6 to 2.5 hertz for these stations. So there's high amplification in the first 9 stations, and the last 2 stations at Karimganj and Nong Stoin have lower site amplifications of factors of about 2 with high predominant frequencies greater than 3 hertz for our site. So we have represented this analysis with these 2 contour maps depicting the spatial distribution of the predominant frequencies and the site amplifications respectively. So the stations, those 9 stations where we were getting the high amplifications are in the western, northern, and eastern part of our study area. This seems to be consistent with the local geology, as there are loose sediments in the thicker alluvium in these areas, and there's a drainage system of Brahmaputra and other rivers and their tributaries. So these are floodplains, and typically the sediments are looser, so the site amplifications are higher at these sites. And for our 2 stations where we got the lower amplifications, they were in the southern part of our study area at Karimganj and Nong Stoin. And this is hard rock sites with metamorphic rocks of the West Khasi Hills. So our results seem to be consistent with the local geology. The study can be expanded to include more sites, and it can be further expanded to estimate the thickness of the sediment layer, knowing the shear wave velocity model, or vice versa. So it can be useful for seismic hazard simulation at the surface, if you know the seismic hazard at the bedrock, and may also be useful for microzonation applications. So
Thank you very much, Manat. So move to next presentation. I would like to invite Priyanka Chauhan. Priyanka is there. Priyanka Chauhan, RBS Yadav, and Rajiv Kumar. Some of them is there. If I think Priyanka is not there. So we can move to next presentation, that is Indubala.
Sir, Priyanka is there, but she's not responding. I can see her in the list.
So Indubala is not there?
Yes, sir.
Indubala is there. Okay, we can go back to Priyanka later. Okay, Indubala.
Yes, sure.
Just 1 second, sir.
Can you zoom?
Yeah, it's visible.
Oh,
You can
okay.
go ahead.
Okay. Thank you. Good afternoon, all. I am Indubala. Today I am here to present my poster on the topic the Coda wave attenuation characteristics for the Kutch region, Gujarat, India. We all know that the area is seismically active, which is covered in Gujarat region, and attenuation, seismic attenuation. When an earthquake is occur, pent-up energy release this the energy while propagating. This energy release in the form of seismic waves. As the energy move, the amplitude of the seismic wave decrease with increasing distance from the referred to the attenuation. The attenuation is measured by the dimensionless quantity, which is known as Q, which is inverse to the attenuation. Here there are several studies have been done for the CODA Q estimation, study area and data. Here we use the total 75 velocity time history for 15 local earthquake which occurred during the 2011 year and recorded at 16 different stations. And this map showing the earthquake use earthquake and seismic station for the present study. The recorded data used in the study is part of seismic network station installed by the Institute of Seismological Research, Gandhinagar, Gujarat. Here the method uses single backscattered method. The method is based on the idea that CODA wave is a backscattered S wave, which is also say that tail of the seismogram generated by the random heterogeneity present in this earth crust and upper mantle. This method is proposed by the first Akki in 1969, and after that updated by Akki and Kaut in 1975. Present, which presents the detailed discussion of origin of CODA Q and property of CODA wave. Here is AFT is CODA wave amplitude, which is function of frequency and lapse time. A note is or source CODA source factor, and gamma is or geometrical spreading factor, which we take 1. This is attenuation factor E minus pi FT divided by QC. Here we simplify this equation and taking natural log both sides, and slope here slope gives the QC value.
Please conclude.
Okay. The velocity data have been filtered for different central frequency, which is 1.5, 3, 6, 12 and 20. Here in figure 2 we show the variation of log amplitude of CODA with lapse time window. The CODA wave amplitude start measuring the twice of the travel time of S wave. In figure 3, this is show the plot between CODA Q and frequency. Here we obtain the result CODA Q for different central frequency 1.79 to 94. As we showed from this result, the average, which is frequency, QC value is frequency dependent. As the frequency increase, CODA Q value is increased. The average frequency dependent relationship we get 123 into f raised to the power 0.96. This the study have been done for the Kutch region is Beta et al. Get the value 148 f raised to the power 1.01, and Mandal et al. 2004 had reported 102 f raised to the power 0.98, which is similar to.
Thank you, Indubala. Thank you very much.
Okay, thank you
for your good presentation. Now, Tanvi, you can take over, please.
Okay, sir. Thank you, sir. Actually, it was interesting to listen to them as well. So our next speaker is, it's Pia Diatherion. I'm not able to pronounce it.
Yes, ma'am. It's
Diatherion. Okay. Yeah, please have your poster presentation.
Yes, ma'am. Good evening, everyone. My name is Priyad. This poster presentation is on seismic hazard analysis using deterministic approach for Arunachal Pradesh. This Arunachal Pradesh state lies on northeastern state of India, and as we all know that northeastern region of India lies on seismic zone 5, so they are most prone to earthquake. So in this study, we have tried to assess the seismic hazard using deterministic approach for the state Arunachal Pradesh. This deterministic approach is straightforward. Sir, can you please scroll down to the methodology? Yes, these are the methodology that we have followed for the deterministic hazard assessment. First is collection of past earthquake data and preparation of homogeneous comprehensive catalog, and then identifying possible sources around the site and computing the minimum distance between the source and the site and computing the maximum possible magnitude. And after that, we compute the ground motion intensity, like peak ground acceleration, that is PZA value. And then finally, we get the hazard curve. This will be much clearer when we go to the figure. So the earthquake data are collected from the ISC website and from some published literature, and we make a homogeneous comprehensive catalog. And after which we have analyzed the data for magnitude of completeness and the data completeness with time. So for this magnitude of completeness, we get for magnitude 4.1. So 4.1 is the magnitude of completeness. And for the data completeness with time, as we can see from this table, small table, for a different range of magnitude, there are different interval of completeness. For example, for 3 to 4, it is 20 to 30 most recent years are complete. And after that, we analyze for the focal depth of future earthquakes. And it comes out that for our magnitude range 3 to 4 and 4 to 5, it is around 10 kilometer. And for the magnitude range greater than 6, it's around 15 kilometer. So we have analyzed the focal depth of the future earthquake as well. And then a seismotectonic map is prepared. This seismotectonic map, the blue shaded zone is the site, that is Arunachal Pradesh state. And the blue line shows the seismic sources. So after we have made this seismotectonic map, we compute the ground motion intensity, that is peak ground acceleration. In order to compute that peak ground acceleration, we use the logic tree approach using more than one ground motion prediction equation. This small figure on figure E is the logic tree structure. So for the site of interest, for hypocentral distance less than or equal to 300 kilometer, we use 3 GMPA. First one is Anbhajagan, second one is NDMA, and third one is Toro. And for hypocentral distance greater than 300 kilometer, we use that NDMA only. And with this logic tree approach, we have computed the peak ground acceleration. And finally, we create a hazard map that is in the results. So from this hazard map, we can see that the PZA value for the state is ranges from 0.27 to 0.79. So in conclusion, we can see from the map that the southern part of the Arunachal Pradesh are more vulnerable to seismic hazard analysis. So this is the work I have to present it. Thank you.
Okay, thank you, Retrion. So we can have the next speaker, next presenter, please. Mr. Rajiv Kumar.
Ma'am, I don't have the presentation for Mr.
Okay.
Rajiv.
Okay, so the next one, Rashid Shams.
Yes.
Yes.
Yeah, please.
Yes, I am here. Can I have my poster, please?
Yes, 1 second.
Yes, thank you. Good afternoon, everyone. I am going to present my poster titled 1D Nonlinear Seismic Ground Response Analysis for Various Locations in Dhanbad City, Jharkhand, India. In the study, we have carried out 1D Nonlinear Ground Response Site Response Analysis for various locations in Dhanbad City using standard penetration test data obtained from 11 boreholes spread all across the city, obtained from state and central level public works department and various other agencies. As you all know, Dhanbad is quite important urban agglomeration in the Jharkhand state, and it is also the second most populous city in Jharkhand and an important center of mining activities. It is also situated in the seismic zone 3 according to the IS 1893, which has Dhanbad city has also experienced low to moderate seismicity in the past. So it is important to study about the local soil condition, as we know that local soil condition can amplify the incoming seismic waves, and it is important to explore the effect of local site and local site deposits. So here 11 borehole SPT data has been used, where the VS profile, that is the shear wave velocity profiles, has been estimated using the 5 empirical relationships, and the final VS model has been adopted for each borehole after taking the average obtained from each empirical relation. Two major input bedrock ground motion has been adopted, that is Nepal Gorkha 2015 earthquake and the Imperial Valley 1979 earthquake has been adopted as the input bedrock motion, whereas the soil models such as Dobry 1991 and Sierra Idris 1981 has been adopted to define the shear modulus and the damping ratio. Deep soil software has been used to carry out the nonlinear time step integration, where the final results obtained were corresponding to the PG of the ground surface, the response spectra corresponding to the spectral acceleration curves, and the shear strain and shear stress ratio. As we can observe that the final results obtained on the basis of the PJ values for all the 11 boreholes show significant amplification at all 11 borehole sites corresponding to both Nepal and Imperial Valley earthquake from the deep soil software. All boreholes show some amplification, but some boreholes such as 6, 7, 8, and 11 show high ground acceleration amplification ratios and high ground level PGs, indicating the presence of soft and unconsolidated deposits near to the ground surface, and even the presence of some old patches of alluvial beneath the ground surface. The spectral acceleration curves obtained for all the borehole site and corresponding to the input ground motions, they also can be used for designing and development of earthquake resilient infrastructure and for the similar and adjacent region to the Dhanbad city. And finally, the result obtained from this analysis, these can be used prove useful for city planning and further developing the microzonation maps. Thank you.
Rashid, that was really very quick. But the next, thanks a lot. And the next presentation is also by you?
Yes.
Yeah, so can we have the poster, please?
Yes, ma'am, 1 minute.
Uma sir, we are missing the introduction of the speaker actually. So it's
yeah.
So it's going so fast that we are not able to identify and read also.
So I request the speakers to kindly switch on their video, please, when they are presenting, basically. So
or maybe at the end,
yeah, at the discussion we can let them introduce.
Okay,
well.
yeah, thank you. So Mr. Rashid, please.
Yes, ma'am.
Rashid, please, can you on your video, please?
Yes, sir.
Yeah. Yes.
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 Thank you. This poster I'm going to present is titled Seismic Analysis for Kishanganj, India using probabilistic approach. In this study, we have carried out the seismic analysis to produce the seismic bedrock level seismic maps for Kishanganj district, which is the easternmost district in Bihar, and it is also close to the Indo-Himalayan border. So it is quite close to the Indo-Himalayan thrust, and also some of the prominent faults, close to some of the prominent faults that have previously produced large earthquakes, such as Nepal 2015 earthquakes and Bihar, Nepal 1934 earthquake. So it was indispensable to carry out the seismic analysis to produce some kind of seismic map which can be used by local authorities for time planning and earthquake resilient infrastructure development. So in this study, we have developed a earthquake catalog consisting of data from past 300 years obtained from various agencies such as NCS, USGS, ISC, and some historical data from various published literature. The raw catalog was then processed, homogenized to more magnitude scale. Then it was declustered to remove all the dependent events, and finally we were left with 4411 main shocks. Then the seismic discontinuities in our study region that was surrounding Kishanganj, the study region that was considered was around 500 kilometers of radius surrounding the Kishanganj district. The seismic discontinuities that were falling in the study region were geo-referenced and identified using the SciSat atlas that is published by Geological Survey of India, Dasgupta et al. 2000, and the various attributes corresponding to those discontinuities, such as the maximum magnitude for each potential magnitude for each discontinuities, the length and the distance from our grid points and our study area of interest were identified. Then we selected the 4 GMPs based on the log likelihood efficacy test ranking method, which were later incorporated in the logic tree. Moving on to the methodology, in the methodology part, our Kishanganj district was basically divided into 175 number of grid points, and the logic tree was also used, where we had different weights for different GMPs. In the PSHA methodology, we have to compute 3 basic uncertainties. That is the uncertainty with respect to the distance from the sources, uncertainty with respect to magnitude, and uncertainty with respect to the probability of exceedance of the ground motion parameter, that is the peak ground acceleration here. These 3 uncertainties are basically convolved using the total probability theorem to produce the frequency of exceedance. So we have to, in this study, we have calculated the PJ values corresponding to 2% and 10% probability of exceedance in 50 years time period, and the final PJ maps were obtained corresponding to MC, that is the maximum considered earthquake, and the CLE, that is the contingency level earthquake conditions. So we can see the variations of PJ values in the 2 maps for the Kishanganj district, and where the PGA obtained at each 175 grid point were finally interpolated using Kirkin interpolation to obtain the smooth variations. And finally, we can, in the conclusion, we can conclude that the Kishanganj district, the PJ values are varying from 0.25 to 0.39 G for the MC condition and 0.095 to 0.17 for the CLE condition. And we can see the various districts that are the various parts of the district that are more prone to higher PJ values. And these maps are basically for the bedrock level, but the study can be further taken out for the microzonation purposes and for the district and level planning authorities. Thank you.
Okay, thanks, Rashid. It was really very quick. So I request Mr. Ravindra K. Gupta.
Yes, ma'am, I'm here.
Yeah, please. Please go ahead with the presentation.
Yeah, one second, madam.
Please zoom it. Good afternoon, all judges. Myself, Ravindra Kumar Gupta, PhD student from IIT Assam Dhanbad. My topic of presentation is joint modeling of HBSR curves and the dispersion curves for seismic site characterization of Dhanbad city. This is actually the technique-based paper. So please come downside. Yeah, downside. Yeah, methodology. Yeah. Yeah, okay, fine. The methodology had 3 steps. In the first step, we feed HYV and dispersion data to VFSA module. And in the second step, we give priori information with search space 20%. Then we change the control parameter after examining the synthetics and the objective function variation. After that, we estimate the uncertainty using the PPD and PCM statistical tool. PPD is actually the posterior probability density, and PCM is the parameter correlation matrix. Now go to the result, please. So here I am showing the synthetic test of HBSV and the relative diffusion dispersion curve. So you can see here the red one is showing the computer data and the black one is the observed data. And here is the good matching by using the very fast interlearning optimization technique. So the figure E shows the best shaper velocity model, and figure C is the PPD plot. That is a posterior probability distribution plot. PPD shows the VS and the layer thickness, and the colored portion of PPD represent search ranges. Hotter and red colors indicate a higher probability that the true velocity will found at that value. And the figure F is the PCM, that is the posterior parameter correlation matrix. Actually there are 4 parameters: Poisson ratios and shaper velocity and density and So each model layers consists of 4 independent parameters: Poisson ratio, shear velocity, thickness, and density. The correlation values range from -1 to +1, and the synthetic and symmetric above the diagonal of the matrix. For sake of clarity, we only show value below the diagonal. Off diagonal colored squares indicates cross correlation trade-off between the corresponding model parameters. Diagonal element represent the autocorrelation, that is they perfectly correlated with itself. Hence they are identically one for all values. In simple way, the model parameter correlation matrix provides an estimate of the strength of constant imposed by data. So for real data example and validation of result, we have done the same thing. Here we can see the in PPT plot the acceptable model range is very narrow. That means we are getting the very more reliable result by using the two different data sets of HBSR and dispersion curves. And also we have validated out means technique using the litholog data, and we can see at up to depth of 3 meter and around 20 meter, we are getting change in the lithology geology, and according to we are getting the different velocity range. So
Yeah.
I will now
I think Mr. Gupta, it's done.
Okay, ma'am.
Yeah, thank you. Do we have the next speaker? So Rudra Karmakar,
Yes, ma'am.
please. Try to finish in 2 minutes. Now we are running out of time. So
Okay,
somehow we have to cut down.
Okay, I'll do it, ma'am.
And Mr.
present?
S.P. Maurya is here.
No, ma'am. His presentation is not with me, but the last Ms. Yaya Rasool will be there.
Yeah, Rasul, and did Priyanka has come back?
Yeah, Priyanka, are you there? Can you hear us?
Okay, so Rudra, please present.
Yes, ma'am. Hello, good evening, everyone. My name is Rudra Karmakar, and I am pursuing IMTech from IIM Dhanbad. So today I am going to discuss about the Hindu Kush primary seismicity and seismic B value. So to identify why we have to find the V value. So to identify a precursor phenomena that could be used for the earthquake prediction and all. So we all know that in Central Asia, the Pami Hindu Kush region is the most active zone and intercontinental seismic activity.
There is no voice. I think we lost Rudra.
Rudra, we can't hear you. Are you there?
His PPT is also gone, I think.
Sir, I stopped the presentation
Okay.
to check what's going on.
Yeah.
I don't think he can hear us. I don't know what's going on.
Maybe we can have the next one, and then he can join.
He can come back. Okay, ma'am. Okay, ma'am.
Yaya Rasool.
Yes, ma'am.
Okay.
Just 1 second.
Thank you. Hello.
Yeah, please go ahead.
My name is Yahya Rasool, and title of my presentation is Evaluation of Seismic Hazard for Kishanganj, Bihar by Deterministic Approach and Comparison of Seismic Declustering Methods for Bihar, Nepal, Himalayan region, India. In this work, efforts have been made to prepare deterministically the seismic hazard map for Kishanganj, Bihar for considering worst case scenario, that is maximum credible earthquake. As we can see from the figure, this pink patch represents in figure 1, pink patch represents Kishanganj. It lies in the vicinity of several complex faults, including Himalayan thrust fault, which makes it more vulnerable to seismic risk. And for our study region, there was absence of ground motion, region-specific ground motion prediction equation. So we have adopted the logic tree approach, considering four different GMPs and giving the different weights. And for declustering purpose, we have used 3 different algorithms like Reisenberg 1985, Gardner and Knopp of 1974, and stochastic declustering algorithm, which was proposed by Zhang et al. 2002. And we have found the suitable one for the declustering also. Now the methodology, as we can see from figure, it shows a logic tree, and in which different weights have been assigned to different magnitudes and different GMPs in order to get the final GMP value, in order to get the final value of PG. Now scroll up, please. And now analysis. As we can see, these 3 plots are the final analysis for declustering, which shows the distribution of main shocks around the Kishanganj for 3 different approaches like Gardner and Knopp of 1974, Reisenberg 1985, and stochastic declustering algorithm, in which Gardner and Knopp of 1974 removes much number of earthquakes after declustering. Now scroll down, please. Now results. This figure 11 shows the seismic hazard map for Kishanganj, which the red color represents the higher value of PGA. So southern region and some part of eastern region showing higher values of PGA. So these are more vulnerable to seismic hazard. And this is the acceleration response spectrum for our region, in which region 3 and region 4 shows higher values of spectral acceleration than suggested by Indian standard 1893 2016. Now conclusion. Reisenberg 1985 and stochastic declustering method, which was proposed by Zhang et al. 2002, comes out to be stable for Bihar, Nepal, Himalaya region, and PGA ranges from 0.25 G to 0.37 G in the entire region of Kishanganj, with southern and some part of eastern region more vulnerable to seismic hazard. Thank you.
Thank you, yeah. So, do we have Rudra back? Or Priyanka?
No, Rudra is not here, and Priyanka is also not here.
Okay. So, Uma sir, now
let us start the discussion, starting from first presentation by Karthikeyan. If you have some questions on the signature of post-seismic ionospheric distribution associated with magnitude 7.6 Peru double earthquake. Have you any question from audience?
No question in the chat box, sir, just for your information.
So next presenter is that Mannat Khanna.
Yes,
His topic is estimation of site response using HVSR technique for northeastern region India. So any question on this topic from Mannat Khanna?
If not, then I have a question for her.
Yeah. Sure.
Manat, can you put on your video, please? Yeah. So you have estimated the alluvium thickness in your study as well, but I could not see any figure, like how much is the alluvium thickness estimated?
Ma'am, we have not estimated the thickness because we didn't have the velocity model for the layer, and we need that even if we have the predominant frequencies, we need either 2 of the 3 parameters. We have just, from the knowledge of the geology of that area, from other authors, we know the local site, local geology. So from that, we have said that our results seem to be consistent with the reported geology of the area, but we have not estimated it.
Okay, so like based on the available literature, you identify that it's coherent.
Yes, ma'am.
Okay. Okay, thank you.
Thank you.
So next presenter is Priyanka. Priyanka is not presented, I think.
No, sir. Oh.
Yeah, then next presenter is Indubala on topic the Koda wave attenuation characteristics for the Kutch region, Gujarat. Have any questions from audience to Indubala?
Indu is here, and then I have a question. Actually, this session is quite challenging for me as well.
Yeah.
I am not from the same field.
Indubala, can you on your video, please?
Indubala, she's here, but she's not responding.
Okay. So we can move to this Daitreong. If any question from him on seismic hazard analysis using deterministic approach for Arunachal Pradesh, India. Any questions?
Hello.
So
Please.
Indubala is here now.
Okay.
Yes, ma'am.
Indu, can you put on your video, please? I have some question for you.
Oh, okay, ma'am.
Yeah. So in your work, you have shown like these attenuation values which you have worked upon, and in the result you have put a remark that it can be used for hazard assessment.
Yes, ma'am.
So how it can be used for hazard assessment? Just give me a brief.
जैसे मतलब क्यू नोट वैल्यू है जो हम एस्टिमेट कर रहे हैं, क्यू नोट और जो रिलेशन है हमारा फ्रीक्वेंसी डिपेंडेंट रिलेशनशिप है, तो उसमें क्यू नोट की वैल्यू जो हम सोर्स पैरामीटर एस्टिमेशन के लिए भी यूज करते हैं, और जो स्ट्रॉन्ग मोशन सिमुलेशन टेक्निक्स हैं उसमें भी यूज करते हैं, तो उसके लिए हम मतलब
आपको जो देखना होगा वो ये कि हम कैसे यूज करेंगे, करते हैं ठीक है, बट हाउ मतलब आप उसको कैसे आगे यूटिलाइज कर पाओगे, दैट यू नीड टू लर्न. सो दिस इज अ सजेशन.
Okay, ma'am. Thank you, ma'am.
It will be more effective, no?
Yes, ma'am. I will.
Yeah. Okay. Thank you.
Thank you, ma'am.
I think Rajiv Kumar is not presented.
No, sir.
So then Rashid, we come to on Rashid, the 1D non-linear seismic ground response analysis for various locations in Dhanbad city, Jharkhand, India.
So Rashid is not okay. He's back. He's here.
He's here.
Yeah, he just joined again.
You on your video, please, Rashid.
Rashid, can you please switch on your video? Oh, he's disconnected again. I think he's having network issues.
Okay. Then we can move to the Ravindra Kumar Gupta.
So I am here.
Yeah, on topic joint modeling of horizontal to vertical spectral ratio and dispersion curve for seismic site characterization of Dhanbad city.
Yes, sir.
So any question from Ravindra? From audience? If not, then I have a query from Ravindra that which method you have used for this dispersion curve analysis?
Sir, I have used Baum-Herman code.
Which one?
Baum-Herman code, sir.
Okay. So which that the code basically, that which method? Spatial
Yeah, sorry, sir. Actually, sir, I have used MSOR data, multi-channel simulation with one receiver.
No, I'm asking about which method you can use. That is frequency wave number or spatial autocorrelation method for generate the dispersion curve.
Sir, actually, it is spatial autocorrelation method, sir.
Spatial autocorrelation. Okay, then what are the velocity range you are getting from this area? Because this is also a kind of alluvium.
Yeah, sir, I am getting from 100 to 1200 meter per second, sir.
So 1200 at what depth?
Sir, at 60 to 80 meter.
So see, what are the predominant frequency in that area?
Sir, about actually, sir, it is varying because Dhanbad is a very complex geology. So
yeah,
sir, it is varying up to means 7 to 20.
7.
Yes, sir, 7 to 20, sir.
7 to 20. It's quite high.
Yes, sir.
The sedimentation is very, very low, I think.
Yes, sir. Yes, sir.
Okay, then thank you. Then Rudra Karmakar is there.
Yes, sir, he's here.
Yeah, can you put on your video, please?
He wasn't able to finish his presentation, sir, because he disconnected.
Okay.
He's still not responding. Mr. Rudra, are you there? Can you hear me? Can you hear us?
I think he still have the connection issues.
Yeah, I think so, ma'am.
Yeah, sir, but can we count him as presented because he was there in the initial presentation?
He should be counted as presenter because problem from networking side. He is helpless actually.
Yes. Okay.
So this is last presenter is this.
Hello, ma'am.
Yeah.
Yeah, that's Rudra.
Rudra.
Sorry, ma'am. Actually, I lost connection, ma'am. So sorry, and sir.
It's fine, Rudra. So you can put your video on and maybe brief us in 3-4 lines what you wanted to show.
Actually, ma'am, in B value, I find the B value in 3 methods. Actually, one is like GEDMAP, and other is from GR Richter law, and other is maximum likelihood. We know that the Aki method also, and I.
Okay, good.
Thank you so much, sir. Yes.
Rudra, we can't hear you.
Oh, ma'am, he disconnected again.
Okay. So, sir, you can take the call now.
Yeah, this is last presenter is Mr. Rasool is there.
Yes, sir. Yes, sir.
So his topic is on evaluation of seismic hazard for Kishanganj, Bihar, and comparison of seismic declustering methods for Bihar, Nepal, Himalaya region. So
Yes.
if you have from audience any question to Mr. Rasool.
Excuse me, sir.
Yeah.
Can I put question?
Yeah, sure. You are
Sir,
welcome.
yeah, yes. I am from Nepal. I'm Tribhuvan University, Nepal.
Yeah, sure. You can put the question.
Yes, you have told that you have used 3 methods or maybe 2 methods: Reisenberg method or
Gardner and Nabob 1974 and Zong et al. 2002. 3
yes.
methods.
What is the outcome and which one is suitable for the Himalayan region? Could you please tell?
For Bihar, Nepal, Himalayan region, we have used different MATLAB codes and R codes, and finally we conclude that Reisenberg 1985 and this stochastic declustering method that was proposed by Zhuang et al. 2002 comes out to be suitable. I can say suitable, more suitable.
I mean, you say Reisenberg method is suitable for that region.
Yeah.
And your finding tell that most of the dependent events are removed by the Gardner and Nabob method in your presentation.
Yes.
Now you are telling Reisenberg is suitable, and when you present.
Yeah. Actually, if more number of dependent events are removed, that means it will underestimate the B values. If we remember that if the more number of events are removed, then it can. We have analyzed the past literature also. Analyzed the past literature like B values, the variation of B values for that area also. So it comes out to be, it removes sometimes Gardner and Nabob removes much number of independent events also. That is earthquake events. It removes the earthquake events also. So it must not be suitable for that.
Okay, thank you very much.
Thank you, sir.
So this is the last presentation discussion in this session, and session was very successful, and Most of the paper is relevant to this theme, basically natural hazard. And most of the presenter maintain the time because they know that it's a very short presentation of PowerPoint in this poster session. Basically, this is unique kind of things to express their things in 2 minutes. So this is also a learning lesson to how to tell this your work in 2 minutes. That's a smart thing is there. They can learn from this. And most of the presenters are present, but only 2 are not present in this list. So 10 presenter was there. So I request our reporter is there, that Mr. Abhishek is there. Abhishek. Dr. Arora, you know Abhishek?
No, sir, I am not aware of him.
Yeah.
So, Walia sir, this session is almost.
Yeah, I noticed that you people also are very, very efficient, and with lot of discussion, you have finished everything on time. So
Yes,
we are
sir.
very, very happy and really obliged to Professor Umashankar ji and Dr. Tanvi Arora madam. But I didn't see Abhishek interacting. Probably Abhishek, you are there or you are there? Yeah, Abhishek, would you like to say something as a reporter? No, because he was not interacting also, so it's okay. But he was there. He's there now, organizing team.
Yes, sir. He's there. He's just not
He's
responding.
there. Yeah, towards the last. It's okay. So I am thankful to the session chair, Professor Umashankar ji, and co-chair Dr. Tanvi Arora madam, to have taken out time for this excellent interactive and most difficult poster presentation session.
Just sorry to interrupt. Wanted to take a picture with everyone. Just
Yeah, so before ending the session, I would like to request you all to kindly switch on your video so that let us have a photograph, and it will be sort of memory for all of us. Till the end, there were more than 66 participants were there. Now only in the process of discussion, around 13, 14 participants, they have gone out. So still I would like to request all of you, Mannat madam, Yesha, yeah, Mala Bhagya madam, Saurabh Barwa sir, if you are there, Rudra, lovely, Abhishek. Yeah, those who are there, let them switch on their video for just for 30 seconds, not for very long time. And if you are there at a place where you cannot, don't switch on. You cannot switch on your video, don't worry. Your name will appear. Your name will still appear. Thank you, Saurabh ji, for excellent presentation and to be there with us. Yeah, Himanshu ji, if you are there. Yeah, I think many people are there, but they don't like to switch on their video. It's okay. So organizers, you can click some photographs. There till the end, there were more than 66 participants. Now only 48 are there. So around 18 participants, they towards the last part of discussion, they have gone out. So it's okay. So thank you everyone for being with us.
Sir, excuse me, sir. Can I ask a question, sir? My name is Rudra Karmakar, sir. Actually.
Yeah, Rudra ji, you can ask. Yeah.
Sir, actually, मेरा sir network sir issue हो रहा था. Sir, will I count as a presenter or sir absent? No.
For during the poster, no.
Yes.
You are counted as presenter. There is no issue in that.
Okay, sir. Thank you so much.
P-value study for Hindu Kush Pamir region.
Yes, sir.
Yeah, your poster was there, but finally your voice couldn't come. So it's
he
okay,
tried lot. He tried lot.
Sir, I have joined 3 to 4 times and I was disconnected again and again. I don't know.
Our chairman is very generous and he could understand, go through your poster and understood everything.
Okay, so thank you so much.
Yeah, thank you everyone. Now, organizing team, is there? And Abhay ji is there? Abhay Bansal?
Sir, before we close this session, I would like to thank you and organizers, because this was the first poster experiment in India, and we both were there, myself and Uma sir. So I think it's really an honor for considering us for this experiment. So this
Thank
is
you very
really
much.
is really so thankful to you and all the organizers.
Yeah,
it was very well done. Yes, sir.
Yeah, actually we wanted to do it in a physical mode, but COVID restrictions, of course, has put on some SOPs. But definitely this poster presentation section was very well managed by both of you. Thank you very much.
Thank you, sir.
Thank you, sir. Thanks a lot.
It is a successful section.
Definitely, sir, definitely.
It's really praiseworthy effort on behalf of the organizer, Professor Deveshwalia. Thank you so much.
Thank you, sir. Thank you, sir. So, dear participants, now we are going to wind up the session, and just to tell you that tomorrow we are going to start at 9:40 sharp, because there will be one of the excellent lecture, and it is the Krishnan medal, MS Krishnan medal is there, and the topic of tomorrow morning presentation is earthquake cycle and seismic hazard in the Himalaya, space geodetic perspective. So it is one of the very good presenter and the presentation. So I would like to request you all to be there at least 10 minutes before. Kindly join us by 9:30, so that you are all these presentations, everything is for dear participants. So don't miss such an opportunity to witness the program. So with this, I would like to thank all of you once again, especially the morning from the inaugural session, then the second technical session, then the third technical session, and then the very important fourth technical session. And probably again tomorrow we'll have little more hectic program, wherein some of the invited talks are there. They are the awardees, and then there are some oral presentations followed by the poster presentation like today. So thank you participants once again to be there with us whole day, and probably tomorrow more numbers should be there. Last important announcement is that this program is being telecasted live on YouTube, and you know that once it is there on the YouTube, it is going to remain forever. So if by chance anybody has missed any part, you can view it, you can go through it. The link to the YouTube is already posted during the program, as well as through email to you. So you can anytime consult, anytime you want, you can go through any of the material, any of the discussion. And most important part of it is, the last important thing is that you can have the cross interaction or networking in the times to come to gather more knowledge. So with this, we have come to an end, and see you tomorrow, day 2 of the 58th Annual Convention and the IGU, this national seminar on natural hazards. So see you, dear